the INAE Technology Conclave 2026. We begin this session with a plenary talk on a subject that lies at the heart of the global technology revolution and is central to India's vision of becoming a global hub for electronics manufacturing and innovation. It is my privilege and honor to invite Professor Shanti Pavan, FNAE NT Alexander Institute, Chair Professor, IIT Madras, to deliver the plenary talk on the theme Semiconductor Technologies. We are indeed privileged to have him with us today to share his insights on the latest developments, emerging opportunities, and future directions in semiconductor technologies, an area that is pivotal to the growth of artificial intelligence, communication systems, computing, automotive, electronics, healthcare, and strategic technologies. May I now request Professor Shanti Pavan to kindly deliver his plenary talk.
All right, good morning, everybody. My talk is titled Semiconductor Technology and Atmanirbhar Bharat. The outline is the following. What is semiconductor technology really? Matters for India in numbers, historically. it has to be packaged and mounted on a board. So, packaging technology is basically again another piece of the puzzle, which turns a fragile die into something that survives on a circuit board. Once you make the chip and you make millions of them, we need to be able to verify and make sure that every chip actually works at speed under real conditions. So, testing is another very, very important piece of the puzzle, because you do not want returns from the field. Systems engineering is making thousands of these pieces work together in a phone, in an EV, in a satellite, what have you. And there is no real one master of it all. It is basically an ecosystem of really cutting edge technologies all coming together to make something that is immensely relevant in practice. However, when you look at the value chain, it turns out that the design of the chip or the integrated circuit adds 50% of the value of the chip, right, even though it is only a fraction of the capital invested in the whole IC manufacturing process. So, the rest of it, fabrication, EDA tools, everything else, packaging, etc., basically do of course add value, but design is the one which adds the most value. And given this economics, well, the most prevalent model today, which is very different from what it was maybe 40, 50 years ago, is the fabless semiconductor house model, where you have a company which designs the chip and owns the brand and the IP. For example, these are Qualcomms, the NVIDIAs, the MediaTeks of the world. So, they make chips, they build systems with these chips, but they, when I say they make the chips, I mean that they design the chip. The manufacturing of the chip itself can be done elsewhere, right. For example, that's done in the foundry. All of you are sure of, I'm sure have heard of foundries like TSMC and Global Foundries. These are manufacturing houses whose only job is to take the design from the fabless design house and make chips, right. So, they are and in some cases package them. Then there are what are called OSAT partners, whose job is to assemble, package and test the finished chip, and these are the ones that these are the companies that take these millions of chips coming out of the foundries, test them as per the recipe of the fabless company and ship them out to customers, right. So, the fabless company never touches anything about a factory, does not touch a factory, but yet keeps most of the value, right. So, that's the power of the fabless model, and as you can see, most of these fabless design houses have traditionally been headquartered in the US and in Europe. Most of the foundries have been in Asia, and same can be said for assembly and so basically the high value part has traditionally been in the Western world, whereas the low margin parts of the whole process have been concentrated in the eastern part of the world. So, to summarize, well, when somebody says semiconductor technology, it's like the proverbial blind men trying to kind of figure out what an elephant is. To each person, it means something else, and every specialist is of course right about their part, but wrong about the whole. So, to summarize therefore, semiconductor technology has got many facets: materials, process technology, equipment, modeling, analog and digital design, testing, tools, packaging and so on. But the bottom line is that it is the design which alone captures about half of all the added value in the chain. Now, why semiconductor technology matters for India in numbers? India's electronics imports crossed about $116 billion in 25-26, and out of this, about 50% or maybe about 40% is the semiconductor market. Electronics is not merely semiconductors, there's other parts to it, but the semiconductor market is about 50% of that, and is expected to grow to about 110 billion in just a few years. Now, all of modern defense systems, satellites, telecom networks all run on chips. So, it is not merely a consumer market, it is also very important for our national security, right. And being reliant on external foundries, external designs and external chips is basically a strategic vulnerability, because we cannot trust our own chips, and it's not, therefore, it's not merely something that a consumer is not given a choice of chips, but now it's a strategic vulnerability. All of you are aware of what problems this has caused with respect to defense. Now, so to summarize why this matters for India, electronics is important not only commercially. The electronics import bill is already comparable or more than our oil import bill, and our semiconductor market is racing towards the 100 billion mark very soon, and chips sit at the heart of national security, not just commerce. So, given that semiconductors are so important, historically why have we lagged? That is what I want to talk about next. Semiconductors is a very, very capital intensive business, and a single modern fab can cost several $1 billion and can take years to pay back. And this, I mean, for a very, very long time, until about 30 years ago, we were, within quotes, a poor country. So, any industry that requires a lot of capital investment was automatically put on the back burner, saying we have more important priorities. And when the economy opened up, still the risk and the capital intensity of this whole effort pulled our best engineers towards software, where returns are guaranteed and faster, right. And more importantly, software services. We will come to that a little later. And semiconductor manufacturing is a very, very, what I would call bleeding edge technology, and therefore, export control has also historically restricted access to the most advanced equipment. And finally, it does not make sense to have a fab without, without demand and suppliers. So, we do not have an ecosystem, right, without and there is no supplier ecosystem without a fab. So, it is like a chicken and egg problem, and so this is basically, has remained dormant for a long while. Post liberalization in the late 90s, we saw a lot of growth in IT services and software, but not hardware, and for good reason, because hardware is a lot more risky than software services. And until recently, policy attention and funding did not match the scale of the challenge. It's not for lack of talent, mind you, because a lot of global majors, so every major chip design company has built captive design centers in India for execution of complicated, cutting edge, bleeding edge chip design products, but not for product ownership. And investors always backed, and I would say even continue to back, fast return, software, app type companies, food delivery. These kinds of things are much easier to attract funding for rather than capital intensive, risky chip bets. And as a consequence, domestic electronics mostly assembled imported chips. There is no homegrown MediaTek, for instance, or Mellanox, Mellanox was basically the company that came up with, this, with the InfiniBand standard, which is a standard for networking. It was acquired by NVIDIA for good reason. MediaTek, of course, everybody knows, is a major player in the cell phone market, and many cell phones basically all use MediaTek chipsets. And it's a Taiwanese company. Now, furthermore, as I said, design tools are also extremely expensive, and licenses for these tools basically can cost, more than the entire seed round for basically maybe a software services company or a software startup, and therefore our both our VCs as well as our policy was built for IT exports, not for chip design. The recently announced design linked incentive scheme, of course, is a good thing. It's changed the math. There have been many startups that have been supported by the DLI scheme. Many have raised venture capital. Many chips have come out. So things are changing. So that's the lining, the silver lining on the cloud. And RISC-V basically is an open instruction set, which basically means no expensive license just to start designing a microprocessor. So there are many startups basically trying to design RISC-V processors. The compelling case for these startups is to be able to make secure processors that are based on open source, so that it helps our strategic interests. With 5G, defense, satellite and EV programs also basically making big headways, I think the market is ripe, or the system is ripe to be able to support more semiconductor startups. Finally, many engineers who built their careers at Qualcomm, Broadcom, NVIDIA, etc., are now founding their own companies. These are what I would call mid-level, mid-career people who've had a lot of experience and now have a lot of hunger, as well as they know what to do to be able to make a viable product. Having said all this, the incentive is still capped well below the real cost of an advanced chip, and every design still depends on a foreign foundry, right? Because the manufacturing of the chip in any advanced technology has to be done abroad. So to summarize, historically we have lagged because fabrication demands massive capital, and talent has been pulled towards software instead of hardware. And there have been global barriers, and we've been stuck in a chicken and egg problem. Our design ecosystem has stayed service first with no capital or role models for chip products. The DLI scheme and the RISC-V are now changing that math startup by startup. So what are our strengths? Well, Bangalore, Hyderabad and Chennai already host large chip design centers for global firms. So every semiconductor company that you can think of has a big design center in Bangalore that employs Indian engineers trained by Indian schools. And as I said, a deep English-speaking engineering pool well suited to chip design tools and flows. We have a large and fast-growing domestic market that gives partners a reason to invest here, not just sell here. There is sustained government commitment for the first time via the India Semiconductor Mission. And on the academic side, the Chips to Startup program already engages a lot of academic institutions. There is a large diaspora of Indian engineers leading roles across the global semiconductor industry. So to summarize, I think three things are in our favor. We have a large pool of design talent, we have a fast growing market, and we have government commitment. So, what can universities and academics do? Well, for a large part of the last 40 years, we have basically been stuck, our engineering education has basically been stuck in a happy, consistent loop that produces a whole, that's basically not satisfactory for a bunch of reasons. So, parents are happy to send their children to universities, and the universities basically, and students are happy to go to the universities not to pick up core knowledge, but to get a degree. And the the companies are happy to hire any engineer because all that they were looking for were a pair of hands to do IT work. And therefore, the students didn't really care about what they were learning in school, and therefore, there was no pressure on the universities to hire good quality faculty members or hold faculty members accountable for what they teach in the classroom. And so, the universities were basically collecting fees from parents to give students a degree after 4 years. Students didn't care that they didn't learn much because, well, the companies were hiring them not for what they learned in those 4 years, but just as a pair of hands. The parents didn't care about any of this because, well, their kids got jobs at the end of 4 years. And the companies didn't care about this because, well, they were just looking for warm bodies. And so, this is a consistent loop where basically there's our students are not they're not adding value to themselves at the end of a 4-year degree. Now, so as I said, IT let almost anyone in without demanding deep fundamentals, and well-paid jobs came without mastering core subjects, and fees kept flowing regardless of what was taught. Unfortunately, a core area like semiconductor design asks for a lot more. It demands a deep understanding of the fundamentals across physics, circuits, mathematics, and so on, and qualified faculty who can teach it, and students who are willing to put in work across multiple semesters. Well, the hope is that the churn AI is bringing to IT employment may finally push undergraduate programs towards deeper and more serious learning. And how can we generate a lot more engineers who are, ready for the job? Unlike today, where companies pretty much hire smart kids and have to train them up on the job, sometimes for as long as 2 years, to make them battle ready. So, it's very well feasible, as it's been done in a few elite institutions in the country, but this has to be reflected at scale, right, across tier 2, tier 3 institutions, and this is very much possible. And there is a lot of national, recognizing the fact that we have to churn out semiconductor professionals at scale. The government has several schemes, for instance, the Chip-in Center, which basically is a way of giving virtually, licenses to CAD tools, which are really, really expensive for any institution to buy, virtually free of cost. They're hosted by CDAC, and anybody who's interested actually can use, can make their own chips through subsidized access to, the semiconductor fab in Chandigarh, right. So, the government is indeed doing a lot to be able to foster this culture of design across tier 2, tier 3 institutions. And, of course, none of these areas is, receives as much press and glamour as the software IT type industry, but all of this is essential if we need to make India a design powerhouse. The fact we should also be able to continuously refresh curricula against real industry flows, not just textbook exercises, and faculty training is as important as training students, because these are the people who are going to be working with the students in the universities, making a difference. And this can only be possible if there are durable industry academia partnerships. And so to summarize what universities can do, universities must be able to teach chip design as a hands-on craft using shared national infrastructure, build depth in seemingly less glamorous but essential research areas, invest as deliberately in faculty and partnerships as in students. And what can government do to engage academia? Well, let's see what's already working. For the last 30 odd years, the Ministry of Information Technology, whose name has gone through several avatars, has been funding what's called the Special Manpower Development Program, or SMDP program in VLSI. And what they did was to basically give tools to a whole bunch of educational institutions so that students could be exposed to industry standard tools. They ran a lot of faculty development workshops where faculty were trained in design and so that they could teach their students. MIT funded a lot of academic institutions for chip design and research, and now, SERB, now ANRF, funds foundational semiconductor research. CDAC's Chip-in Center gives free shared access to electronic design automation tools, which no single university would otherwise be able to access on account of their cost. Chip fabrication shuttles, from Semiconductor Limited at Mohali, takes academic designs through to real silicon, and so conceivably today, a student, even an undergraduate student, can design, fabricate, and test a chip at in the university. However, one must understand that deep expertise takes sustained effort. And time constants of chip design and testing basically are long time constants. So for instance, it takes maybe, depending on the complexity of the chip, of course, it can take as long as a year or a year and a half to design the chip, maybe another 6 months for the chip to get fabricated, and another couple of months for testing. So we're basically looking at almost a 2-year cycle for design, fabricate, and test. And because people are learning, it's entirely possible that a single design cycle does not work, in the sense that you make the chip and the chip, there's some problem. Well, you learn from failure and fix these bugs the next time around. So a good estimate is to say you need 2 chip design cycles to make working silicon. And if you also add along all the time required for the coursework for a student to be able to get competent in the area, that's at least another year. So basically, we are looking at a 5-year cycle to be able to train a bunch of students to be industry ready. And this is where programs like MTech, which are probably adequate for a whole bunch of other areas, simply do not work in the area of chip design, because MTech students are taking courses for about a year or a year and a half, and they have a 6-month project where they really can't do much, right? So PhD programs are basically where students, top quality manpower can be built. However, the uptake for the PhD program basically is somewhat poor in our country, simply because after a master's program, given the nature of a lot of industries where they're looking for, I would say, kind of manpower which is not deeply trained but good enough to run tools, companies are happy to hire them at much larger salaries than what the PhD can pay, and which is why we do not have students signing up for PhDs in this area, because the job market is so hot. Increased funding is also needed in tier 2 institutions so that they can design and build chips too, and not just restricted to the elite institutions of the country. And government funded summer fellowships for faculty to spend time in industry, not just visit them. So this I think is a viable thing where the summer vacation of faculty in institutions can be utilized so that they can go and spend time in industry. And of course, industry has no incentive to do this because they're only going to be there for 3 months. So this is where the government must step in to be able to fund these visits, or at least partially fund these visits, so that faculty can become well versed with with what exactly goes on in industry. They can come back with ideas, they can come back with project ideas that they can put their students on. Many of these ideas may be so risky in industry that nobody would want to spend resources on that. These are ideal projects for academia because, well, there's no risk, and if something comes out, it's fantastic. If nothing comes out, well, you learned a lot. And as I said, these funding cycles from funding agencies need to be long enough to design, fabricate and test a chip, not just design it. And every university, not just a favored few, should be able to get a chip fabricated in the country. So it is important, like what our neighbor China has done, to fund research, not just manufacturing incentives. One must make shared design tools, fabrication shuttles and testing easy for every institution to reach, and commit to long multi-year funding cycles, because chip research, as I just mentioned, typically takes, I would say a 4 or 5 year cycle to be able to successfully design a research quality chip. We encourage faculty, industry sabbaticals and secondments in both directions. I mean, one can always tap experienced designers in industry to come in as professors of practice at universities, and also take academic inputs in drafting policy. So finally, talent, not merely incentive outlay, is the binding constraint, and one must fund accordingly. So to summarize, there is already a lot of schemes available from the government, which has made chip design in universities a reality. About 400 institutions today get access to free tools, design tools through CDAC. But of course, as always, there's a lot of room for improvement, and the key point is to be able to train faculty, motivate faculty to be able to train students through appropriate reward mechanisms and longer funding cycles, so that we can grow chip talent at scale. So semiconductor technology is just not one discipline, it's many. The stakes, economic and strategic, are large, and there's no longer any doubt as to the importance of this technology. Our real strength is people. Our real constraint is also people at the scale this moment demands. So universities and government must move as genuine partners, not as trainer and funder, and I would say government, along with the government, I'd also add industry. So that's all I had to say. Thank you very much for your time and attention.
Very lucid. I think anybody in the audience or elsewhere would be able to follow you. 2 or 3 questions, sort of comments. Ecosystem is what probably is the biggest reason why we haven't made an inroad. I mean, talking about, let's say, a place like Taiwan, 25 years ago, they were nowhere in the scene. They certainly were trying to make inroads. I'm not talking about mainland China. We had ministries, we had enough number of learned people and so on. The students, when we expect them to actually pursue semiconductor technology or take that kind of a thing as a profession very seriously and seek a job, not so high paying, it doesn't happen purely because of what you said, that salaries are not very attractive, the career growth profile is not very attractive. Teachers are even in an even more difficult situation.
Absolutely,
no funding available practically, very little funding available. Most importantly, there's no lab. This is something which is not like you take a hammer and start beating and you get a product. Are we seeing a lot of change in this scenario? I mean, as simply from a distance, if we look at, now we know that there is a gap and we know it's a dire need. Are we really seeing a lot of changes? I mean, we have heard government announcing 2 major initiatives. Tatas have stepped in, 2 new fabs are being created. But I mean, looking at what happened to the Chandigarh lab and what happened to CDAC and so on, are you seeing a lot of change?
Yeah.
And
so,
one other thing, Shantikavan, one other thing is, you mentioned the importance of design 50% and so on, which is absolutely true, but then any hardware, here is where we are not only talking about the logic, we are also talking about the actual physical chip. When the hardware fails, it has to be a material failure. I mean, that part you never mentioned. So being a man from materials area, I thought that I would bring to your notice. Thank you.
So thank you for your questions and comments. See, the good thing we see is that over the last maybe 15, 20 years, every semiconductor design company, IC design company headquartered in the US basically has got design houses in India. These people employ a lot of engineers, and it is now a well-known thing that the salaries here are way higher than IT. I mean, IT salaries, as all of you know, have been, adjusted to inflation, have actually been falling, whereas these salaries are going, going crazy. If I'm not on record, I would say, I mean, fresh master students are basically, earning maybe 35, 40 lakhs a year, and who are trained in design are earning these amounts. So you can imagine why nobody wants to sign up for a PhD, and the kind of traction that design programs, at the MTech level are gaining traction in the I would say the old in the IIT system is basically it's unbelievable. So we have 20 years ago we probably have 15, 20 students taking these courses. Now you have hundreds of students taking these courses. So and as this has been happening for the last maybe 5, 10 years, we basically also see that now a whole bunch of engineers who've been in these companies for 10, 15 years now have had enough experience, and it's not merely enough to design. I mean, the important thing is to know what to design, right? So product definition is basically the key, and so people who had design experience for a while in companies like this also now are in a position to be able to figure out what to design, right? So there's a whole lot of IC startups coming up in India, and as you pointed out, this our unfortunately risk appetite in India has always been very, very small. So we are very, very averse to taking risks, which basically means that we are very happy with IT service industry. We are very happy with design service industry, but taking the risk to be able to build a chip which still costs a lot of money, right? I mean, even if you are a fabulous design house, the amount of money you have to put down to be able to develop a chip is, I would say, several $1 million. And to be able to put that is risky, right? And there's no guarantee that your chip will be a success. So that, I think, risk appetite is something that we still have. And so things are looking up, and I'm positive that things like design linked incentives and so on will kind of boost this going forward. And as you also pointed out, the Tata Fab is a very exciting, is a very exciting development. Nobody now knows how this will eventually play out, but the fact that a fab is coming up with access to reasonably advanced technology is already, I think such a very good thing, because not all chips made today need 2 nanometers and 3 nanometers technologies. A lot can be done with legacy technologies like 28 nanometers, 65 nanometers and so on. So, so the fact that we have a fab in India will soon mean that there will be packaging houses, there will be hopefully people developing semiconductor materials right in India rather than having to import them. All of you probably seen in the popular press, things like, helium gas, which is needed with very high purity, basically is needed in the semiconductor ecosystem, and this has to be imported, right? So, nothing practically is made in India today as far as this ecosystem is concerned, but the fact that a fab is coming up in India basically means that there will be a lot of motivation, commercial motivation for us to be able to develop these technologies, right? So, and of course, the fact that there's a lot of importance now to security, national security in various forms, and so on, is also going to be a big push for people to be able to develop systems and chips within the country. So, I would say we are going on a good trajectory, and maybe the next 20 years will be a very eventful time for those in the semiconductor industry. Yes.
See, I have a slightly different question, in the sense that there has been fabulous design companies also in the startup space for a while. The question is, how do you assess the IPs that has been generated by Indian companies sitting in India? What is the status of those?
Well, see, the IP business is actually a very, very difficult business because unless you sit and you're very close to customers, it's very difficult to design an IP in isolation, right? So, so it is difficult business. I only know of a few companies who made it successfully, and they've also gone through acquisition. But running a standalone IP business in India is actually quite difficult, right? And is risky, because you put in all this effort, and you pay engineers a lot to develop IP, and if you don't find a buyer, then it becomes very difficult. This is in contrast to IP companies in China, for example, and Korea, right? You have Samsung right next to you. You have, in China, you have any number of IC companies next to you. They're all looking for IP, right? And they'll be willing to buy IP because you're so close by, and they can talk to you, and ask for modifications, things like that very quickly. So those IP companies have a big advantage, and likewise with IP companies in the US, where the customers are sitting close by. We've, as I said, this is a chicken egg problem. We've never had system companies, which basically means we never had chip companies, which basically means that we don't have IP companies, right? So, the only successful companies have all been kind of service companies, even in the design space.
Sir, I have a similar context of maybe a question to you, but at the same time it is a very, very challenging, because we don't have although we have an institutional ecosystem for semiconductor integrated circuit IP ecosystem, SICLD under the CGPDTM Government of India, but registration is very less there, and there is no manpower who can evaluate such kind of application. That intellectual property application is coming from SICLD. How? Because you are such a great expert, because I know you, but how you are bringing change in the institutional platform to make the difference? Because awareness is lack of, there is a lack of awareness, because I am also a PhD in intellectual property, but when I talked about semiconductor integrated circuit layout design, I am also not aware. So if I am being a national expert working in the Government of India, I do not know how do you think that the institution or the organization people will able to know? I think there is a need of capacity building in a large way. It is very, very important, sir. In fact, my daughter was asking some other day about semiconductor, but I was not able to give answer. This is I will request you and urge you, capacity building, the way intellectual property capacity building, I think Madam Suchita Mekran is here from ICMR. Now we have a patent mitra, but how we can develop a SICLD mitra in the country? That is my submission before you. Thank you.
Yeah, a couple of things. As I said, the Ministry of Information Technology has been doing its bit to basically lower the barrier to entry for chip in the chip design area. So by giving out free tools to pretty much any institution that asks, right? I mean, the barrier to entry is almost zero, and therefore, in principle, anybody in these 400 institutions across the country will be able to access these tools and design chips. However, you know, as I think Professor Manna pointed out, I mean, there is a serious problem with faculty across. I mean, there's a big, I would say, gap in training of faculty in tier 2 and tier 3 institutions. And again, the reasons are not hard to fathom, because people who are good with design and so on learn and then go and get employed in a company, right? I mean, they can get paid a lot more. So traditionally, tier 2 and tier 3 institutions have been battling this skill gap in faculty who are absolutely necessary to train students. Having said that, well, I mean, the elite institutions of the country have done their bit in terms of putting out courses through NPTEL, right? All of you are aware, not merely in this area, but today if you want to learn anything, you can go and find the course on NPTEL, which basically teaches you what to do. So the same holds for the VLSI area, and so there are a lot of very good course materials that are not merely on NPTEL, which are not merely used by students in India, but actually, industry and students abroad, right, to train their students, train their engineers and so on. As regards intellectual property, see, in the IC design area, it's actually, across the world, what I have seen, what I am aware of, is that it's very, very difficult to pursue intellectual property in the area of semiconductor design. And the reason is the following. See, it's first of all, it's very difficult to figure out, where a company has used your idea, right? Because this is now, these chips are so huge, and of course, no company is going to reveal what they've done inside the chip. So to catch people, violating IP is very difficult. At the company level, most companies have cross-licensing, IP cross-licensing agreements, which basically means that they can use each other's patents, rather freely. And even if you figure out that some company is basically using your idea, it's now, as an academic institution, it's almost impossible to fight a huge corporate and try to extract royalty and so on. So what universities, at least in the US, have basically done is simply get companies to fund their research groups with the understanding that the students who kind of design, who are trained on specific domains basically will be very useful to companies, and companies recruit them. And unlike our country, in the US, a lot of the companies actually only prefer to hire PhDs in the area. So in our country, a lot of hiring is at the master's level, because as I said, many companies are looking for basically people who are kind of better than average trained, and they can run their tools and know the basics well. So as long as they've taken some courses and learned some basic tools, they're okay. But a lot of US companies basically have, restrict their design hiring only to PhDs, which basically means that there are a lot more PhDs being produced. Yeah.
Yeah. So myself, T. Bhaskar from Tata Steel. Good morning, and thank you for a very lucid presentation. So over the last 2 days, if you see, many of the problems which you mentioned, the chronic issues, that cuts across all sectors. Actually.
Absolutely.
Professor Yadav talked about export of raw materials and importing of finished goods. and no Indian OEM able to design steel plants and so on. So I think the issue is what are we doing about it and what we can do collectively. So one of the things regarding faculty development, the problem of that is already being addressed. The other major issue I think is the cost arbitrage model. Many Indian companies have been successful and very profitable by following, including companies like Infosys and TCS, by following the cost arbitrage model rather than focus on high-end work or value creation. And the same applies to Indian steel plants as well. And that's the reason probably we import so much of high-end steel, because we have neglected this aspect of the fundamental design aspect. Now, are there any Indian companies or Indian examples of very good design in manufacturing? I would say yes, because I think Bharat Forge is one classic example. So this company has attained global leadership by focusing on design, core competency as design. Their design dies faster and better than anybody else in the world, even today. And one of the examples, one of the advantages, or I think long-term advantage of this design competence is that you can extrapolate to other sectors. And that's a classic example how Bharat Forge moved from automotive to defense through their advanced knowledge and competence in design. And if you see the steel plants, which today advanced high-strength steel is one typical example, where Tata Steel, for example, is trying to learn from its the collaborations in Netherlands, UK, and try to develop these steels faster. So collaboration is one way. Technical tie-ups, like for example, the tie-ups which we have with the MIT and Imperial on the academic collaborations, I think that's also helping us to accelerate the design process or knowledge. And the other thing is that once you have this expertise, you can also get it back to the local manufacturing. Like Tata Motors, for example, what they did through Jaguar and Land Rover acquisitions, once they learned to design cars, you see the last 5-6 years how they are becoming a force to reckon with. I think from the INEA perspective, what we can possibly do or what we can think of is that excellence in one sector does not necessarily give you the competitive advantage. When you have the parallel expertise developing across all sectors in a multidisciplinary way, for example, you talked about this chip manufacturing. Chip manufacturing is actually, when you go for advanced manufacturing of these chips, you need silicon wires. I mean, to cut the silicon chips, you need very thin wires, something of purity of tire cords, which we cannot make in India today. So if you want to bring manufacturing in a big way, chips, you have to actually develop those wires and the steel to develop that. So excellence in one sector, other sectors, when collectively it happens through a multidisciplinary approach, and I think that's where there's an opportunity for, us like INEA to, really look at this as a multidisciplinary and approach and design some ways to develop this. Yeah, thanks.
Yeah, I think there's hardly anything to disagree with there. Yeah, I agree with everything you say, and which is why I said, I think there's a lot of excitement about the Tata Fab, simply because of what you were saying, right? The fact that there's a fab here, and they will need materials, they will need tools, they will need, and now, of course, in the beginning, I suspect we'll have to import most of them, but the fact that there is a commercial motivation now to be able to do these things means that there will be a whole bunch of high-tech industry that will hopefully, kind of sprout up around this, so that we build an ecosystem. And I'm absolutely in agreement. It is not just one sector, it is across sectors. And, Bharat Forge is one example of an old company which is doing excellent work. A new startup which I would say is very recent, for example, I can think of, which came out of IIT Madras, is Ather, right? They build fantastic electric scooters, and if you talk, if you see presentations by them, by the research folks, you can see that the amount of thought that has gone into, into every scooter. These are all, I think, early success stories. Only time will tell where this goes going forward. Thank you.
Thank you very much, Professor Pavan, for that enlightening and insightful plenary talk. May we request Professor Santanu Chaudhary, Vice President, INAE, Professor and Dean, School of Advanced Computing, Ashoka University, to please come on the stage and kindly felicitate, sir. May we please have a round of applause? A small announcement, those individual members who have not registered themselves and they are sitting here, you are kindly requested to please register yourself at the registration desk. We now move to another highly anticipated session of the conclave, a panel discussion on healthcare technologies. To deliberate on this vital and rapidly evolving domain, we are privileged to have with us an eminent panel of experts representing academia, premier healthcare institutions, research organizations, industry, and the innovation system. Their diverse expertise and experience promise a rich and insightful discussion on the future of healthcare technologies. It is my privilege and honor to invite Professor Suman Chakraborty, FNE Director, IIT Kharagpur, to organize and moderate this distinguished panel discussion. Joining him on the panel are Professor Ashutosh Biswas, Director, AIMS Bhubaneswar, Dr. Dilip Kumar Chekuri, Chief Executive Officer and Scientist F, AIC-AMTZ Medievally, Dr. Shishir Kumar, Huvel Life Sciences, Dr. Ashok Chaudhary, ILBS, New Delhi, Dr. Suchitra Markan, Scientist F, Indian Council of Medical Research, New Delhi. With such a distinguished panel, we look forward to an engaging discussion on emerging healthcare technologies, innovation, entrepreneurship, and collaborative approach to addressing the healthcare technology for tomorrow. Okay, so Dr. Biswas could not join us due to some medical emergency.
Good morning and welcome to this particular session. And we have very eminent panelists, and I think that whatever time we have, we need to go ahead with the deliberations. We will try our best to be interactive and as much as engaging with the panelists. Unfortunately, Professor Dr. Ashutosh Biswas got an emergency, so he wrote to me that he is unable to come, although he is the director of AIMS Bhubaneswar. Because of the emergency, he is at Kolkata and he could not join. So the overall philosophy with which we will organize the session is like we will consider 5 different levels, and we have very specially curated list of highly eminent speakers who will traverse through all this: technology, translation, integration, equity, and the future. And that is how we will move. And perhaps the central message that we like to convey while we are deliberating on is that the next revolution of healthcare that we are going to see is not to be invented inside just hospitals. It will emerge from the convergence of engineering, medicine, AI, manufacturing, policy, entrepreneurship, and human-centered perspectives. So with that, I would like to begin with a statement that healthcare is perhaps the only industry where extraordinary scientific discoveries coexist with outstanding challenges of inequity. We have robotic surgery, genome sequencing, foundation models in AI which can be applied to such applications, and digital twins, and yet millions still lack access to timely intervention, be diagnostics, be therapeutics. So I think that unlike many other sessions where innovation has been the sole focus, we cannot just simply keep on discussing that can we innovate. And I think we should extend that and discuss more critically that what can we do so that not only we innovate, but the innovation reaches everyone. And that is not an easy thing to do. So in that way, we have divided the entire session into some thematic parts, and different experts, I will approach them one by one with their ideas on that. If we had unlimited scientific capability but limited resources, and that is truly what our nation has, so where should our nation invest first in terms of healthcare? Diseases, hospitals, technology platforms. So I will start with Dr. Chaudhary being one of the eminent physicians and representative of a super specialty foundation. What do you believe will fundamentally redefine tertiary healthcare over the next decade? Will hospital remain center of treatment or become center of continuous intelligence that flows from the hospital to the other parts of the nation?
At the outset, thanks everyone. As rightly pointed that tertiary healthcare sectors and doctors, I think you can see just now published that 80% of research is happening only in the government institutes or R&D institutes. And I can say, if you think of Professor Biswas got busy on a Sunday also, and we also, the clinicians who are doing the research, India is not conducive for the research. Research you have to do with a compromise of your family and social life. That I think if policy system is here, we should think how this medical related academic institutes can go. A single doctor in OPD seeing 200 patients. It is not practically feasible. So definitely there is a need in any sector to develop, be it the outpatient, you can see the inpatient things, and in labs also. Suppose I have a sick patient. I need a diagnosis that he is having infection or no. So what I have to send the culture. Culture will come after 72 hours. I cannot wait. So now the BioFire has come up that giving results in 2 hours. Now you can think of a point of care diagnosis in the emergency itself by a LFA or a microfluidic, can get a report in 30 minutes. That is how it can help. In OPD, lot of hospitals, still the government institutes, the OPD consultation, 60% time is gone writing the prescriptions, taking the history. You can think of voice AI, you can NLP to get the summarize the cases. You can get into that how medicines can be prescribed. And another one is the 30% of OPD prescriptions is wrongly interpreted by the chemist. Suppose you have recent crocin, it become a crocid. So crocin is paracetamol, crocid is a different medication. Only later diffusion is, and everybody know the doctor's handwriting, everybody praise for that, okay, how the doctors write. So these are the way things are happening. Then third, drug interactions. So there we need, suppose you have written a prescriptions, and it is very difficult to know how they are mildly doing the interactions. That way you can think that you can help in a clinician that way. So this is what I told in the OPD basis. If you think of IPD, suppose a radio diagnosis. Radio diagnosis is such a become a huge area, and AI has also come a big way. Suppose I have to go through a CT or MRI to get a report, it takes 1 hour. If I take the help of the AI, what I can do there, I can get a basic report, that is human in the loop. So that means I got the screening done. In the 5 minutes, I can just check through, get a final approval. So that where you can utilize the manpower effectively and talentfully. If I think of the critical care areas, like it was a robotic surgery, the lot of thickness happening, like I do endoscopy or the related illness. So now digital twin has come big way. Even I have 2 projects going on digital twin. How you can at least predict that this patient is going to behave in a next hour. Suppose you know the government hospitals, sick patients, limited infrastructure, affordability is also issue. So you can say that this is the disease likely to go 80% this way. So you can plan your finances, you can plan your resources. So in that way, the first question you have answered that academic institutes definitely need an integration of health tech in a robust way. And for that, only thing that I can this panel discuss, there is the approach is coming that doctors and engineers sitting together. But still the IP issues there, doctor wants the supremacy, engineer wants the supremacy. So this is also a big platform how to address so that it can, they know that they can complement each other. But there is a fear factor of IP. That's why it is also not so much developed. So what happens, doctor is lack in technology, engineer has the technology, they don't know the ground reality how to implement. So that is also another area how we can integrate, so we can get the help. So and then third, you could talk of this, how this tertiary is to go to the primary. I can say hepatitis B, I think this month which is going to World Hepatitis Day in July 28th. Till now, we college of finding the missing millions. In hepatitis B, simple disease, where a single tablet can prevent a liver disease, liver cancer. But every year in India, 10 lakh kids are delivered by birth, at birth point, they are having hepatitis B because the mother is not been tested. So how to do? So you have to go for the hepatitis B testing kit. You can see the kit is available 10 rupees to 500 rupees. So there is no QC. We don't know which kit is better. So I see very often that hepatitis B test is negative. They landed with cirrhosis to me in when I see in a tertiary center. That is a big problem. So how we can make a mandatory QC compulsory so that the testing kit should be better. Then third, how this can be done effectively in a resource poor. Suppose there is now called a dry spot. So what I can do, I can collect the blood spots in a tissue paper and send this sample to the AIMS Bhubaneswar. So in a Koraput and a remote area, the sample has come a dry spot, it gets analyzed by droplet digital PCR, we can get the diagnosis. So there is a lot of ways we can mitigate, even a remote center also, keeping the premier institutes as the hub for the research. I think that is my submission.
No, absolutely, and I think you are spot on. So the tertiary hospitals, they can actually be the highest level of the living lab. If you see the kinds of cases which are coming in, requiring the rapid diagnostics to the AI interpretation, and taking in a loose sense that, the handwriting of doctors, and we all know that, how challenging it can be. Now, of course, it is being digitized, but there is a lot of AI-driven effort to decode, some of those. So I would imagine that the tertiary hospitals would remain as the central engines to come up with the cases and the data for innovation, and bring in the doctors and the technologists together as much as possible to work on that, while the impact should be disseminated all around. And with this very important note, let me now focus to Dr. Suchita Markan, and we have been working with ICMR MDMS, Medical Devices and Diagnostics Mission, for quite some time, and Dr. Markan has been the real building block. I mean, what I would say is that without her, ICMR's innovation in medical device and diagnostics would not have existed in the way in which it is currently having, with the different centers of excellence. IIT Kharagpur also is proud to host one. Now, from the perspective of ICMR, which technologies you think from your experience would be of the highest national priority today? Not just because they are very good technologies or fashionable technologies, but they can improve the health outcome at really population scale. So what kind of technologies you are sort of looking for that?
Thank you, sir, for this question, and I'm happy to be part of this, privileged to be part of this session. So from the perspective of what sir is saying, we all know in this room that the demographic profile of our country, wherein huge lot of population and 60–70% of non-communicable disease burden we have in our country, deaths are happening through the NCDs. Gone are those days from CD, now we are shifting to NCDs. So what ICMR is trying to focus on as a biomedical research organization of the country, to look at the top priorities, Of course, the national health priorities are our starting points. We focus on technology development based on the national health priorities, wherein we have different programs like NCD program, we have program for CD, we have for Anemia Mukt Bharat, so likewise. So those are our priority areas, and what we are trying to do, since we are leading in biomedical research in the country, we cannot just focus on the low-hanging fruits. Like point-of-care technologies, of course, are very close to our heart, because unless you do screening of the diseases, ideally we have to focus more on screening of diseases and treatment rather than going on diagnosis later. They can have lot of referrals as well. So point-of-care technologies for handling basic disease burden like NCD screening, CD screening is our priority. So that is the key thing for which we truly believe that they can really impact the healthcare. But at the same time, we are not just relying on creating these point-of-care technologies and our country being seen as making basic technologies only. So ICMR has come out with very different kind of funding opportunities. We have also launched First in the World Challenge, wherein we want our countrymen to believe that we can produce things which are first in the world. We are also having a specific call on frontier technologies, wherein we are trying to motivate institutes and industry to come together and develop high-end robotic technologies, gene therapy-based products, and CAR T cell-based products. So we cannot, so that's the kind of thing we have to look at. We need to try to create point-of-care technologies to support the screening, strengthen the screening arm, and strengthen our Ayushman Arogya Mandirs of our country, where the primary screening happens, including the community settings. But at the same time, we cannot be looked at just making basic devices and not creating best of the world devices. That's why we are having that mixed kind of a scenario wherein we are trying to promote all kind of technologies in the country, with of course healthcare being impacted more through the primary healthcare ecosystem.
Absolutely, and I think that it is the central message of what we are discussing today, that technology for everybody for the benefit of healthcare. And of course, once we think about that, as Dr. Chaudhary was telling, the challenge is that you have a 10 rupee kit and you have a 500 rupee kit, and quality, regulatory, and all these things are of prime importance for reliability to the clinicians. And if that doesn't happen, the technology will remain at its own pride, but it will not reach the impact. And if it doesn't reach the impact, I think that diagnostics, it is difficult for diagnostics to leave the clinical settings, although we all want that to happen. So the next theme that we are looking forward to while we are discussing this, that for nearly couple of centuries, healthcare has waited patients to come to the clinic or the hospital. And tomorrow, the diagnosis comes to the patient instead. It has already started with some point of care technologies, but not really has taken the kind of shape. And then, how do things change in terms of not just the technology for use, but the technology for development and manufacturing? And that is where I would now come to Dr. Dilip, and we have been all familiar with how AMTZ is working outstandingly well. Dr. Jitendra is today on travel and therefore he could not come. But AIC-AMTZ has transformed medical manufacturing. And how do we ensure that innovation does not remain tapped inside the labs and becomes affordable products across the country, so that manufacturing itself becomes one of the backbones of healthcare? What is your central message from your experience of AMTZ?
Sure, thank you so much, and Jai Hind everyone. It's an honor to be here, and I would like to share what we really experienced and thought. Exactly, sir, what is asking is how we can take this innovation to the last mile. When we thought of MediValley, which is an innovation arm of AMTZ, we thought of this, how these innovations can taken to the last mile. That's where the Medivalley was born. And as we are present in this MedTech Park in Vizag, we thought of making plug-and-play manufacturing units as well as the scientific facilities where these medical devices can be tested. So the main 3 principles were how this can be accessed by the public for affordable medical devices, the cost, and the quality. So we built these manufacturing units so that many manufacturers can come and use these manufacturing units to produce quality products. So when I say quality products, of course we should give confidence to the clinical users. That's why we have created labs which are accredited by NABL and also the American accreditation body called A2LA. So these were not available. When we created manufacturing units, we created scientific labs, and they are operated by the international players, and they have their presence in India, so that they can be, if those medical devices are tested by this notified body, it is globally accepted. So that's how we focus to maintain that quality. When it goes to the market, we meet all the quality standards, international standards. So that, with that aim, we have created that. Now, how we take this to last mile is the important task. So several innovations has come out through this incubation center. Also, there are multinational companies inside the campus. Nearly 185 companies are there in this MedTech Park. And one example I want to mention, how this can be taken, and we have actually taken to the last mile. The MRI which we used to import for 10 crore Indian rupees, we are making for 3 crores in the campus. That is because how we drastically brought down the cost because of this ecosystem. The manufacturing units, we able to build and give to the manufacturers, and the plant and machinery which is required through Government of India support, we able to put it. And these scientific labs, it's a huge investment to create such a scientific labs. So we have made it through the support of Government of India. And because of this ecosystem, the manufacturers able to come and produce in the campus. For example, I was talking about the MRI. The MRI major component is superconducting magnet. In the world, only 3 manufacturers manufacture them and give to the MRI manufacturer as a system. So this one component which was very important to bring to India, and we able to do that, and one manufacturer is doing the manufacturing of superconducting magnet in the campus. Because of that major component, now we have 4 MRI manufacturers in the campus. So that's why they able to give it at a very competitive price. And to test this magnet, we have a scientific labs. So if you see, the magnet itself weigh around 3 tons. So from one manufacturing unit where superconducting magnet is produced, going to a 500 meters scientific, 500 meters distance of this testing lab, it will cost very less. That's where we have able to brought the cost down. And not only that, the various things are applicable. This is just one example. And this MRI now, we able to deliver to a Champawat. If you Google it also, you will find it. The Champawat town in Uttarakhand. The first MRI made in Vizag, made in India, went from Vizag to Champawat and made in India device at 3 crores at this price. And that's where, like this, we have made various platforms where we are taking this innovation to the last mile. For example, we are coming with a cluster model called hub and spoke model, which has been already implemented in Andhra Pradesh, where we tied up with Med United group of hospitals. you know, to take this to the last mile, this innovations what we are doing at Medi Valley or any part of the country, we need platforms to validate and prove that it is clinically accepted. So in villages still the public have the trust on the rural medical practitioner called RMP doctor, right? To convince them, it was a big challenge for us. But yes, we able to explain, like portable ECG, right? Now you have a pocket ECG machine, which is tested in these labs and validated the accuracy with the standard ECG machine. And to give the confidence to that RMP doctor, it was difficult. But we able to showcase the results. That's why this has been accepted, and now it is possible to remotely monitor also. So with this model, we able to take this innovation to the last mile and convince that clinical user, right, for which is called RMP doctor, and connect it to nearby hospitals which are called satellite hospitals, where anything which can be treated at that point, the clinics where this RMP doctor sits, he can be treated, and if not, then it can be referred to a nearby which is around 20 kilometers. And there is a accidental and emergency centers we have, that is around a distance of 50 kilometers, and then a multi-specialty hospital. So this is a cluster model what we have implemented in Amlapuram, is a town in Andhra Pradesh, and Palakollu. Now this we are bringing to Visakhapatnam, and I want to share this experience that I have raised in Chhattisgarh, and I know how medical tourism in Visakhapatnam is, and as this Andhra state is adjacent to Odisha, Chhattisgarh, mostly everyone goes to Visakhapatnam for treatments. This I have seen. Now this is the time, how sir was also mentioning, how we can take those services to those villages. And this can happen with these models. And surely I think what we have implemented will be taken to Visakhapatnam, and then we are planning to for Odisha and then Chhattisgarh. Thank you so much.
Fantastic, and this is where actually import substitution is, of course, one of the greatest achievements, and it is coming through innovation, not a simple copying pasting of what others are doing. And when we trace back to the innovation, we also have to look deep into the foundation technology which is leading the innovation, and the industry partner in that respect, if we think of a consortium where we have public-private partnership, the industry partnership is very critical. And for that, I would like to focus on the experiences of Dr. Shishir Kumar, a very distinguished personality. Everyone knows him who is there in the medical diagnostics arena, that the Huel Life Sciences, starting from the foundation knowledge that he himself, has been a scholar during his research, scholar days, and from there taking up the innovation to the molecular diagnostic, platforms that Huel Life Sciences has been developing over the years, and we have also been very, privileged to connect with them for some of the technologies. So they represent an industry where speed is mattering a lot, because we can talk about many things, but typically in molecular diagnostics, when rapidly the requirement changes, one after the other, the pandemic, epidemic, all these things, they keep on folding and unfolding. What prevents the lab innovation from becoming scalable healthcare products, and how do you think it can be accelerated from your experience in Huel Life Sciences?
Yeah, thanks a lot. I represent Huel Life Sciences. Huel is human welfare. So many think there is connection of Japan and China to it, but it's human welfare. We are stationed in Hyderabad. We have a unit of 120 people who work. We have different verticals. We have chemistry, engineering, and biology. We make right from plastic tube to the device, as well as we make enzymes, we make chemistry behind it. So we have engineers, around 10 to 12, those who work in embedded systems and AI. We have PhDs, those who work in enzymes and others. So, and also we have around 170,000 square foot facility, and we have around 3 acres of land in Medical Devices Park in Hyderabad. So this is my second company. First company, it's been acquired by a company called Biomerio, is a French company. So they acquired us, and then we now grew from 2017 to so far. And to give you a perspective, we were the largest in-house manufacturer of COVID RT-PCR kits in country. We supplied around 5.7 crores of tests across country. And the good part, I think, in-house manufacturing or indigenous manufacturing will actually so far more than 85% are imported. So the current benchmarking is all done by the pricing or quality, or every benchmarking is done by only the imported product. So the current COGS, cost of goods, has not been calculated, but during COVID times, because of in-house manufacturing, we could get down the cost from 1,200 rupees to 16 rupees per test. So that's a significant contribution of in-house manufacturing in the country and back to society. So regarding the scalability, we are working on, actually two of our products. One is the POCT product, and the other one is the routine RT-PCR lyophilized product for TB. They have been validated by ICMR and CTD, and subsequently now in the national program. So we are reaching the last mile connectivity. The problem of scalability is that many of the innovations, they don't look at the perspective of what exactly the innovation is for. There's a huge gap. When that has to be determined, the URS, what we call the user requirement specification, has to be defined at the stage of innovation itself. Then we can basically look at the perspective where it is implemented, how it can reach masses, what could be the last mile connectivity problems in this particular. For example, when we decided to go with TB tests, because all the RT-PCR test kits or equipment which were used in COVID, were to be repurposed, and that has to be reutilized. So we started working with the liquid formulation of TB, and subsequently validated that took us around 4.5 years, because I think basically the validation part, the regulatory validation is little bit fragmented. It's not, and it's expensive. And sustenance for all, for especially those who have to reach the last mile, the sustenance of those industries for that long without funding and with focusing on only specific products becomes a problem. So funding and regulatory, if we can expedite, then probably scaling up and reaching to last mile would be possible. And I request, I think everybody spoke and we had connection with Professor Suman. So we have to have more collaborations with smaller companies. I think mid-size, smaller companies with industry, institutional collaborations has to happen at the MSME level. The problem is, like, many of them house bigger companies in them, and they don't focus on MSMEs. MSMEs where we generate lots of revenue and lots of employment and many of the MSMEs which we are focusing, and they struggle for good guidance from the institutions. And that has to be a mutual understanding between the institution and the industry. So many of the IITs, actually, they should focus on working with MSMEs. So the scalability and the perspective of implementation. For example, currently we have released a product. I just came from Bangkok yesterday. We have released a product with WHO on handheld RT-PCR machine. This is the first of its kind in the world. We are not only doing import substitution, but also are doing innovative products which are reaching masses. That involves engineering, optics, mechanical, and IT overlay of AI. So all this had to be integrated, and until unless we have expertise in multiple fields, we cannot actually scale up any product. Scalability becomes a big challenge until unless we have integrated approach. We cannot have a single unidirectional approach. So that we look at only the biology perspective and engineer looks at only engineering perspective. So we need to have a complete aggregation of all these experts on one platform to look at the scalability of the product.
No, this is spot on because it really requires a consolidated effort of these different parts of the pipeline, starting from innovation to validation to regulatory compliance, and then the commercialization as the technology moves from the lower TRL to the higher TRLs. So if we can develop such an ecosystem, and of course ICMR itself is championing several such ecosystems like the ICMR-COE, which exists in some of the IITs, and also DSIR in their CRTDH program on affordable healthcare. So that is also a good program where MSME integration is, it happens, and IIT Kharagpur has been working on that. I think we should work more intensely where we have this technology creation, manufacturing, the health and biology aspects. And as all these deliberations, they eventually pointed out, and it is very important, that validation aspect. And one thing that always, as just as a common person working in the subject but not being a clinical expert, I see a lot of gap where a validation has a clinical protocol, but it is being actually deployed at a place where such things, such facilities do not exist. And it is absolutely an uncontrolled environment or semi-controlled environment. So technology at the frontier of clinical care when it comes, and the patient first, because patient has to be the most important person. So Dr. Chaudhary, ILBS has consistently remained at the forefront of highly complex clinical care, transplantation, translational medicine, and these are very complex things. Looking ahead, what technologies do you believe will fundamentally redefine not just the primary care, but possibly also tertiary care in some of the areas, like for example, an intelligent integration of AI, genomics, digital twins, robotics, predictive analytics. What do you think? That is where the innovation should focus on.
Yeah, this is rightly pointed out. It is high-end complex cases. I can say first of all is the data what you're talking to, and the best example is the UK Biobank. So I can say now in this house, if you go to a predictive model with a longitudinal follow-up, I can say with 80% accuracy that there is a transition as far as the NCD or metabolic health is concerned. There is a very thin line, that is you are metabolically healthy, you are metabolically unhealthy, you are metabolically diseased. If I have to take your whole genome sequencing, I am taking your demographic profiles, I take your family and background histories, then I take the laboratory parameters. And with the accuracy, if I follow you for 3 to 5 years of data collection, I can tell that this person is likely to have a surgery. You can say, like earthquake. When earthquake comes, before that the dog can know, the bird can smell, but human cannot know. But I can say with EcoBank ideal model, but they have taken the disease cohort. If I am taking a healthy cohort, I am integrating these type of things in the integrated platform, integration of AI. I can tell that how in very, not maybe 100% accuracy, that someone is going to have a disease, diabetes, or having a disease of cardiac problem or a brain stroke with a good accuracy. That I think you need a eco-biobank with a longitudinal follow-up in Indian perspective. So that can be one of the big way where you can think of predictions.
Absolutely. And this is just a specific follow-up because you are a super specialty expert in the liver diseases.
Yeah.
So with this kind of approach of multimodal intervention, do you foresee a future possibility, and if we start working on this right now, when organ failure is predicted years before the symptoms appear, allowing preventive intervention rather than transplantation?
Yeah. So similar way, the digital twin. If I have developed a, because my most of the area is on acute and chronic liver failure. So in that, what you can see that if person comes to us with a single organ, they progress over there to multi-organ failure. If I could identify these persons, the disease phenotype is this, then disease predictability of this, disease severity is this, complications are these are the parameters I can follow. Then there is either two way. I can give preventive therapies in a highly sophisticated much ahead to prevent further progression, or I can think of going for the transplant timely so that there is a no condition that will come up that there is cannot be treatable. I think I have developed a model that is called as the golden window concept. What we have developed, the patient comes to us a liver disease, then we monitor them the first 7 days. A liver failure complex case comes as CLF. In 7 days, 60% show the behavior, how they will go for. So that the concept of taken as a transplant suitability. That means patient is too sick at the beginning, you admitted, you optimize, in 7 days you know the trend, then either they are worsening, so you cannot offer anything, or they are improving, they can be managed medically. And the third category comes where these people, if rightly transplanted, they can survive. So definitely, here it is the clinical model developed, digital twin can come that way to develop the further organ failure can be prevented or can be managed properly. So this again.
No, I mean, this is great, and according to your idea, of course, you are practicing it from the viewpoint of the tertiary hospital, but if this kind of approach has to be adopted in the clinical as well as the technology institutions, what kind of intervention you think, what should we change in our education research type of system to actually implement this?
Okay, so very rightly, so one concept particularly, if you think of liver disease, I say alcohol is a major problem. Is there any way you can make an alcohol sensor? That can be a transdermal patch, wearable device, where you can monitor them. So what you can know, if he is a diseased person, if takes further, he is going on, and you will detect when the alcohol has been taken, organ has damage coming up. If you are anyway able to monitor them before, you can try. Similarly, way for the diabetes, diabetic food, other things are coming up. Now the CGM has come up. So what you do CGM, you put the cloud, you monitor in the digital twin at the system, you give them intervention. So there's a lot way you can, even community level also you can intervene. That way you can think of technology coming even to the remotest part, and you are monitoring at the research center. In fact, I am doing digital twin and I have wear the CGM with me now also. So I am one of the subject of my own experiment. So this
that is simply great, and now, so this is really intelligent, learning from health cases, and all of us who work on medical technologies know that the regulatory aspects, which are traditionally set up with certain things, they are also to evolve dynamically as these digital twins and this dynamic learning, all these things are coming. So focusing on that, Dr. Sujita, so at ICMR you are working a lot on guiding different national policies with regard to regulatory frameworks, and it is very important for the MDMS also. So how do you think such frameworks would evolve to harness this kind of collective intelligence, to come up with perhaps different regulatory benchmarks, but at the same time safeguarding ethics and patient trust?
Thank you for this question. First of all, I would like to just add on to what Dr. Shishir mentioned on can we have some mechanisms to talk to the regulator more often. It might be important for him, of course, as a big industry, he already has those linkages. But particularly for the innovators who work on the bench, say from IITs, say from any individual innovator or startup, there was the innovators had no opportunity to speak to the regulator upfront. There won't be any kind of pre-IND discussions. The innovators at IITs and leading institutes know how to develop engineering technologies, but understanding the regulatory strategy upfront, drafting clinical study protocols, conducting the studies in the real life settings wherein the product has to be positioned. And then even if you receive a manufacturing license, unless you have a market development is of no use. So keeping these 2-3 issues in mind, the 3 important things which an innovator always wants to be able to innovate, they definitely need hand-holding support for regulatory. It's a wish list for them. Can we have a regulatory strategy in my mailbox which I can follow while developing a product, rather than regulator telling later that you didn't do the right thing. Rather than being a inspector, can regulator be your friend? Can ICMR, with the strength in clinical study protocol drafting and clinical validation, has skin in the game? And if an innovator, indigenous innovator comes with a manufacturing license, can we have health technology assessment done for them and recommend those products for public health procurement? Because 60% of the market is government market. So these 3 wish lists of the innovators, ICMR has tried to bridge through 2 leading initiatives called MedTech Mitra initiative, wherein every month we sit with the regulator 3 hours, 6 hours in fact, twice a month we sit with the regulator, talk to the innovators 101, give them regulatory strategy advice upfront. ICMR teams helps them with these innovators in drafting clinical study protocols. I'll give 2-3 examples. We did this for the HemoQR technology, hemoglobinometer developed by the IIT Kharagpur startup company. We did for Mobilab, it's a point of care, the company is developing point of care technologies for liver function test, kidney function test, HbA1c, diabetes. So now ICMR is not just a funder, we are also the facilitators in the innovation ecosystem, particularly in the biomedical innovation system. I would urge people in this room to please take this use of this opportunity, MedTech Mitra and Patent Mitra initiative. With the Patent Mitra initiative, we are helping with the patent filing and technology transfer industry connect, all at the expense of ICMR. So we are not charging anything from any innovator. We are truly believe that these initiatives are important for biomedical innovation, ecosystem development and nation building. So these are 2 important submissions I thought I'll make before I come to this question. For we in today's world, we also find lot of proposals coming to us for preparation of organelles or maybe sometimes organoids. You have some people say digital twins, AI-based products, and these are the 2 kind of things which come to our mind. Of course, we need to create kind of guidelines or policy documents as we move forward. But the onus goes on both sides. The onus on developing quality products, particularly in today's era and moving forward, relies on both the innovator and the regulator or the people in the government system who are trying to monitor that quality products, safe products are used by people at large. From the innovator perspective, particularly in the AI era, when we are still building trust in these technologies, responsive AI product development is very, very responsibly, and making quality products is very important from the innovator perspective. Relying on the appropriate data, quality data, standard data sets to be able to train the tool. Looking at different kind of standards which are even important for almost software perspective is important. So internal validation and development of the tool based on the appropriate data set, the quality data set and the number of data sets, taking all permissions from the, keeping ethics and patients in mind is the responsibility of the innovator. Moving forward, there is a lot of responsibility that also lies on the government in terms of governance, in terms of policy making, appropriate policy making. In the era of AI, like AI is evolving, the policies also needs to be evolved. They cannot be a stagnant kind of a policy which is like a black line which everybody has to follow. It has to be a responsive policy making. Of course, the patient has to be in the center of it. And we believe that once a tool is developed in the lab settings and well tested in the lab settings, they should be validated in real life settings. The clinical validation of AI tools and emerging technologies in the real life settings is of utmost important. Therefore, from ICMR, when we validate these tools, we create 2 types of tools, data sets. One is the training tool and one is the validation data set. Validation data set needs to be tested on the product in real life settings. So these are 2 very important points. Responsible making of the innovative products by the innovator is important. Having very stringent regulations on validation is very important. Clarity on the risk classification of these devices and mandate from the regulator is also very much required. because in our country, if we don't mandate, then we can't get those quality products. So getting those bars high for the AI-based technology is very much important, and close engagement with the doctors and the people who will be using it is also very important to be able to gain their confidence on these products. So bringing these advanced technologies on in ground will need a very collaborative ecosystem of everybody working together, innovator, the regulator, the policy makers, the governing people and the users. So that's how I think a very different kind of innovative policy making, which is very, I would say, agile in nature, at the same time strict on some things, has to be developed. Thank you, sir.
Absolutely, and taking this as a lesson, AI embedded software is now like a medical device. So the definition of medical device itself is extended much beyond. So Dr. Chaudhary, being a doctor, you have been seeing the medical education world, and we have not yet discussed about the medical education. We were discussing more about technology. Just as an imagination, imagine a medical student entering the residency in 2047, say when we aim to achieve our Vikshit Bharat. What kind of clinical skill, which is indispensable today, I mean, without that you do not give a medical degree, do you think will become largely obsolete because of the rapid advancement of technology and being close to the clinical world, which may have transformed by that time?
No, I differ, because first of all thing, technology will never a replacement, it will be only augmentation. That should be clear from the, even if whatever you do, if you are yourself being a big technocrat also, whenever you illness, you go through the models, you develop anything, but you need a human touch. So that can't be replaced. Only thing that your expertise level, accuracy will be much better. So if you think of 2047 for the medical education, definitely AI will be part. In fact, now class 9, my son is also reading AI in the curriculum. So now it is going that way. Medical colleges are now gradually going to add. Even in IL-based, we have started taking faculties for the AI also. We have 2 faculties now on AI. So in that way, medical AI is definitely should be an integral part. And even clinical practice, I think human in the loop for all type of clinical practice will remain always a favor. Only thing that the intensity will change. That they definitely have, because today you can see, previously you see the doctor see the pulse, nadi, and the way they can tell the disease. But I don't know how much accuracy that time, but it is a point of connection, communication, as well as a trust building in addition to the medication and investigations.
Yeah, absolutely spot on. We have very learned audience, present, and because of the limitation in time, that questions I do not know how many we will be able to take at the end. So we are almost towards the end, but not really at the end. But because the audience is quite learned, I would like to go for a poll from the audience. You have definitely your own ideas about what will save more lives over the next 20 years in terms of priority area. So I will mention some of the areas, and if you just think that it is going to be one of the most priority areas, you can just raise your hand so that our panelists know that what thought process. So AI is the first one. So how many of you think that it will be a decisive one? Okay. Then genomics, medical devices, right? Preventive healthcare, behavioral science, and so what we see all are correct and all are important. So there is no single answer, and in fact, whatever may be the answer, AI will be there, definitely connected with the answer. So we just want to get into a bit of, into AI. We do not have a lot of time, and we have coined this as AI beyond ChatGPT. So, all of us use generative AI, be it ChatGPT, Cloud, Gemini, whatever. So every discussion today reaches AI. And it is true that, we jokingly say that in any publication, in any project proposal, if AI is not there as a topic, it is very difficult to get it through. So, people have also learned how to master it without actually getting into anything effective out of it. But then, as Dr. Chaudhuri rightly pointed out, that AI augments, it doesn't replace several things, and definitely it amplifies certain things. So very quickly, I know maybe you are the right person to tell about this. Just a few keywords or points which AI will not be able to replace anywhere in the medical domain.
First of all, I can say is the deep, highly qualified skills for the surgery, like liver transplant. I don't think machine can do the liver transplant. It can help in making the liver volume calculation. It can say how much complications can predict, but it cannot make up the joining. So now surgery has come up robotic that they can help to get the liver, taking half of the liver. We call the robotic donor hepatectomy. In that what happens, if donor is giving liver, the half of the liver can be taken by the surgery. But for the joining, it is the 3 millimeter blood vessels. And you can see it is very difficult to go to anastomosis. That is one. Two, there is a life and death situation. If one anastomosis is wrong, we call as the hepatic artery thrombosis. That is the most common cause of liver failure leading the retransplant. And transplant, again within 24 to go for retransplant. So that is one of the high, suppose you are going for the brain. So deeply core surgical skills or interventions. So what do we do in I have a liver tumor, I go to them, burn them. So you have to go through it's called as transarterial chemoembolism. You have to go through a small vessel to put some drugs come out. So technology here can help how much amount to be delivered, how it will protect the organism. So it can precise more way, but it cannot replace. So only one thing that a highly skilled, more interventional, where life and death is a question, there AI can help to make the process smooth, outcome better, that way it can help.
I think, that is the overall message if we say, and at the end, the question boils down to what should physicians learn from engineers and what should engineers learn from physicians. And, this will always foster cross-disciplinary dialogue. And having said that, one of the end objectives that we said, that the hospital of the future may begin inside the home. And that is one of the major things, which is the preventive healthcare. And prevention is better than care. All of us, have learned this, for a long time. And if healthcare budgets continue to rise globally, are we investing in health or investing just in disease management? That we have to see. And one of the questions I think, first maybe to Dr. Shishir Kumar, what consumer technologies could become healthcare technologies? If you say, you want to bring healthcare to home, currently what we say as Amazonization, what kind of technologies you might be thinking about?
I think smartphone would do everything. So what I would say that smartphone can do a PCR as well. I mean, entirely, and variables. I think one point to add, I think globally the research is shifting to HHG, head, heart and gut. So if you look at more problems are coming, as ma'am said, regarding non-communicable diseases, I think they are more shifting towards your mental health and heart health and gut health. So if you orient towards that, then probably the research, I'm just out of discussion, I'm just adding that point. But I think the smartphones would do everything, and probably going for diagnostics in 2047 to a lab may be very, very, very limited. Probably everything can be monitored from home, and most of the things would be variables, and even the biochemistry and all your cardiac, all parameters can be monitored through gadgets, and essentially I think it would be everything on phone.
Yeah, we are of course looking forward to reaching that sooner. we are now getting into what we say as very, short and quick response, questions because of the time management. And, not that every panelist has to answer in everything, and possibly I will point out depending on the relevance. So, I was just thinking deeply about what is India's opportunity in all this, specific to India, where we have some exclusiveness which will make us leaders and not followers. So I would just like to have one identical question, maybe not for all but a few panelists, that imagine you are given 10,000 crores of Indian rupees and one mission in which you need to drive, no bureaucracy, no constraints. What national healthcare technology mission would you launch? First to Dr. Markan because of obvious reasons of connecting with ICMR.
Responsible and robust AI mission.
Yeah, absolutely. I know. Dr. Dilip?
I think I will make 5 medtech parks to beat China in precision engineering in medtech.
Dr. Shishir, what is your dream project?
I think affordable democratization and decentralization of diagnostics. That's what I feel.
Okay, and maybe Dr. Chaudhary?
Yeah, my will be a, that is called the biobank. It is a longitudinal follow-up digital and medical biobank that at least having a follow-up of 30 years. I need a disease cohort from age of 12 to 45. If I can get genomics, laboratories, imagings, clinical details, family history, backgrounds, then I can help every one of you.
That is great. And towards the end, let us just fast forward to 2047 and think about a child born today will become an adult, at that point of time. What will surprise them most, now even the children who are studying, they are surprised by the way in which all of us have learned in our school. Sometimes they say that we belong to dinosaurs era. My son sometimes tells that. So a child who is going to be practicing some of these, maybe as a physician, as a technologist, what will surprise them the most about how healthcare is practiced today? Maybe any one of you, just maybe Dr. Shishir.
It's all data driven. Everything, I think we have inadequate data as of now to go about. Probably they would be amazed to know that we still don't have data, but everybody is using AI without having the data. That probably can amuse any, because they are learning that AI is learned even in schools now, so they understand the value of data and that is required. But we are still operating AI without data, so I think that's very amusing for any of the newcomers.
Dr. Sujita, any inputs from your side?
So I think they might be thinking that why are we in 30 years earlier, why were we going for preventive health? Why could not we predict the health of a person? Maybe you have a lot of gadgets and lot of high level technology in place, that why were you not able to predict and treat rather than going through preventive healthcare? Maybe it's a dream. I am just thinking that maybe we enter into that era and we'll be blessed in that way. So that's imagination from my side.
Yeah, I mean, it's all like we imagine things, and just at towards the end, some of the points that we could not cover. So I will have maybe just a rapid fire type of question which will have very short answer, and any one of you can answer in each of these. Just take the microphone and answer. So one technology India is overestimating. Anything? I know.
Again, I would say AI without data.
Okay. One technology India is underestimating and it can really create an impact.
Yeah, I think robotic surgery is the one which can bring the revolutionary
We will also
in India.
agree to this. One of the biggest healthcare myths, possibly you can Some myths which are not realities.
कल तो हुआ था सर, we have a dinner yesterday, so we're discussing जातस्य मरण ध्रुवम, सबको तो मरना है, खाना खा लो अच्छा से एंजॉय कर लो, बाद में देखेंगे. That was the thing. So everybody know that once you born you will die, but only thing that how you are going to have disease and death, that has to be defined by you, because you are having a stroke, the pain you have to suffer. But that is still the myth for every one of us. जो होगा देखा जाएगा.
What is the greatest opportunity, those who are working on healthcare technologies? Dr. Shishi.
Yeah, I think huge potential of decentralization and democratization and make it the low cost healthcare support at the rural and out, because still we lack lots of, we claim too much, but we still lack on ground support, healthcare support at the village level or at district level even.
One policy change that is needed, if possible to implement from tomorrow morning.
So like IDEX in healthcare, we have some MEDEX program wherein we give specifications, the government decides the specification of healthcare technology and make it public. And any innovator who is able to make that product, it automatically goes into procurement.
That's great.
Is what,
it happens.
if it happens, I think then innovation in our country can really scale. And market is the real challenge, 70% is the government market. So if we have something like an auction, wish list from the government very clearly specified in technical specification, innovation challenge of the country, specification met, procurement automatically happens.
And one more I want to add, so most important is the quality. I want to say, even now the medication is now come up different ways, which is more potent, less potent. But life should not be taken as potent, because now I can see people are coming that this medicine is poor quality, and we have no robust quality control for anything is coming up. Same is for the diagnostic kit also. So there should be minimum standard has to be must, so that healthcare in any aspect, maybe the diagnostic, maybe treatment has to come, because that is a very difficult area still not attended.
Yeah, please.
One thing very crucial from manufacturer's side, I think probably we should exempt customs completely for all components which we are, because to build up the manufacturing ecosystem, that is very, very must.
Yeah, these are all very important recommendations. And one advice to young innovators, I'm sure, although in the physical auditorium not many are there, but the online thing is there, and many of them will be listening to the recorded version of this also. So one piece of advice to the young innovators, any one of you. Yeah.
I mean, to be focused and see how in a good pace you can make it, because already we are behind so many years if you see the Western countries, right? And this is the right time that the innovators think fast and actually do it and bring to the market.
And possibly the last point, we'll go to Dr. Chaudhary. Say 2047, he will become a very, very senior doctor. So one sentence possibly describing healthcare in 2047.
It should be preventive or promotive rather than treating at the disease stage.
With that sort of very positive note that, preventive healthcare with a lot of technology coming in, but technology not without the clinical wisdom, and combined together with AI, augmenting but not replacing, and the convergence of all expertise, like starting from the technology development, its validation, design, manufacturing, scaling up, policy, regulatory implementation, and it has to be a coordinated framework rather than in isolation. And more we can build up that coordinated framework with such an ecosystem where the clinical and the technology experts come together from industry, from academia, and try to solve the problems which are our national problems but of global impact. And that is how I think we can progress more positively towards Vikshit Bharat 2047. I would like to thank all. I do not know how much time we may have for questions, but I would like to welcome at least a couple of questions before we close.
Thank you so much, very nice discussion. This is Dr. Arun Mohanty from CEO of 3D Genomics in USA. I live in Boston. I just visiting here. We're setting up a molecular diagnostic lab in Bhubaneswar in Forest Park here. So I am having some problem getting a lot of equipment. Dr. Kumar mentioned that we claim too much, but I am trying to get some instrument, but most of the instruments we're trying to import from USA, like for example the sequencing. My main focus is setting up a molecular diagnostic lab, world-class laboratory in India and here, because as you mentioned the preventive care, so we are trying to set up a disease when the baby is born, even before like gestation, within 3 months of pregnancy. Like a lot of monogenic diseases, we still don't know how to predict those, right? So we are trying to set up those kind of work here, but still we are depending on the getting sequencer from Illumina from USA. So how to stop that? How do we are still not able to get those equipment here. I'm struggling for those. So I think Dr. Kumar can address, to build those such instruments, we need to get some support. Thank you so much.
Yeah, I think, again, emphasis is on getting expertise together. It's not only the engineers. We need multi-directional approach to design, because simple RT-PCR, for example, nobody have made in country. I was surprised to see a few years ago, normal PCR machine was not made in India. We still used to import from Biorad or Thermo, or, still we import. And we made a small pocket PCR or very small PCR where that can be carried to schools and colleges. We demonstrate, but we don't teach them. The hands-on experiences are not there, even in good schools, even in pretty good schools. So now we started building that. I think in the down the line, now the technology will advance quite faster than what we have seen earlier. I'm sure next-gen sequencing would come very soon. We are also discussing for a tech transfer from Oxford Nanopore and multiple companies. So definitely this on cards. Maybe down the line 2 years we'll make one next gen for you. So that's for sure. But that would take little bit time, because simple optics, putting all together with optics and the thermal engineering and all that stuff itself took us a lot of time for us. So now we have gone through that. So one cycle of dynamics of making a equipment is all done. So we have launched recently, as I said to you, for WHO PQ. We are going for WHO PQ as well. So things are improving. I'm sure within next 3 to 5 years, many would come from India. So I am very, very optimistic about it.
Absolutely. And maybe one last comment or, yeah.
Good morning, all of you. Sir, development is in health research is increasing, diseases are also increasing, and almost all unknown diseases are also coming. So how we make in India this healthcare completely free for all citizens, affordable, and all of you know that the corporate hospital, if you land in a corporate hospital, how the treatments they are doing based on your budget, based on your insurance card. And air is polluting, water is polluting, food is polluting, and by default, before 40-50 years, by default we are taking the organic food. The milk we were eating is pure, but now the paneer is mostly adulterated, milk is mostly adulterated. So in this sense, how we can come back to what we were doing before 40-50 years, and my question is how we can make this healthcare completely free for all citizens of India.
Maybe a very short answer, because we are running out of time and we will take 1 or 2 more questions. So maybe just one short answer.
Sir, that is a policy issue, and you can say it is more of political issue. Health education should be a right that to be done. That is not here we can say, but you can see most of the developed countries they focus more on these two aspects, which is last. Not for the policy, for us also. मैंने अभी बताया ना कि बीमार होने के बाद डॉक्टर के पास जाना है, बीमार नहीं होने के लिए कोई जाना नहीं चाहता. So if you think of preventing, promote, because policy will take years to develop, but what I can do, we can do today. So I can ask, please raise hand, how many people in this house are doing 10,000 steps per day? Can you raise anyone? 10,000 steps daily? No. So this is how I need that. I don't know policy because India is such a, and I think I have been in a meeting there, they told that any country having population more than 20 crores, it's difficult to do a public system of healthcare because there is a lot of limitation. You can see wherever the country across the world, the population size makes it difficult for this access to be free. So in that way, let the thing go to policy. That is difficult. दूसरे घर में क्या होना है, but अपने घर में हम क्या कर सकते हैं? So I think that you can take a healthy life tips, healthy food habits. You can make it your kitchen garden own. Rooftop में garden बना के कुछ बनाओ. So
No,
this
I have one just point to add here. Just like we have point of care diagnostics for diseases, we should have enhanced point of care diagnostics for food quality, which currently is there in research form. So at least milk or this paneer and these common things, there are simple diagnostic tests. They should come in and at least that screening can be done. Yeah, next.
Today, actually, we are moving from health to wellness. If you take the corporates, for example, I come from Tata Steel. So here we have a concept of, the balance between the spiritual, the physical, and the mental. Trying to balance these three aspects to go for overall wellness as opposed to just health. And if you see our ancient medical systems, like say Ayurveda, typically it talks about this, this balance. The balance between the electrochemical, what is that, your blood, your physiological, and your mental condition. And the spiritual, the ultimate is the spiritual. So how many lessons are we taking from these ancient systems of medicine in order to, look at the present day issues and the problems?
sorry, that is my passion. Sir, to make more idea and engage, all these preventive are in our genes by birth, you can say. People sleep around 7 p.m., woke up at 3 a.m., Brahma Muhurta. No one is following now. Late night sleep, late night awakening. Second, the food, the common rule is that how many number of teas you chew that time, your food will be healthy, you will be body getting asymptomatic. But we are in a process of having the processed foods packed for preserved foods. That is going on. Third is, एक कहावत है कि आप जितना खा रहे हो इसको निकाल दोगे तो बीमारी नहीं होगा. That means if what I am consuming, what is my bank balance, if I am using the bank balance is steady, that means money. Same way also our habits. The more bad habits you are inculcating, late night sleep, junk foods, physical inactivities, that is transformed to your disease bank, and that we are getting the disease way. So these all, as now the concept of intermittent fasting, we know everyone is doing. हमारा घर में रोज fasting होता था, कभी एकादशी, कभी संक्रांति. So this is the intermittent fasting was much before. Then if you sleep at like Jainism, they don't take meal after the sunset. It becomes naturally a intermittent fasting. So a lot of things are there. Like yoga. Now we are taking yoga to the health. It is known much before. So only that we can, even I have on paper on FMT, fecal, we are doing the stool transplant. पहले ज़माने में था, even Moraj is taking urine. So that we have now coming back to that area that we are taking stool, we are reformulating to get the microbiota, we are transferring to them. So it is a poor, in India we have poor problem in that technology discovery. We don't want कि पुराने ज़माने क्या था to repurpose. Then poor in tech transfer. था कि मेरे गांव में एक पंडित थे, वो एक दवाई डाल देते थे, मेरे घाव ठीक होता था. But the person died, the science stopped there because there is no technology transfer. And we are very much insecure that our science should go to the next generation. So it is our cultural problem that we are suffering this way. This allopathy system comes to India only 500 years. But this traditional Ayurveda is 1,000, 10,000 years ago. But nothing has progressed now. Because now what is the problem happening that because what happens, you talk to many of the peoples, that मैंने ऐसे ट्रीट किया था, but मैंने ऐसे ट्रीट किया था, is level of evidence is D, expert opinion. You go for any treatments, it is always the randomized control trial followed by meta-analysis. But you go to our Indian system of medicine, there will get very limited RCT, you will get rare of meta-analysis. That is why we are weaker in our part.
I know, absolutely, and this is a long discussion that can one last question. I know that's it. Yeah, sure. So if you just take it.
Good morning to the esteemed panel. My question to Dr. Dilip is, for medtech startups, what should be the approach while selecting an evaluation laboratory to do the test required to get all the CDSCO test license? Can AIMTZ be a primary evaluation partner?
Yeah, yes, we are doing that already. Actually, Medtech Mitra, through Medtech Mitra also the innovators approach us where we support the regulatory part. We have a dedicated team which works on it because the classification is A, B, C, D, right? A, B is for the state and C, D goes to the central, which is the most complex part where we support them, we follow up with them to get it done. So that can be easily done.
Okay, sir, thank you. Can I ask another one?
Yeah, 1 second. That, even for helping the startup innovators as Government of India, we know that test license stage is the critical step, which is important even to go ahead for clinical studies or any kind of testing to get regulatory compliance. So in ICMR headquarters, Medtech Mitra team, we have dedicated team sitting in the ICMR headquarters, helping innovators file test license application. We have helped filed in last 2 years, 72 test license applications our team has facilitated. At no cost to the innovator because we are government. So you can write to Medtech Mitra and we will facilitate guide you also on how to prepare the documents, help you with the filing as well.
Okay, ma'am, thank you.
Test license.
Okay,
I think we have to stop somewhere because next session, we can always have the discussion extended, but it was so engaging that I also did not want to, close it like that. So I would thank the entire panel and the audience to make it so engaging and so lively. And as a recommendation on the way forward, because this is being video recorded, let us make a good transcript out of this entire conversation, make a note, and we will submit the note to INAE for further course of action, maybe communicating to the ministry, different ministries or parent bodies, bring them together to actually come to some workable recommendation, because otherwise we have lots of panel discussions, it leads to just, good discussion but no outcome. Let us hope that it has some outcome. With this positive note, let us end this session. Thank you very much.
Thank you, Professor Suman Chakraborty and our esteemed panelists for a truly enlightening and engaging discussion. May I request Professor Indraneel Manna, former President INAE and Vice Chancellor BIT MESRA, to kindly come on the stage and felicitate esteemed panelist and distinguished moderator.
Let me take a minute here. I think all of us would definitely agree. Professor Suman Chakraborty is a very passionate researcher. We all know for quite some time. Of late, he is in his new avatar, is the director of the largest and the most complex IIT of the country, and the first in the row, IIT Kharagpur. And he arrived yesterday from Bangalore, felicitating his former supervisor. And today, Sunday, he is spending with us until middle of the day. I'm sure all of you would agree that we have one of the most enjoyable and a very engaging panel discussion. Suman rightly pointed out that in many cases it becomes more of a perfunctory exercise, but he made it so lively and so engaging. All of us truly enjoyed and got enlightened to a large extent. And he actually took the word from my mouth that we need implementable recommendation. INAE will definitely take it forward and make it, take it to the logical conclusion. So would like to, on behalf of all of you, would like to accord a very deep gratitude and appreciation to Professor Suman Chakraborty and all the very esteemed panelists. All of you really did wonderful job. Thank you very, very much.
Thank you. Ladies and gentlemen, it's now time for the distinguished address of today's morning. Meanwhile, we are having the panel sessions, which comprises of paper presentations, poster presentations, and startup display at their respective venues as indicated in the program schedule. It is my privilege and honor to introduce our distinguished speaker, Professor A.B. Pandit, Vice Chancellor, Institute of Chemical Technology, ICT, Mumbai. Professor Pandit is an eminent academician, renowned researcher, and an inspiring leader whose pioneering contributions to chemical engineering, process and engineering education have earned him national and international recognition. We are delighted to have him with us today and look forward for his insightful address. May I now request Professor A.B. Pandit, sir, to kindly deliver his distinguished address. Ladies and gentlemen, please join me in extending a very warm welcome to Professor Pandit with a round of applause.
Don't know whether it is good morning or good afternoon. It is just the stroke of 12. So let me wish you all good afternoon. And I must first apologize that I don't have any PPT, either to interest you or to bore you, whichever way you want to look at it. But the topic which I have chosen today to talk, being a chemical engineer by profession, the topic which I have chosen for today's discussion is the evolving and ever-expanding landscape of chemical engineering. Of course, being a chemical engineer, I will promote my trade, and I'll show that how chemical engineering has played a role in every part of engineering. So the talk is going to be consisting of two parts. Part one is what is actually happening in the area of chemical engineering and what is possible or happening and requires an immediate scaling up. Meaning the technologies are available, the proof of concepts are available, but it has not been implemented at a scale at which it is possible and it is needed to make a real change. And the second part of the talk is actually peeking into the future, which is predicted with the help of AI. If we want to integrate AI and ask AI, what is the future of chemical engineering? AI has come out with multiple answers, and I would like to discuss those answers in due course of time in the second part of my talk. So you all know that chemical engineering started with an intention of making platform chemicals such as alkalis, chlorine. Hydrocarbons came much later. We have got now equipments and industries which are of a significantly large size. Our specialty chemical business is the most innovative business as far as chemical industry is concerned. And chemical industry as such contributes about 7 to 8% of the national GDP, that is of our country. And it has seen multiple disruptions. And I'm going to list out one by one and briefly talk about each of these disruptions with some concrete examples. The first disruption occurred during the digital area. Forget the AI part, AI came much later. The advent of computer age brought the marked change in the students' priorities, because being an educator, I am going to look at how the entire course changed as a result of digitization and how that affected, in turn, the industry later on. The number of students who started shifting from core engineering courses, including chemical engineering, to computer science, now of course you realize that unless you have some manufacturing base, computers is not going to be doing things for us, making things for us. So unless you have basic engineering at place, computers will not be used. And this realization has started, and slowly now again the shift is happening. Not as fast as you would like, mainly because of the salary structure which still exists, but it will take a long time. The field of chemical engineering traditionally, which was rooted in foundational principles of thermodynamics, transport phenomena, and reaction kinetics, is undergoing a profound transformation driven by the integration of artificial intelligence. This is not just computational tool, but it has become a partner in enabling unprecedented efficiencies and the innovation. AI-driven analytics are revolutionizing process optimization, allowing for real-time adjustments to maximize yields and conserve resources. This predictive capability also extends to equipment maintenance, preventing costly failures, ensuring continuous production into material science. AI accelerates the discovery of new compounds by simulating properties and enabling inverse design, a process that previously took years of trial and error. Beyond efficiency, AI enhances safety through dynamic risk assessment and improves sustainability by optimizing processes to reduce emissions, waste, guiding the industry towards greener practices. We just had an excellent panel discussion moderated by Professor Suman Chakrabarty, and the preventive maintenance in equipment is equivalent to preventive diseases or preventive healthcare. So the importance of preventive healthcare can be derived from the preventive maintenance which is currently used and applied in industry. Despite its immense promise, the increasing reliance on AI introduces critical ethical and operational considerations. Now, this is extremely important, and this problem was also talked about. And I think Shishir Chaudhary talked about jumping to conclusions without having a reliable data. Now, that is an extremely important consideration. Algorithmic bias, for instance, could lead to unsafe or suboptimal operations and recommendations if the training data itself is flawed or unrepresentative. There are also significant challenges related to data privacy and intellectual property of AI-generated designs. A crucial aspect is the need of explainable AI, XAI, to ensure that engineers can understand the logic behind the development and follow that and validate the logic for its correlations and mathematical rigor and integrity. There are many modern innovations which have happened in the core chemical engineering. One is, of course, the miniaturization process. In the early 60s or the early 20th century, there was a tendency to make bigger and larger plants. Slowly that has now shifted to make it smaller and miniature plants without compromising on quality and productivity. These microflow reactors make hazardous processes much safer and can substantially improve reaction rates and yields by improving the space-time uniformity. In separation technology, which constitutes a major part of investment in any chemical plant, including pharmaceutical sector, significant advances have been made. Even the conventional distillation, which is a workhorse of chemical industry, is now available in its modified forms as reactive distillations with divided wall columns. In the area of extraction, which is again a process which is followed either in metallurgy or in chemical industry, novel methods such as supercritical extraction are commercially employed for high-value products like fragrances and flavors. Separations based on adsorption have been seen a dramatic improvement with the advent of new adsorbents like zeolites, molecular sieves, carbons, MOFs, and COFs. During the COVID-19 pandemic, this technology was found to be critical, and one could see the impact on-site enriched oxygen generation through pressure or vacuum swing adsorption. Membrane-based separations here also have made a major impact, notably in reverse osmosis for converting sea and brackish water into potable water. Extraction with reaction has allowed valorization of lean ores, starting with uranium, the strategic and a critical material requirement. Chromatographic separations have now become common with new chiral columns, which allow us at commercial level resolution of racimates, and simulated moving bed columns has made an impact in terms of commercializing these operations. A major advance for solvent-based nanofiltration, even for polar solvents, which allow molecular level above a particular molecular weight of 250 kilodalton to be retained, making the separation facile, robust, and with much lower energy requirements. A particularly novel advance in the case of membrane-based separation is charged membranes. Now, these charged membranes has allowed you to extract lithium from ores, which is essentially a monovalent cation can be extracted, ignoring the divalent cations as impurities such as magnesium. Crystallization remains a vital area, especially for active pharmaceutical ingredients, APIs, where product quality in terms of particle size, bulk density, and polymorphs is critical, and we have developed a significant separation tools and techniques to address these particular issues. A primary example of hybridization. Chemical engineering is always considered as a jack of all trades and a master of one. Many a times, it is not even master of one, it is master of none, but they know everything about everything else. A primary example of this hybridization, where chemical engineers have borrowed different concepts from different branches of engineering, is the deep integration with life sciences. This synergy has given rise to biochemical engineering and bioprocess design, where engineers apply their expertise in kinetics, thermodynamics, fluid mechanics. At a cellular level, this hybrid field is now essential for large-scale production of biopharmaceuticals, which are also termed as biosimilars, such as monoclonal antibodies and insulin. Chemical engineers are critical in designing and optimizing bioreactors, the vessels where living organisms are cultivated, and developing a downstream processing methods to purify the product, actually meeting the standards as per GMP. Biosimilars, especially in India, is taking and growing by leaps and bounds. The intersection of chemical engineering and biotechnology represents a crucial and dynamic field and bridges scientific discovery with practical applications. While biotechnology focuses on using living organisms and their components to develop product, it is the discipline of chemical engineering that provides the tools and principles to transform these biological breakthroughs from laboratory curiosity to scalable, safe, and commercially viable reality. Without the expertise of chemical engineers, the vast potential of biotechnology would remain largely untapped. In conclusion, chemical engineers is the essential link that translate biological innovations into industrial production. By providing the expertise in process design, scale-up, and purification, chemical engineers enable the mass production of biopharmaceuticals, biofuels, and countless other biotechnological products. They are the problem solvers who ensure that the groundbreaking breakthroughs research can have tangible and positive impact on society. Materials is another field where AI and chemical engineers have contributed. Now, what we sometimes call it as a moonshot material, the material which is not known, but following the principles of chemistry and physics, it is possible to have such a material. It's not impossible. What was thought as an impossible has become now a possibility. Smart polymers, responding polymers, self-healing polymers, these are all the gifts which chemical engineers have developed along with the physicists and chemists to the world, and that is now slowly being accepted and being utilized in a variety of applications. This cross-disciplinary approach is vital to the developing of a building block for future technology. This hybridization of core principles is essential for addressing the world's most pressing issues, from global health to sustainable energy. Water, energy, and health. These are the three major challenges which are faced by our country. And chemical engineers, along with the other engineers, will definitely contribute, whether it is civil engineer, development of materials for developing faster and quicker setting and improving strength of the concrete. Similarly, in the case of development of materials which are in the area of polymers, this business of additives, which is essentially application-oriented, has been and has offered golden opportunities and significant availabilities for exploratory work by budding chemical engineers, including those who are involved in the startups. The list which I have made up till now and the ones which I talked to you up till now essentially are the technologies which are currently available, being used, but have not been used to its fullest potential. So there have been a limited number of industries, a limited number of governmental organizations where they have been able to use it and adopted this particular technology, but much more needs to be done. This is available for us to implement it. Now, if we stop here and look into the future, when I say future, is what future? I would say 2047 is not a future. We should be looking maybe 100 years down the line, 150 years down the line. And if we ask AI, what do you see as the future of engineering? AI will come up with an answer that there is no branch of engineering. And I must compliment IIT Jammu, where they have started a BTech course in unified engineering, where multiple engineering disciplines come together and come up with a solution possibilities or solution providers, incorporating all aspects of different engineering branches. And if you ask AI, then AI provides the following answers. And I'm going to give these one by one, and it will include what AI predicts, what is the game-changing aspect of this possibility, and what is likely to be the impact on the society of this activity. First is quantum chemical engineering. What it could be? a discipline where chemical processes are not just optimized using classical thermodynamics and kinetics, but are designed and controlled at a quantum level. What is the game-changing aspect? Harnessing quantum computing, quantum chemistry to simulate, predict, and even steer reactions in real time with atom-by-atom precision. The impact? Fast development of new drugs, materials, the ones which I told you about, the moonshot materials, and catalysts designed in silico with zero trial and error, leading to a near elimination of lab-scale experiments. Second prediction by AI is programmable matter engineering. What it could be? Instead of producing chemicals or polymers, chemical engineers would design matter that can change its properties dynamically, self-healing, shape-shifting, tunable conductivity or permeability. This is what I call as moonshot materials. What is the game-changing aspect of it? Using molecular switches, supramolecular chemistry, and adaptive polymers make materials that reconfigure themselves on demand. Impact of such a development: buildings that adapt their porosity for cooling, clothes that change thermal insulation instantly, or medical implants that remodel themselves inside the body after implant. These possibilities do exist. Third, is there real possibility of carbon negative Earth system engineering? And that is what AI does predict. It predicts beyond carbon capture, engineers design planetary scale chemical processes that actively restore Earth's balance, scrubbing greenhouse gases, regenerating soils, even fixing ocean acidification. Game-changing aspect: a fusion of chemical, biological, and geoengineering to run synthetic metabolisms for the planet. Impact: human-driven climate repair industry with chemical engineers as custodians of planetary health. Fourth, synthetic life processing engineering. I think we had an excellent panel discussion about it, and this is what is the extension of the same. What it could be: chemical engineers converging with synthetic biology, which is also termed as evolutionary biology, to create engineered organisms or protocells that act as factories, sensors, or healers. What's the game-changing aspect? Not just fermentation or bioreactors, but the design of entirely new forms of life to carry out chemical transformations. Biosimilars, to a certain extent, is actually following this. What is the impact? Living materials for construction, bacteria that clean up plastics, heavy metals, they clean up plastics and heavy metals anonymously, or even artificial cells that act as nanomedicine inside the humans. I continue with this. The next the AI predicts is quite futuristic, but indeed, since we want to predict and want to explore, why not go and go the full way? Astrochemical engineering. What is it? Engineering chemical systems that functions outside Earth, on Mars, the moons, on asteroids, or in deep space. Game-changing aspect: resource extraction from extraterrestrial bodies, chemical synthesis under microgravity and radiation, closed-loop life support chemistries. Impact: establishing sustainable off-Earth colonies and enabling space industries with chemical engineers as the terraformers of the other world. Next, conscious materials and neurochemical engineering. What it could be: design of materials and devices that interact directly with human nervous system at the molecular level. What is the game-changing aspect of such a discovery? Neural chemical interfaces that allow matter to sense and respond to emotions, thoughts, or intentions. That is AI with empathy. This is one of the major issues which is currently faced by our society. Seventh, energy alchemy engineering, which I would like to generally call this as resource engineering. What it could be? A future branch dedicated to direct matter energy transformations far beyond combustion or batteries, moving from energy carriers such as fuels, hydrogen, batteries to direct conversion methods. Now, in fact, you would find that a couple of weeks ago, German scientists predicted that direct sun energy to hydrogen, right? Basically, an integrated system available with efficiencies of solar energy, incident energy conversion of 31.1%, which is unheard of, at least at the lab scale that they have been able to achieve. What is the impact of such? Radical energy abundance, decentralization of power grids, and solutions to the world's energy crisis. So in conclusion, I would like to make a statement. I'll stop and it will be open for any questions which you may have. Is chemical engineers in their future avatars might not just be about manufacturing chemicals, but about engineering life, matter, and even planetary systems themselves. The field could move from factories to living organisms, intelligent materials beyond cosmic frontiers. Thank you very much for allowing me to make this futuristic presentation, and I apologize again for not having the PPT. I'll convert this into PPT and possibly send it across to INAE for wider circulation in due course of time. If anybody is more interested in these particular details, these is available through an article which has come in Horizons publications which have come out with INSA, where Professor Sharma and myself have written a detailed article, and today's presentation is mostly dependent on what is existing and what is written in that article. Thank you very much. Sure.
Whether it is electric or hydrogen or mix of ethanol and methanol, how do you see that, sir?
The movement of internal combustion to EV vehicles is essentially just shifting the location of pollution. That's it, nothing else. We are still not realizing the fact that as the EV consumption increases and EV popularity comes in, what is going to happen to the huge amount of unused batteries, used batteries which we are going to have? And that's why I call resource engineering is an important thing. It is high time that we start looking at the waste as a next set of resource and come up with technologies which allows us to utilize that waste as a resource for a variety of materials as well as energy requirements are concerned. As far as the various articles which appear, 20% ethanol, 100% ethanol, etc., 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 again, we are drawing conclusion without having any reliable and substantial data to support either of these things. So I don't want to jump to conclusion, say this is good or this is bad. There have been countries which have been running on 100% ethanol for so long. Right? They have adjusted, they have learned the metallurgical improvements which are required in internal combustion engine. There are going to be also issues when somebody complains whether a real quality ethanol has been made available, has been used, or just to increase the volume because it is delivered in terms of volume. You add something, ethanol, water, just separate it out, and then you have all the problems which are associated with the internal combustion engine. What really needs to be done as far as any engineering application is concerned are two things. One, you carry out a life cycle analysis of any activity. Any anthropological activity which you are introducing as a new activity, as a replacement of an old activity, it is necessary for us to carry out a life cycle analysis, cradle to grave approach, and really find out what is its long-term impact on the environment. And the second part which we need to do is do an exergy analysis, not the energy analysis, exergy analysis, which takes into account the quality of energy rather than only the quantity of energy. I'll give you a simple example of that. In coal mining, about 1 to 2% of the actual calorific value of the coal is utilized in terms of energy required for the extraction of the coal from the mines. But most of the time, this energy is in the form of electrical energy. It's not a thermal energy. The conversion of thermal energy to electrical energy is considered with, at the most, 40% efficiency. That means we say 1% of the calorific value divided by 0.4, about 4% of the total calorific value of the coal in terms of exergy value is being utilized, which is not very different if you compare the energy which is utilized when you are extracting crude oil from oil wells, or a similar analysis. So you need to do analysis which is based on exergy rather than energy, because energy, as we say, cannot be created, cannot be destroyed, but that is not the case with exergy. Exergy, once destroyed, you cannot generate it. You cannot create it again. So the limiting quantity for the sustainability is the exergy analysis, and exergy analysis, along with the energy balance, needs to be taught as an integral course for, in fact, chemical engineering or anyone who handles energy as one of the topics in the engineering course.
So I just have one question, that is, I think the chemical engineering is going through a rapid change and very changes which has got huge implications. Now, how is the education, chemical engineering education is adapting to it? It appears in most of the classes it has remained very classical. So what is your opinion about it?
Good question, and that's why I said, I think Gargi was involved in the kind of analysis which we did a few years ago, where we asked ourselves is how sustainable the chemical engineering course is as it is taught today. And extremely interesting conclusions came out of it. Similar to CFD-driven designs are now becoming an integral part of the chemical engineering course. AI-driven designs with the reliability of data is also going to be an integral part of the course. The national education policy has allowed us to do that. In fact, giving a specific example related to ICT, what we have now in ICT, along with the conventional BChem engineering and BTech engineering as degrees, main degrees, they are also allowed to have MDM, which we call it as multidisciplinary minor degrees, in which AI, management, polymer processing, food engineering, this you can do along with chemical engineering. So basically, the principles being extended to variety of engineering, because you need to make yourself useful not in a conventional chemical industry, but industries which rely on the chemical engineering principles in a different domain. So these changes are happening, but you all know how lethargic the general education system is. You ask a faculty to teach a new subject, no, I've got notes of this, and they will keep on using those 10-year-old notes, 5-year-old notes, and there is a huge resistance. In fact, NEP also, if you really want to implement it in a spirit, faculty requires significant amount of additional efforts. Things will change, but of course, it's like ICT, it's like India. You probably have read the news that China scrapped 12,000 conventional degrees and have introduced new degrees. Suddenly, scrapping out old conventional 12,000 degrees. We can't do something as drastic as China, because being a democratic country, we cannot undertake that. But things will change, things are changing. Yes, of course. Thank you.
Sir, here.
Yeah. Yeah, sorry.
Sir, I just wish to know what are your opinions for hydrogen and green hydrogen versus electrical vehicles? Because it has been, as you have rightly pointed out, that this is just a shifting of the poles for pollution, but they are still polluting. So in that case, how would you see the role of hydrogen and green hydrogen in that case?
See, green hydrogen is one part of it, but hydrogen definitely is going to be a future fuel. As far as if you are interested in net zero, we'll have to look into hydrogen being used in all the carbon intensive industries, whether it's steel industry, automobile industry, or any other industry which is carbon intensive. Now, generation of hydrogen, again, is dependent on energy. We again need to do a life cycle analysis. You have a complete hydrogen spectrum available, green, blue, purple, etc., etc., etc. Now, depending upon the availability of resource and a location, you will find that different color hydrogen is optimum for that particular location. We still have a huge problem or huge bottleneck in terms of storage and transportation of hydrogen. So we'll have to have a distributed system where the hydrogen is generated and used. Indian government has, the Department of Science and Technology has come out with high-vac Hydrogen Valley Innovation Cluster at 4 different locations throughout the country, handling this entire generation, storage, supply and usage. And I think in next 4 to 5 years' time, things will change and hydrogen definitely will become a future fuel as well as a reducing agent in majority of the chemical industries as well as metallurgical industries. Thank you. Done. Thank you very much indeed for all your kind attention. And as I said, I'll circulate the final PPT to Colonel Rai and then hope he will be able to circulate it to our fellow members. Thank you.
Thank you very much, sir, for your insightful and inspiring address. Your thought-provoking perspectives and wealth of experience have provided us with valuable insights. May I request Professor Shantanu Chaudhary, Vice President INAE, to please come on the stage and felicitate, sir. May we have a huge round of applause, please? Thank you. Ladies and gentlemen, We now move to a special segment of the program, the felicitation of the newly elected individual members of Indian National Academy of Engineering. Today we have the privilege of felicitating the newly elected individual members of the Academy, whose achievements exemplify excellence, innovation, and dedication to engineering profession. May I request the newly elected individual members to kindly come forward as their names are announced to receive the felicitation. Okay. Okay, so this session, actually the individual members are presenting outside, so we'll wait for 10 minutes, then we'll start this session. Okay, so we can disperse for a short tea break. We can use this exit on the left side and one at the back, and we can have a short tea break there. Thank you. And there is a short announcement regarding INAE social media also.
This is for the current, like the newly elected members. I request all of you to please kindly follow our LinkedIn page, because we're going to tag you on that page. So if you can please go and type on LinkedIn Indian National Academy of Engineering and follow that page so that I can have your direct account and it's easier for me to tag. Indian National Academy of Engineering. Just write it and you'll find it. We've almost 15K followers, so that is the page. Yeah.
After felicitation. After felicitation. ये वाला ceremony के बाद.
15 मिनट का 10 मिनट का ब्रेक है आप आ जाओ.
10 मिनट.
2 मिनट. अच्छा 2 मिनट तो अल्टीमेट है. आपको मैंने अपर टाइम बताया.
AC बहुत वो है.
एक काम करें. In the meantime, let me announce the names and kindly request you to be seated on the right side of the. ठीक है ये अभी 5 मिनट बाद अनाउंस कर देगा. I know, I saw that. अभी तो मैं आया था. क्या हुआ?
So if we have individual members here in the auditorium, may I request you to please be seated in the front rows? So do we have individual members here? So please come on the right side and sit on the front row.
Please occupy first, second row, so that it's easier for you to come. We'll announce the names. Names announced.
So Professor Sridhar, do we have him here? Right.
The way she's announcing, then start sitting, so it's easier for them to come in time.
Yes, so you can sit on the first seat. Then Professor Roy, Chemical Engineering. Yes, please on the second
Sorry
seat.
for the inconvenience. Sit down, that it's easier for you to get up and come.
Yeah. Then we have Dr. Prasada Raju. Do we have Dr. Prasada Raju with us?
The one vacancy is probably gone behind.
Okay. Then we have Dr. Pushpdant Jain.
Dr. Jain has come? Yes. Yeah, please come ahead. Your train was late, no? Come, please.
Dr. Saha, please come forward. Professor Gargidas.
She's there, ma'am is there.
Yeah.
Ma'am, please occupy the sixth row, sixth seat.
Then Dr. Paramita Das.
Dr. Paramita Das is here. She's here, seven seat for her.
She's there outside? Okay, so we'll keep the seat vacant for her. Then Dr. Shubham Banerjee. Yes, please.
Yeah, please occupy in 8th seat.
Dr. Neerja. Dr. Neerja, do we have her?
Dr. Nija is here?
No. Dr. Neerja, the question mark here.
I saw her. Is Dr. Nija, anybody seen Dr. Nija? Okay, leave one seat vacant. Move to next one.
Dr. Ashish? Yeah, please.
9th seat.
Yes. Professor Prabhakar Rao. Please have a seat. Dr. Venkatesh? Dr. Venkatesh? Yes, please. Dr. Solanki?
No, he's not coming.
Okay. Dr. Biswas? Dr. Arindam Biswas?
Dr. Bishwas is here?
Oh.
Okay, he's there.
Dr. Akshay Kumar Verma?
He's from SOA only. Leave one seat vacant here.
Okay. Mr. Sudeep Narayan Banerjee? Please come. Yeah.
Please come.
Professor Vasu, NIT Warangal?
Yeah,
please come
ahead.
forward. Dr. Deb? Yeah.
You can occupy the second row, first seat. Yeah.
Dr. Manoj Kumar?
Dr. Manoj Kumar is here? Okay, leave a seat vacant. He's confirmed he'll come.
Dr. Bala Muralidhan?
Yeah,
please.
Third one.
Dr. Abhijit?
Dr. Abhijit is there? Yeah, please. Fourth row, 4 seats.
Dr. Sharma, Shreyan Sharma? Please come.
5th seat, please.
Professor S. Indu?
Yeah, ma'am. 6th seat, ma'am.
Engineer Raman, E.R. Raman, please, next. Mr. Saxena, Krish Saxena.
Mr. Krish Saxena, please.
Please.
8th seat.
So we do not have Dr. Neerja Batla.
Dr. Nija is here. Anyone seen? Any idea?
Dr. Neerja.
Okay, she will answer your names. I'll request you can come one by one. You to send your certificate and a memento. We have a photograph also individually.
So what's her name?
You will have a group photograph.
Yes, yes, ma'am, we have your name. We have your name. Please sit. No, that's okay. You please sit, ma'am. In the front row, you sit, please.
No issues, even one sit left and right, there's no problem.
Neerja ma'am is not here. Dr. Neerja. So, do we have Dr. Neerja here or outside somewhere if you know Dr. Neerja?
Any of the members, she missed out the names who has joined, who was a recent member, anyone? Who inducted today? Aapka naam hai? Your was the, I think your seat is here on the 3rd. Please come ahead.
Dr. Prasada Raju, right? That's what we have.
सर आगे क्या नहीं
है but he's not here अभी
मैं बुला
so let us wait
आगे
आगे
पहले सर स्पीच देंगे वरना से 2 मिनट
Yes. So we now move to a very special segment of the program, the felicitation of newly elected individual members of Indian National Academy of Engineering. We have the privilege of felicitating the newly elected individual members of Academy. May I request all the members to be seated in front rows as I've announced the names. Let us congratulate all our newly elected individual members with warm round of applause. May I kindly request Professor Indranil Manna, former President INAE and Vice President BIT Mesra, and Professor Santanu Chaudhary, Vice President INAE, and Professor and Dean School of Advanced Computing, Ashoka University, to please come on the stage to felicitate our newly elected individual members. Should I announce the names? So, I would announce the name. Please, one by one, come forward and collect your certificate. Professor Sridhar from Mahindra University, Hyderabad. Thank you. Next we have Professor Roy from BITS Pilani. Thank you. Next we have Dr. A.V.V. Prasada Raju from HES Infra Private Limited, Hyderabad. Thank you. Next we have Thank you. Next we have Dr. Pushpatan Jain from VIT Bhopal University. Please can we have a round of applause for him? Thank you. Next we have Dr. Poorna Chandra Saha from KIIT Bhubaneswar. Thank you. Next we have Professor Gargi Das from IIT Kharagpur. Thank you. Next we have Dr. Paramita Das, IISER Bhopal. Next we have Dr. Shubham Banerjee, Naipur, Guwahati. Next we have Dr. Ashish N. Savarkar, MNNIT, Allahabad. Thank you. Next we have Professor Venkatesh K. Prabhakar Rao from BITS Pilani. Thank you. Next we have Dr. Vijendra Venkatesh. Thank you. Next we have Dr. Arindam Biswas from Kazi Nazrul University. Next we have Professor Akshay Kumar Verma from SOA Bhubaneswar. Thank you. Next we have Mr. Sudeep Narayan Banerjee from IIT Delhi. Thank you. Next we have Professor V. Vasu, NIT Warangal. Next is Dr. Aniruddha Deb from BIT Mesra, Ranchi. Thank you. Dr. Manoj Kumar, CSIR, IMT Bhubaneswar. Next we have Dr. Bala Muralidharan B, Welltech University, Chennai. Next, Dr. Abhijit Devnath, IIT Varanasi, IIT BHU Varanasi. Dr. Shreyan Sharma, NIIT University, Rajasthan. Professor S. Indu, Delhi Technological University. Mr. Devagya Raman, CSIR, CBRI, Roorkee. And the last one is Mr. Krish Saxena from Value Line Interiors Private Limited, New Delhi. Ladies and gentlemen, let us congratulate our newly elected individual members with a warm round of applause. So, can we have a group photograph of all the members? Kindly come on the stage, and can we have a group photograph? The old members also can come on the stage. The old members, individual members, if they are present here, can also come on the stage. So all the members can come and we can have a group photograph, please. No, sir has refused. That is what I'm saying. No, it has to be pre-planned. No, it is according to the list. Not here. Thank you, everyone. With this, we conclude the morning sessions. Okay, so I request Professor Indranil Manna to briefly address the audience, please.
So good afternoon, and on behalf of Indian National Academy of Engineering, it's my honor first to congratulate all the newly inducted members to our fold, to the Academy. This little ceremony gave us an impression almost like the convocation of a typical university. But you are yourself faculty members, so obviously you are part of this occasion that I'm referring to. You know very well what I mean. We are very proud to embrace you into the fold of INAE. And there's a good reason. You know, I mentioned yesterday, and let me repeat, that for a country which is the largest population in the world, to have only 1,000 individuals as members, as fellows of the Academy, and the Academy, which is supposed to be the highest peer group in engineering and technology, certainly is not a very good commentary, is not enough. So the INAE leadership some years ago decided that we would like to reach out to a much larger cross-section without compromising with the very stringent process that we follow for election to the fellowship. So we have our INAE mandate, and that allows us to elect only 50 individuals as fellows to the Academy every year, up to 50. And typically we consider about 10 times of that, about 500 nominations. And please remember, these fellows are drawn from 3 different groups: academic institutions, research organizations, and industry. We also have a mandate that ideally it should be 1/3 to each of these categories. Very difficult to maintain. INAE also has taken a decision which we call as affirmative step to try and induct more women professionals into our fold. Now, despite all these efforts for the entire period of our existence of 40 years, the number of individuals connected with the Academy directly associated with the Academy stands around 1,000. If you look around today, what the country desires is to make not just any more incremental step, but a very major and a significant and a bold step towards progress and prosperity. And the challenges that the country faces, if you go across if you list out all of them, majority of them actually are of engineering origin or are associated with engineering and technological intervention, be it energy, water, climate, habitation, transportation, security, physical, as well as cyber. In all these cases, we require a very large amount of involvement of the active involvement of the professionals who are serving in various capacities. So we desire to take this fellowship fold to 10 times more than the number of fellows, the membership fold to more than 10 times the fellowship, which means we would like to have someday in the future 10,000 members associated with INAE. Initially, the plan was to induct them in 3 different routes: the senior, the associate, and the junior or student. For the time being, the student part is kept in abeyance, And qualification, you all know, essentially some number of years from your last degree of engineering. And in Engineering Academy, we strongly believe that the first degree cannot be the deciding factor about the quality and importance of your contribution. You might have earned your first degree in some branches of engineering, beyond engineering in science, or even a very different discipline altogether. But if you're actively involved in engineering profession and you are making very significant contribution, then we believe that's good enough a qualification for you to be a part of this National Academy. The numbers that Colonel Rai shared with me until last week stood at 248. And certainly, Shantanu and I weren't very amused because we wanted many more. Today or yesterday, I was told that number actually is nearly 348 or something like that, nearly 350, and another 80 are now currently under consideration. Then again, I would say that still we are not making enough progress. Looking at purely going by the affiliation all of you carry, IITs, NITs, CSL laboratories, various institutions in the private category. I don't think we heard many from industry. So we are going in the right direction, but we need to increase very significantly and without any delay. So in that respect, I would appeal to you on behalf of the Academy that please act as ambassadors of the Academy and identify individuals around you in your department, in your organization, or even outside, who you believe actually is appropriate enough to be inducted into the Academy. And then you know the procedure. And what we have is a round-the-year consideration cycle in every quarter. So every 3 months, INAE looks at the number of applications or nominations we have, and we go through a usual peer process and then announce the result. So this will continue. We are trying to reach out to various INAE academies, INAE chapters. We have about a dozen of them distributed throughout the country to actually identify individuals who should be inducted in the membership. You're aware of the benefits, but instead of sharing you the document which you yourself already are aware, I would make only one very major assertion on behalf of the Academy. You know, it probably will not be an exaggeration to claim that every engineering professional in the country would consider it to be a matter of pride to be inducted into the fold of this Academy, either as a fellow or in any other capacity. We expect all of you would someday in the future be inducted as a fellow, but until then, there is this opportunity that you please try to seize. And please remember that the story only begins today. It should not be seen as if you have got a certificate and a photograph taken and that's where it ends. It should not. There'll be multiple opportunities. This very platform that we have created, Technology Conclave, is actually meant for the members, primarily for the members and the industries. I mean, until now, INAE had other annual events, but this particular one is designed mainly to offer you a platform to present your scientific or engineering exploits. It is just in the beginning, so probably we are following more of a conventional approach of presentation and poster. Yesterday, I myself spent a considerable amount of time listening to the presentations, walked across the posters. Very, very impressive. Absolutely impressive. But the numbers are not yet very impressive. So we need to make a difference there. And it is time that we actually reach out. We have just made a beginning we should reach out to the industries. There are a number of, actually, I would say that someday in the future, the industry professionals should outnumber the ones coming from academia. Because we all know that it's easier for an individual belonging to a university to establish or showcase achievements which are of individual nature. Whereas in an industry, it's rather difficult because you work as a team, you work for a project, and rarely one can cite that this product or process is primarily developed by this individual. But we would like to recognize such efforts because engineering is a team game. And we also are quite aware that no engineering solution is unique. So we would like to reach out to industries and the leadership of the industries so that they actually nominate many more at different levels. We haven't segregated the members as yet into the 10 different sections that we have. We are waiting for the numbers to swell to a reasonable amount, and then you'll actually be associated with specific engineering sections. And each engineering section has certain mandated annual activities, starting from technology gap analysis to holding various events, contests, selections, and various national level activities. So you all will be part of those activities and be an active member of your local chapter. But most importantly, all of you must feel that you are an integral part of the academy and feel charged and inspired to make a difference. This is our job to make sure that you all feel that you are as much sought after as the fellows. And it is with this collective effort, we hope that we'll make a difference to the journey of progress for this country. I may also add that we are the only academy in the country belonging to any of the professions, science or agriculture or medical or all other professional streams. We are the only academy in the country which is not only functionally autonomous, but also is financially autonomous. About 3-4 years ago, we received a direction from the controlling ministry that INAE should emerge as financially autonomous and the government grant would stop in a while. From the initial shock and disbelief, we collected our wits and proved within 2 years that we truly represent the engineering community, because as I often mention that engineers are meant for finding solution to human aspirations and societal challenges. And we said that if we cannot solve our own problems, then we don't have any business saying that we are Academy of Engineering. And we have proven that in ample measures. So you have reasons to feel proud that you belong to an academy which has set up a unique example in this country which never existed before. And now that you are a part of this academy, please take the torch forward and prove that we certainly can make a difference to this country through the pursuits of engineering and technology. So I'll stop here. I think lunch is waiting. Yeah, Shantanu, add a few words. Shantanu is the custodian of the Center for Engineering Education and Excellence. That's another very, very major initiative. Some of you probably are already aware. I'll leave it for Shantanu to explain a few words about that and also welcome you all. So thank you very much. We are extremely proud and happy to have you in our fold and look forward to working together. Thank you and Jai Hind.
So let me first congratulate all the new members who are inducted today. I think this should be considered as a momentous occasion because you are becoming part of the entire engineering community in terms of a bigger body, that INAE. So Indian National Academy of Engineering in that sense is actually looking into the growth of the profession, innovations through the professions, and new technology and discovery in the profession, and how that is to be brought to the service of the society as a whole. And therefore, all of you are part of that initiative from today onwards. They were already there, but today you are formally inducted as part of INAE. And it's very important to have the whole membership and the INAE, the people who are involved in INAE, just not the fellows, but also members together, create the voice of engineers in the country. And being autonomous, this also is a different right in terms of expressing our views and our opinions. And to do that, we need to have a quality in terms of our work, quality in terms of our knowledge, and quality in terms of our commitment. And that commitment itself, which is inbuilt into the INAE as an academy, I think what has been talked about, that CEEE program was initiated. And CEEE program has been initiated with the generous support from Infosys Foundation. And it is targeted for improving the quality of engineering education across the country. We are offering, we should not say courses, but actually kind of an interaction for the faculty from different AICT colleges, giving them the opportunity to come to IITs, look at the coursework, the way it is being done at IITs, interact with the faculty, see the labs, and therefore there is a necessity to look at now the curriculum at a level where it is being done possibly best in the country. So the whole intent is that there has to be a propagation of this quality, sense of quality in terms of education, curricular development, in terms of the exercises the students would do, and the depth of the knowledge of the students. And this is particularly, I think, as members, you can take this thing forward and communicate to your colleagues and others to be part of this CEEE initiative, and also promote many of them to become maybe members of INAE, because your colleagues and your peers can also get benefited through this participation. And one thing I would like to stress upon is important, which actually Professor Pandit also referred to, that it's important to have depth in the area of engineering today. And with AI coming in, that has also become very, very critical. So simple AI or superficial knowledge, which is the students are picking up in various software subjects or programming, etc., and giving them job, that would disappear. And that also enhances the responsibility of engineering in the teaching community, engineering also in the industry. And therefore, industry and academics and the research community coming together is something very, very important. And this forum, that is INAE, actually encourages that. As is being talked about, that we have 1/3, the ideal ratio is 1/3 from academia.
Ladies and gentlemen, a very warm welcome back to the afternoon session of Day 2 of INAE Technology Conclave 2026. We now resume the technical proceedings with a plenary talk on a topic of immense strategic and economic importance. It is my privilege and honor to invite Dr. Rabi Narayan Patra, former Chairman and Managing Director, IREL India Limited, to deliver the plenary talk on the theme Critical Minerals and Rare Earths. Ladies and gentlemen, please join me in extending a very warm welcome to Dr. Patra with a hearty round of applause.
Good afternoon, respected Professor Acharya ji, distinguished delegates. It's a most difficult session post-lunch. Still, we have to, I will try to make it as crisp as possible. So my thanks to Professor Acharya ji for giving me this opportunity to deliver this lecture. Now, this is the topic. This is an overview of what are critical minerals, the attributes. There could be a ceiling in production due to resource depletion in any of these minerals that is being used by industry. Pricing system is not open and transparent, not traded in stock exchanges. It is one-to-one negotiation. Extraction cost also can become variable, or it is difficult because the geology of their occurrence, natural occurrence, is varied. And limited technology access, both upstream and downstream, starting from exploration to downstream value-added products, gadget. Now, strategic mineral is a subset of critical minerals, which is finding use in strategic application, like atomic energy, defense, space, so and so. Some strategic minerals need not be critical, because the first requirement of a mineral being critical is it should be having ample use in the economy, and that should be of economic impact in general. Now, this is how the developed economy has classified critical minerals: European Union, USA, Japan, and India. The red one is the common one for all. India is the 5th largest economy, or 6th, somebody can say that, due to exchange rate fluctuation. USA, the largest economy, Japan, 4th. Now, very interesting, you'll see some common thing like magnesium is critical by Japan, USA, European Union, because they don't make anything. They import everything mostly from China. Our country, it is not there. We have listed potassium, another common mineral, because we need it for our agriculture, for our food production. The green ones are only for India and don't appear in the other countries' list. The important thing to note here is they are variable. Every 3 years or every 5 years, based on the government policy, the countries update the list. In the latest list of United States of America, it has been expanded to 61 or something like that. Almost all elements are there, including aluminum, bauxite. Even some steel is also there for USA, wherever they are import dependent. This is how is the volume of production and market scenario. Crude oil, this is the value, market value. Look at the thing, in none of these 10, rare earth appears. The market is so less. There are only 3 critical minerals appearing towards the end of this list. That is palladium, molybdenum, nickel. And most important is, all these blue arrows, they are basically the bulk base metals. Critical minerals are recovered from their mine tailings, which is not so far processed. And because of the current requirement, there is a rush world over how to recover them from these mine tailings. Even iron ore mines, even in Odisha, some of the known iron ore mines have many of them. Now, it is audience interest always what is China's critical minerals, because China is the provider of all critical minerals to the whole world. And how does China define critical minerals? Mostly China uses it as a geopolitics leverage, trade bargaining. And I have listed beginning 2010. This was not earlier. It started with Senkaku Island incident, putting embargo on rare earth export to Japan, and then 23 onwards it has become intensified. At very frequent interval, trade restrictions have come in. Diplomatically speaking, China says there is no ban on export, but you need to get a license. But the license conditions are so rigorous that the licensee is even asked to reveal who are their customers and what are his customers' products. I don't think, respecting any business confidentiality, anybody will feel comfortable to apply for such a license. That's the whole issue. The second issue here is the biggest economy of the world, 100% defense, Pentagon's requirement of rare earth is sourced from China. Not only rare earth, gallium, germanium, so on and so forth. That's become a security threat for that particular country. Fortunately, it is not so for India, not so for Japan. But this applies to the biggest economy of the world. Now, rare earths we'll introduce and see the importance. Now, International Union of Pure Applied Chemistry, they define it as Group 3, 21, 39, 57 to 71. So total 17. But out of that one, promethium, number 61, this doesn't have any stable atomic nuclei. It is radioactive, very short half-life. So practically you don't see it on Earth. This was discovered in the spent nuclear fuel of atomic reactors. And it was last to be discovered in the whole list of rare earths because of this difficulty. Subsequently, somewhere in 60s, when astronomy progressed, people could see its spectral signature in the distant stars. This is the background of this particular mineral. Now that leaves us to 16. And in that we can see that none of them are really rare. Cerium, crustal abundance more than nickel, copper, neodymium, yttrium, lanthanum more than cobalt, lead, so on and so forth. And densities, many of the REs listed under heavy rare earth, they are lighter. Scandium 2.98, yttrium 4.47, ytterbium 6.9. Many of the REs listed under light rare earth, they are heavier. That's how I have said that. Then how does the term come? This is interesting. This looks boring because it is 250 years of history in a snapshot, chronological history of the discovery. I'll just take first two rows. 1751, the ore gets discovered in a feldspar mine, and for 37 years, nobody could identify what it is. The debate was raging that it is probably a ore of tungsten because it was discovered a few years before that. Others were debating whether it is aluminium iron because the analytical system was difficult. The next plate will bring out the importance of this, which even has its relevance today. This is interesting. This spans over 3 centuries. 18th century, the first discovery, and you could only identify one, yttrium. That is after the second such ore was found. But this was different from the first one. This was basically a heavy rare earth ore, yttrium. And after that, next century, 100 years goes. Then you have cerium, lanthanum, erbium, and terbium. Now you'll see the superscript M that says this yttrium actually is not pure yttrium. This is a mixture of erbium, terbium, and other rare earth. It is something like Matroska stack, the dolls, one is in the other. The front doll is the biggest one, and then you have the smaller ones inside each other. We have egg kind of a thing here in India also, similar toy. Now here, you have to wait up to 1808 till Humphrey Davy brought a paradigm shift in the scientific understanding of what are earths. Before that, earths were thought that they are elements, pure elements. That is why you could see only 2 discoveries, yttrium and cerium, before that. Once Humphrey Davy made the definition clear, brought the concept that earths can be mixture of elements, lanthanum came, erbium came, terbium came. The meaning of lanthanum is hidden, lanthanin, is from the Greek word, because it was hidden inside the cerium ore. Then the history goes on, and the first application was gas mantle, and you have to wait spectroscope invention, 1859, by the same gentleman, Bunsen, his student. Once spectroscope came, the whole lot of them came into picture. Without spectroscope, it's not very difficult by conventional gravimetric analysis. Then you have to wait till you have got atomic energy coming into picture. The nuclear fuels, they basically have the spent thing as rare earth. So ion exchange or solvent extraction is essential to separate rare earths because they are a poison. They capture neutron. Then only the entire refined rare earth system came into picture. Previous to that, it was all mixed rare earth. Gas mantle, your lighter flint metal, then cinemascope projection, so on and so forth. And once the pure refined rare earths came into picture, it took up. You can see this, the top 2 graph. The extreme right end is the rare earth consumption. Just before that, adjacent is the economic growth, GDP. So both can be correlated. GDP grows and rare earth consumption grows. And most of these today are in green economy. And it shows that the market value, if it is X for rare earth, the economic impact could be 1,000 times. Now, this is what in snapshot is spent fuel scenario. The isotopes of all REs, they have radiotoxicity between 1 and 1 million years. We define radiotoxicity as half-life. 1 year means one year half-life. And this is how the natural radiotoxicity falls over the period of time. And this presence is detrimental, and some of the rare earths are used as control rods to monitor or control atomic reaction. Gadolinium, europium, dysprosium, samarium, so on and so forth. Now, this is how the chemistry defines what is heavy rare earth, what is light rare earth. You see this is the 4F inner transitional element orbit. There are 14 vacancies. So till gadolinium, it is 7, the break even, middle way. Beyond gadolinium, 7 to 14, you have odd pairs and even pairs. So the geologists, they define light rare earth up to gadolinium. Beyond gadolinium, it is heavy rare earth. This is the geologist definition. There is no hard and fast rule. Today, in commercial parlance, light rare earth means only 4, cerium, lanthanum, neodymium, praseodymium. Rest all are heavy rare earth. Yttrium, scandium, they don't belong to the lanthanum group. They are above that, 21 and 39, because they have the ionic radius similar to the host of heavy rare earths. They are classified as heavy rare earths also, because their chemical properties are similar to heavy rare earth. Now, look at this acidity. Rare earth is a salt of weak base and strong acid, mineral acid. And the first one, when you neutralize, to precipitate is the heavy ones. The light ones get precipitated last, lanthanum being the last. So that shows the heavier one will always settle fast. And that is how the name struck, that it is heavy rare earth and light rare earth, and that continues. This is the defense application. Whether it is optical fiber, communication, radar, sonar, high-efficiency electric motors, lasers. Lasers are interesting because today the lasers in defense are used for direct energy weapons. And you have electronic warfare, all are used. The world production 25, 390,000 tons, 0.39 million tons. Heavy rare earth is 15,000 tons only out of that. And the growth 6 to 7%, compounded annual growth rate. Compared to that, steel is 1900 million ton, lead is 78 million ton, titanium metal 0.32 million ton. It's a very minuscule production. Now, these are the industry sector applications. 95% of the volume of all industrial application is this 10. Cerium, lanthanum, NdPr. Others find in defense and some strategic application, not much of economic impact. Neodymium, praseodymium, dysprosium, terbium. These are the 4 much sought after used in neodymium, iron, boron, magnet. They contribute to 70% market revenue. Volume of production of cerium, lanthanum is 2/3, but its value is the least among the entire basket of rare earth. Now, they are all in demand because of the permanent magnet, which are used in renewable energy sector. The import to India was 4,000 ton of this magnet. The world production is 3 lakh ton, little more than that. And this is in snapshot the history of application. And this also teaches us the problem with rare earth market today. It starts with gas mantle, which brought brightness to the dull yellow flame of the gas burner. When electricity was not there, this was the source of light after sunset. The Brazilian government, from where the monazite used to be sourced those days, they realized this and put an embargo on export of monazite to Europe and America. So the search started for alternate market, and that is how our Malabar coast beach and mine was discovered as a good source of monazite, alternate to Brazil. That means today what is happening with China, it happened more than 100 years back with Brazil. Subsequently, electric bulb came and this became obsolete. Then comes your CFL and electric bulb gets obsolete. Then comes your LED and your CFL gets obsolete. With LED and CFL, the difference is quantum of rare earth use. Both use rare earth as the phosphor material, but LEDs use 1,000 times less. The Molycorp mine in USA started in 1960 because European price was the highest, $2,500 per kilo in 1960 price. But the technology change today has brought it to $35 per kilo in 2026. This is the impact. This is how the market gets. Market is dynamic. 1915 was the cinemascope projection. The carbon arc electrodes in the core will have rare earth fluoride. That gives the bright arc lamp. But then comes your color television where European was sought after. That is how Molycorp started. But then you have digital projection. Today all cinemas are digital projection. And all these carbon arc electrode, rare earth fluoride is gone. Last one is our flint metal, which when struck gives you the spark. And then comes piezoelectric, so flint gone. Today in battery, it started with rare earth battery, NIMH. That metal is mixed rare earth. Today you have lithium. That battery is losing its appeal. And then S&T advances, we really don't know what will replace what in coming years to come. Difficult to predict. So our introduction is 1908. I have already said that because of the geopolitics of Brazil, leverage used by Brazil government. Malabar thing was discovered, the resource. So 1950, first Indian listed company happened after Atomic Energy Establishment Trombay was formed in 1948, post-independence. And that was the beach sand deposit of Kerala and Manavala Kurchi. This is what is the history. 1952, we had the first monazite cracking plant in Aridi Alwa. 1955 was thorium plant in Trombay, which was taking crude thorium concentrate to process, uranium, thorium, and that cinemascope material, that is the bright spark-producing material. And 1965, beach sand mining starts in Indian rare earth. Now, it is interesting that there are companies in Bombay who applied for patent in rare earth metal in 1970s, based on chloride process. CSIR Secri had 2-3 patents on making rare earth metal from chloride electrolysis, way back that. But then we forgot, we lost the whole track of technology development and stuck to the same thing, and we have to close the operation by 2004 because it was not economically competitive with export material coming in. Now, these are the host of minerals. It starts with oxide, carbonate, phosphate, all kind of minerals. And they occur in different geological settings. Some of them are even in phosphate rock, that is your phosphatic fertilizer. Some of them are coming in a silica-rich environment, sorosilicate, ion silicate kind of a thing, cyclic silica. So they're difficult to process. You cannot extract them easily. You know, silica-based things, they become gel. Today, the world is focused only on monazite-based source and basnasite, the top one. That is a fluorocarbonate. Silicates-based things, they are rich in HRE. Deposits have been discovered in India as well as overseas, but the extraction is yet to be proven. Apart from that, you get it in host of these materials. You get it in coal seam, you get it in iron ore tailings, you get it in titanium ore, beach sand mineral, you get it in niobium ore laterites in Brazil, you get it in phosphate mines, you get it in tin ore, Malaysia, among. And this is how it is. 62% rare earth is now coming from basnasite, only 5% coming from monazite. The other alkaline, igneous and all that is very, very minimal in that whole thing. This is the challenge. Now coming to the beach sand mining, this is the snapshot. The left-hand extreme is the Molycorp mine. This is the hard rock. The middle one is the Indian operation, dredge. That is the beach sand. The extreme right is your ion exchange clay. You simply put sodium chloride or sodium sulfate or magnesium sulfate. The rare earth in the clay exchanges with the cation in the solution, comes to the solution. And you simply precipitate it and recover it. These are the 3 types of things. The extreme one, ion adsorption clay, is the source of heavy rare earth only. Monazite and genotime, they also give heavy rare earth. Molycorp is mostly light rare earth, no heavy rare earth. And these are the host of minerals you get in beach sand heavy mineral, 7 of them, ilmenite, rutile, zircon, monazite, and they have different properties, electrical, magnetic, gravity, and so on and so forth. Diamond, incidentally, also is a pressure deposit. And the definition of heavy mineral is 2.9, density and above, they are heavy mineral. Here it is density, not the other heavy rare earth, no connection with density. Now this is the mineral separation. You just take the advantage or the difference between the gravity, electrical and magnetic properties and then separate them into minerally pure form. But the problem here is tailings of one, like ilmenite tailings, will be a zircon rich source. Zircon tailing will be a monazite rich source, so on and so forth. Monazite is a contaminant because it is radioactive. But at the same time, this is valuable because of rare earths demand. This is the geological occurrence. You can see the orange color things. They're all your potential rare earth deposits we have been discovered. Now, this is the flow sheet, caustic attack of monazite. This is what we operated in rare earth division Alwa, 1950 onwards, and closed in 2004 because of lack of market demand. And this is the thorium nitrate that brought out the residual rare earth value from the crude thorium concentrate, uranium, and produced gas mantle grade thorium by fractional precipitation. That's the first method used to refine rare earth. We had that plant. And the metal making, as I have said, you can get it by electrolysis of fused salt in chloride medium, or you can get it by fluoride medium. Chloride was the first. India adopted it to make mismetal. Fluoride is the latest. We have not gone into that, and today it is under development. Now, these are the magnets you can see from drone, electric vehicle, flying aircraft, wind turbine, everywhere it is required. They are basically characterized by two properties. One is the higher coercivity, stability at high temperature. Other is the remanence, the magnetic field that remains in the absence of any external magnetic force. And most of the things are happening in the defense sector because drones, unmanned aerial vehicles, surveillance vehicle, all are using this kind of magnets and robots. Now the industry, this is a 40-year-old industry in India. We have alnico and ferrite, well established here, people make it. But once these rare earth magnets come into the country, we don't have any technology to make them. We don't have technology to make even metals in a competitive way. So they are imported as the crude blocks. They are machined here, then they are given a corrosion-resistant coating and supplied to European market, American market, and even domestic market for as per end user specification. This is how the thing operates. Now the metals of rare earth are extremely sensitive to oxygen, and oxygen is a contaminant and poison for magnet. So the metals have to be immediately converted to magnet. You cannot stock metals. Like iron can be stocked as iron ingots or similar aluminum, it is not so here. That is why metal, alloy and magnet, they are integrated economically for practical purpose. But technologically they remain three distinct technological steps. And this is what we have already discussed, how it is, and this is the entire family of permanent magnet. Samarium, cobalt and ferrite and among the rare earth magnet, you have bonded magnet, sintered magnet, varieties. There are more than 300 such varieties. So magnet becomes a generic term. It's not a product per se. And this is the value stack of the entire thing. And you can see there is a lot of internal recycling happening at each stage. At refining, at metal making, at magnet making. The swarf generated in magnet making by machining the block magnet is up to 40%, very high. And that needs to be reprocessed further. So recycling is inbuilt. Same thing happens with our lithium-ion battery also nowadays. So this is a characteristic of these type of industries. And they're amenable for small-scale manufacture, many of them. You can have a big industry, no problem, but economy is less sensitive to the scale of production. Now the green one, the existing industrial operation, the orange one are under development. That is only the magnet, alloy, and metal. Now, the industry is driven by application and performance. We have already seen it in the previous slides. And these are the challenges. I have only summarized what I have discussed so far. Mineral resources availability, even if you have resource, you should have the knowledge to extract. Product obsolescence, single country market monopoly, supply chain vulnerability, proprietary technology access, supply-demand imbalance. Now, this is the pie chart showing the production of different rare earth element. We have already discussed this. Cerium lanthanum more than 66%, neodymium hardly, praseodymium only 20-25%, and heavy rare earth less than 1%, 2%. Look at the price. Dysprosium cost 4 times neodymium, praseodymium. Terbium cost 4 times dysprosium. Cerium lanthanum are 100 times cheaper. But for magnet, you need these costly ones. Now, this makes the whole trade geopolitics interesting. 60% mine output from China, but refining 87%. Metal 91%, magnet 94%, value-added products 45%, electric vehicles, and windmills 29%. Electric vehicles in China cost half that of electric vehicles or even cars made in USA. That's the challenge. Now, we have that old proverb, carrying coal to Newcastle. But here, the proverb goes the other way. China imports rare earth beginning 2011. And today, the rare earth produced in China is 73%, more than almost 75%, converted to all value-added products. And Chinese import of rare earth has been increasing steadily. This makes the whole thing a matter of concern to all other nations in the world. This situation never happened, never occurred in the history of mankind, civilization history. Single seller, monopoly. We know a single company doing monopoly business in a particular product or service, but here the country monopolizes entire product services. And single buyer. If you have to sell your concentrate, if you have to sell your oxide, because you don't have the technology to convert to metal and you have to give it to China only, because there is no other buyer. This is economically said monopsony. So you have monopoly and monopsony by one single country. So all other countries' economy is indirectly can be manipulated or handled or controlled by a single country. Now, this is a summary of that. Concentration of mineral resources. This is what we have discussed earlier. 65% of world's RE production is obtained as a byproduct, which you have seen in our critical mineral slides. Only 35% are standalone rare earth mines. Now, sovereign control and high monthly price volatility. Of course, you can't eliminate that when such a situation is there. Now we come here, 2047, Viksit Bharat. Atmanirbhar Bharat was launched in May 2020. National Critical Mineral Mission came in 25. And this mission's entire objective is to support Atmanirbhar Bharat mission. This is Government of India's answer to fight this issue. Now, these are the strategies. I think strategies are very clear. This comes from the common sense. It doesn't require any rocket science. You have to build your strategic reserve, expedite exploration. That's what is being done. Inter-country agreement and collaboration. I think in the last 2 years, India has signed 32 such agreements, various countries. And you get it from secondary sources. Use only when essential, because you don't have enough of this source. And substitute wherever it is possible. Like you can use ferrite, you can use iron nitride, you can use iron samarium nitride, copper wound rotor also. And you can have magnets without any heavy rare earth, without any dysprosium, terbium, and even extent neodymium, praseodymium to the extent of about 30% by cerium and lanthanum. All these products are there in market, but they're all done by China. Now, last one is the recycle. This comes the engineer. What he does, performance, growth, and resilience are to be balanced, economic gains, cost, and sustainability. Example is this. Look at the right side in the red box. The magnets, we know, cannot withstand high temperature operation. You have to add heavy rare earth. If you don't have heavy rare earth, you get magnet whose operational temperature is only 80 degrees centigrade. Your electric vehicle magnet can go up to 160 degrees when the vehicle is under operation. So what do? You go back to basic physics. You make magnets in thin section and insulate them and stack them up. So eddy current heating is completely eliminated. It's already done and proven. Here, again look at the motor design. The electric motor using a permanent magnet will be always subject to a permanent magnetic flux. But during the motor operation, you require the magnetic flux varying as per the motor torque because the speed can go up and down. So this is what gives you the electronic control. Designing electrical motors based on copper wound rotor, which can even perform better than permanent magnets. Or you can have a hybrid arrangement, little of permanent magnet and mixture of copper wound rotor. So what the engineers do is this, take the bull by the horn. Wherever the problem, you go back to the basics. And you look at the drawing board for a product design. Deep understanding of industry's business process and value chain, extremely essential. Identify key risks and impacts. Timely implementation of appropriate actions for leveraging opportunities. See, quite often in many of these seminars which I attend and I participate, the issue gets mixed up. The company's risk requirement is projected as the country's risk requirement. That's wrong. Country's approach should be Viksit Bharat or from a broader angle. The strategic requirement gets jumbled up with common civilian application requirement. So one need to make a distinction on three things. What are the strategic requirement? What are the industry requirement? Where the companies will take action and where the government will exercise the policy or governance requirement. So that gives this framework. The risks are geopolitics, climate change, disasters, and academics R&D comes to solve the problem of product design or improvement or elimination of critical material with abundantly available material, and government is the facilitator. Then only you can reach the Viksit Bharat. Now, rare earths are really not rare. Our planet Earth is rare, so one has to be environmentally cautious. Rare earths are born in distant universe when supernova explosion occurs or neutron stars collide. Criticality is a human-made issue, best managed by networking, collaboration, and governance. Thank you. Any questions?
So what about lithium deposits found in Tibet? Is it...
See, we have deposits. We have in AIC in Jammu and Kashmir. We have deposits in Karnataka. But the question is extracting them in a very economical manner. See, the problem is lithium today, world, is getting bulk lithium from the rock source, spodumene, Australia. The balance is coming from the brine, that is Latin America, mostly Chile. Bolivia and Argentina, they have that, but their government policies and facilitation network does not make that accessible to the world consumption. So if you look at it, the lithium what you get in Jammu and Kashmir is a clay deposit, hectorite clay. So it is only 500 ppm. Initially, that deposit was surveyed and explored for bauxite. Okay. There is alumina in that. That's why the question is not only having a deposit and its report, but its extractability and the economics of it.
Patra sir, with your permission, lithium update I will give to them. Lithium India has 4 resources that, as sir told, that one is Riyasi, one is Amreswar, then third one is Degana, Rajasthan, then just now it has come out in Korba, and then mica belt of Jharkhand. So these are the major primary resources of lithium. And a spodumene deposit is almost like Australian deposit. So Amreswar we have developed lithium carbonate, and it in IMMT has already developed the process technology at 1 kg level, and battery performance was checked by Sikri Karaikudi. So it is giving similar performance what is available in the market lithium carbonate. When we were touching this Riyasi deposit, as sir told, that it is having clay version, and if you go for, it is a spread. Some place you have 10 ppm also, and one place 1700 ppm also. So if you take overall blend into that, it comes to 400 ppm, 4 to 500. But in normal beneficiation route, it's not possible to do that. But now we are making it a rock again. First we have to go for heating and then bring back to that. So that process is there. Degana is once again, it is a hard rock, and we were able to develop the process. It was responding well. And mica, it is very difficult to grinding on a Patra sir. We were going, have asked him also that can we go for cryogenic type of system. So then only it will come, otherwise it was not coming. And Korba work is going on. This is the lithium deposit status in our country.
We import it when we get a battery from outside.
Yeah.
The lithium part of it is
completely imported. But now one good resource is the secondary resource. That whatever you have consumed the battery, that recycling is a probable option. And what sir was talking, that rare earth free permanent magnet one, he was talking, that place also efforts are on that for cathode or anode, those type of materials, once you will recover, can you blend with the other resources so that it should give the same stability? So that approach. So right now, both the things you have to go in a complete circular manner. Primary you explore, and now sir was in the committee of that Khanij Bidesh Ligam Kabil. Kabil is also sourcing from Argentina in that brine solution, and it is good in other parts of the world. So we are also trying to resource from there.
Thank you, sir, for the wonderful presentation. I just wanted to know, the initiative of rare earth minerals has started just now. What is your vision that we would be, if I not say self-sufficient, but the kind of time frame that we would require to really at least gain some critical mass in India, so that we are not 100% dependent on China or other countries?
So to answer your question, I will quote Honorable Minister Dr. Jitendra Singh, Minister of State under Prime Minister's office. It is on print through Public Information Bureau release and as well as public mass media newspapers. The statement is that India is self-sufficient in rare earths and do not need to import anything from China. That's the statement, Honorable Minister in the Parliament. Because Parliament members are also equally concerned about your issue. Now, this is for strategic sector. When government is giving this statement, this is for defense, space, and atomic energy. Industry application will be at least 20 times more than that. Now, for that, we have only sourced monazite. That's what we are processing today. And the MMDR Act, the umbrella legislative framework for all minerals, only in 2023, which I showed in my first slide, included all these minerals as critical minerals, some 24 of them. Otherwise, previous to that, it was all listed as atomic minerals because of monazite. And following that, there has been 71 auctions. Out of that, about 5 or 7 are rare earth, maybe more than that. Most of them are in Karnataka, some of them are in Telangana, some of them are in Rajasthan, 3 or 4 of them. North eastern region, that is Meghalaya, Arunachal Pradesh, they are yet to be explored. There is a lot of potential there, particularly for heavy rare earth. Now, the bids have been given and owned by many private entities. Now, question is, they will do the further exploration, they will develop the extraction, probably business for Dr. Ramanujan Saab. And then the industry will come, then you have to wait. Maybe 5 to 10 years. That's the horizon kind of a thing for this kind of thing. Now, industry cannot wait for this or should not wait for this. So there comes the innovation, look for alternate thing. And I was keeping track of this developments. Just answer to your question. There are 7 efforts on, including one in Bhubaneswar, Indian Institute of Technology, to develop rare earth-free motors by copper wound rotor. One company in Bangalore already markets that. And there are 2 or 3, they are developing it. There is one Indian company in Bangalore who has got the patented version of iron nitride as the permanent magnet, the latest, USA. And he is trying to put it into the motors to be made in India. So a lot of efforts are happening. I was looking at the news items 2025, June to October. When this issue took a very center stage, all electric vehicle manufacturers ran to government telling that China stopped giving material and their production is affecting. Bajaj, they stopped their 2-wheeler production and were diverted to 3-wheeler production. But the big companies, the representative is here, Tata's and Maruti and Mahindra's, they never went there. They said they're fine. So this is a corporate issue. They have identified the risks in advance and taken action. Others who did not, they suffered. But all companies have a backup plan. There is one company who overnight shifted his base from India to China. That means he was making effort while pushing with government. So what we hear in the seminar is many times a simplified version of a complex issue. And that gives an impression which is away from the truth. Okay? Yeah.
Other than monazite resource, that in northeast it has come out nearby that Burmese border, and then second one it is in our Odisha itself. That if you go to Nagar zone.
Yes.
And then third one it is coming to our that coal belt of
Singarani coal field, particularly
coal field. So these are the other resources which will help us, and we want your thought into that direction, because monazite anyway.
Yes. See, a lot of activities has happened, you know. I was fortunate to chair a committee for extracting scandium from red mud, that is a bauxite waste, because scandium is something which we don't have. And the world production scandium today is 80 ton only. I have put it in my slide. Now, India doesn't have the resources, and where is scandium produced from? Scandium is produced from the iron sulfate waste of titanium industry.
So, sir, in this context only, under your supervision, NRTC, sir, we have brought 50 kg fly ash processing unit, that iron hydroxide, which contained RE, although
Yes.
that we have established already plant, so some of you want
So I think Nalco is putting up a 100-ton pilot scale plant.
Yeah.
And very interesting is Singareni coalfield, because that coal, organic form mostly, non-carbon material, that contains lutetium. This is one of the heavy rare earth. And even 2 ppm, 3 ppm, 5 ppm lutetium is good enough for commercial extraction. Where is lutetium used? After the China banned, lutetium using companies were all in USA. 85%, 100% lutetium is exported to Japan and USA in the world. Nobody else does it. Where do they use it? They use it in two strategic places. One is direct energy weapons, lasers. This goes a little doping into the yttrium, aluminum, garnet glass. And that improves the laser power and gives it the focus or the energy. Today 100 kilowatt lasers are very common. In India we have 30 kilowatt lasers already announced by DRDO. The second one is submerged lithography. I think people here will know better, Professor Acharya-ji. That's when your chip size comes below 193 nanometers. Your ordinary process of graving doesn't work. So what you need is, previously people used water simply to improve the refractive index so that the magnification improves. Today you use this type of glasses, that is yttrium, aluminum, garnet, either doped with ytterbium or lutetium. And lutetium is another example, is your prostate cancer. The radiation therapy is by lutetium-177. We import from various sources. Brit is the person, and we produce that radio pharmaceutical, and here it is 10,000 rupees or something like that. That's what I was told. But abroad it is more than $10,000 a shot. That's the kind of a thing. So, question is, if you require value for a mineral, then you should know how to apply. If you don't know how to apply, there is no value.
This is Professor Aparajita from Carnegie Mellon University. Thank you for that very illuminating lecture. I left chemistry a long time ago, but you know, the way you explain stuff, we lay people, we understand. I also am in touch with Professor Gautam Desi Raju. I don't know whether you know him from the Indian Institute of Science. So my interest in this is because of that. I was wondering if you could tell us a little bit about thorium. I know it's not a rare earth, but it would sort of leave us on an optimistic note about India, because having seen those pie charts about China, very alarming. So would you tell us a little bit about India and thorium?
See, as I have explained in my beginning slides, thorium first was put to use somewhere in 1884, gas mantle, thorium nitrate. But thorium nitrate per se will not give you that brightness unless it is doped with 1% cerium oxide, which is a rare earth. But then thorium is radioactive, we all know this. Those days electricity was not there, so you are using thorium, this be broken under nuclear condition to give you energy, okay, because of the mass conversion. Now, between thorium and uranium, only uranium-235 isotope is capable of undergoing fission. And that content is 0.7%. So 99.3% of natural uranium-238 cannot undergo fission like 100% of natural thorium-232. So what you have to do, you have to start with enriched uranium. That is 0.7% to 35. Now coming to uranium resources in India, we are equally poor. We didn't have the rich uranium resources as Kazakhstan has, Canada has, Australia has. That's why in 1950s, Homi Jahangir Bhabha, the father of nuclear energy in India, he envisioned that three-stage program. Today, if you look at the nuclear reactors operating across the world, 450 and odd are there. Bulk of them are light water reactors. They use enriched uranium, which you know as low enriched uranium, below 20%. Typically 3 to 5% enrichment for this type of power production. Who are using this? France, USA, because they have access to good quality of uranium material. Then why do we opt for a heavy water-based material, light water? The reason is simple. The reason is economy in uranium utilization. If you use a low enriched uranium, you can imagine how much of natural uranium will remain unutilized just to enrich 0.7% to 3% or 5%. Now, somebody can afford it who has got access to that resource. When India doesn't have a resource, our uranium is extracted from over 400 ppm. Even today, they are 1%, 1.5%, even 2%. Natural uranium reactors, which use heavy water as the moderator, they are most economical in utilizing uranium. That's the reason India is the only country in the world fully using this type of reactor. That 700 megawatt thing which one of the speaker covered and all that from previous CMD of NPCIL. Now you use this and you generate plutonium and then you use that plutonium to breed thorium. That is the second stage. Prototype fast builder reactor that gone into criticality a few months back. And we are expecting that it will be connected to the grid in a near time. This will generate a lot of thorium generated uranium-233, which are capable of undergoing fission further. Then you will have the third stage where only thorium and your plutonium will be used by using natural uranium, whatever is available in the country, and thorium, Madam's question. Now it looks so simple, but the problem is reprocessing. You will not be allowed to reprocess the spent fuel to recover plutonium. Because if you don't reprocess spent fuel, you cannot get plutonium. If you don't get plutonium, you cannot start second stage or even third stage. So answer is Atmanirbharata. If you buy plutonium from Canada, if you buy from Australia, if you buy from Kazakhstan, you are mandated for international inspection, which we call safeguard. But if you use your own uranium, no questions can ask. Sovereignty of the country. So uranium exploration in last 19 years, 20 years, beginning 2007, the resource established has gone from 63,000 metric ton to more than 4 lakh metric ton. But the grades are all of 400 ppm, 500 ppm like that. So this is the challenge. Now, if you want to shortcut this, the simple answer is, looking at it in a very holistic manner, if the starting material is uranium-235, and you have to essentially go through plutonium and then uranium-233 coming from thorium, then why not integrate all these three processes? Why these three stages? That is where the liquid molten salt reactor comes in, which was mentioned. Molten salt, this entire thing is in a molten salt medium, and the plutonium produced gets consumed. Thorium gets converted to uranium-233 and gets consumed. And molten salt is periodically drawn because it is a liquid and reprocessed and then sent back. That is under development by BRC and Atomic Energy. This is where the engineering comes into picture. Okay?
Thank you very much, Dr. Patra, for that enlightening and insightful plenary talk. May I request Professor Damodar Acharya, Chairman, International Advisory Board, SOA University, and Chairman, INAE Bhubaneswar Chapter, to please come on the stage and felicitate Dr. Patra. Thank you, sir. We now move to the final panel discussion of the conclave on a theme of immense significance to India's industrial and energy future: reduction and diversification of energy inputs in energy-intensive industries. To deliberate on this important theme, we are privileged to have with us an eminent panel comprising leaders from industry and academia, each bringing a wealth of experience and expertise. It is my privilege to invite Mr. Shashi Shekhar Mohanty, former Director, Steel Authority of India Limited, NSR Steel, to organize and moderate this distinguished panel discussion. Joining him on the panel are Mr. Biswaranjan Pillai, Executive Director, RSP SAIL, Mr. Bibu Mishra, Advisor, Hindalco, Shri Naveen Ahlawat, he'll be joining us virtually. He's President and Head, Sustainability and Decarbonization, Jindal Steel Limited. Mr. V. Upadhyay, Head of Vedant Aluminium. We look forward to an engaging exchange of ideas and practicing insights on advanced energy efficiency, sustainability, and resilience across India's energy-intensive industries. May I now request Mr. Shashi Shekhar Mohanty and all our esteemed panelists to kindly come forward and take their seats for the panel discussion. Ladies and gentlemen, please join me in welcoming our moderator and distinguished panelists with warm round of applause.
Good afternoon to everybody. Am I clear now? Yes or no? Being the last, activities in the entire 2 days event. I thought in the panel discussion to change the microphone instead of going to the talk every 5 minutes. The best way to do that, so I take your permission to use this mic and continue. Good afternoon again to all of you. In fact, when Dr. Damodar Acharya contacted me, sir, Mr. Bhanti, not only will be a part of the organizer, but be a moderator for the event that is on the energy. That time I didn't know it will be also last event, almost last event of the 2 days event. I believe that almost all the fatigue that you're having for the next 45 minutes, let's forget that. And I have with me all experts from steel industries and also aluminum industries who will be keeping you engaged. Rather, I will make them keeping you engaged with all of you for the topic that we are talking is very, very vital and essential for the energy intensive industry today. Along with me, there are 2 panelists who are from the aluminum industry. They are veterans, and also 2 steel experts. They are also good in expert in their own way. But before that, it's my present duty to introduce them a little bit. What I think has been written here about that. As far as I know, Bibu was basically Mr. Bibu Misra. He's a pass of 84 from NIT Rourkela, and I think probably he has worked every aluminum industry that you see in this world, not in India. He has worked in Nalco, he has worked in Vedanta, he has worked in Hindalco, he has worked in Bahrain, he has worked in anything aluminum industries. He is there. He is the person. So with me, you got an expert who have been seeing the aluminum industry growing. Left to me, Biswaranjan, who happens to my colleague in Steel Authority, and right now Executive Director works, and also he has enough experience right from the prime, the steel making to all agglomerate industries. Right now, he is heading the operation of a 4.5 million ton steel plant in Rourkela, which is going for a 10 million ton expansions. Right now, he has driven all the way back from Rourkela to here and just reached before a few minutes. And with me in the dais, with Bivav, who is an IIT pass out, IIT Mumbai pass out, and working as the head of the operations of Vedanta Aluminium plant in Jharsuguda. But he is also a aluminum veteran because he also remained in Hindalco for a long time before last couple of years he changed to Vedanta. I think with us, I don't know whether it's getting connected to not. Naveen Alawat is basically a president of Jindal Steel on sustainability, and which you have to understand not only energy and sustainability, they go together. I think when the organizers will be able to connect, I will be connecting them. So having said a brief introduction of my experts, I will drive this panel in this way. I'll take few minutes to set the context on what basis we'll be able to. Then I'll go in a round 1 to each one of steel and aluminum. Then we'll go for round 2, and round 3, of course, whatever the audience we are with us, a late audience, can also interact with us. And round 4, along with all permission, we conclude our discussions. Naveen is connected. Yeah. So, ladies and gentlemen, let me just tell you, when you talk about energy-intensive industries, in the industrial sector, when I meet at industries, there are at least 4 industries come to our forefront to be identified as the energy-intensive industries. What are those? These are power industries, these are steel industries, these are aluminum industries, cement industries, of course, there are other chemical industry, but I'll let these 4 major energy intensive industries per se. Out of these 4 industries, as I said, we have with us 2 major energy guzzler industries. One is steel, another is aluminum. So why? Again, a context I am setting. In a state like Odisha, we are the largest steel producers, we are the largest aluminum producers, and no wonder we have got experts who will be able to not only give the macro view of the world and then India, then also about the Odisha. So having said that, my first question will go to Vishwaranjan, and it will be same. I will be going one by one. After Vishwaranjan, I will go to Vibhu, and then I will go to Naveen, then I will go to Vibhav. And Vishwaranjan, just you have to tell me out, when you talk about energy intensity in the making of steel, and normally we define the energy in terms of a specific energy consumptions per ton of crude steel. So just in keeping this in view, from the day we joined the steel plant, I will be completing my 50 years of steel industry next year. That will be 5 decades. From the day we have joined, and when the 60s when we started the industry, I'm telling you, and from that day to today, we have almost reduced the 60% of the energy consumption per ton of crude steel.
Yes.
And having said that, I just wanted to know, to take you through, in the steel industry today, what has been your energy scenario in terms of consumption, in terms of international benchmarking, in terms of efforts that you are going to reduce the steel, the energy consumption per ton of steel. Yes, Vishwaranjan, please.
Okay. Thank you, Mahesh sir. And सभी को नमस्कार. ये सामने में प्रोफेसर दामोदराचार्य सर भी बैठे हुए हैं, जो हमारा सीनियर भी थे वहाँ पे कॉलेज में. तो ये जो क्वेश्चन मानती साहब जो हमको, मैं भी जब पास आउट होने के बाद में जब 89 में ज्वाइन किया था भिलाई स्टील प्लांट में, अभी जो हमारा प्रेजेंट सिनेरियो है, मैं सेल का ही बात कर रहा हूँ. हमारा जो स्पेसिफिक एनर्जी कंजम्पशन अभी पर टन ऑफ क्रूड स्टील, वी आर अराउंड 6 giga calorie per ton of crude steel, 6.1, 6.05. But at the time when we joined, that was around more than, I think, 9.5, 10. तो ये जो इतना दिन का जो सफ़र, इतना दिन का जो जर्नी है, we have done a lot of things. ये अपने आप as it is स्टील इंडस्ट्री में नहीं आया. एक एग्जांपल बताऊंगा कि जब प्रेजेंटली आई एम वर्किंग इन राउरकेला स्टील प्लांट. राउरकेला स्टील प्लांट इज हैविंग ए 4000 मीटर क्यूब ब्लास्ट फर्नेस. जिस ब्लास्ट फर्नेस से पहले हमने 5000 to 6000 के अंदर में जब हॉट मेटल बनता था, वो सेलिब्रेशन होता था पर डे. नाउ ऑन एन एवरेज वी आर प्रोड्यूसिंग more than 9,500 and 10,000. ये कैसे आया? मैं एक्चुअली एनर्जी से वहाँ तक प्रोडक्शन तक चला गया. उसका रीजन ये है कि हमारा जो मेजर स्टील प्रोडक्शन दैट इज़ फ्रॉम BF एंड BOF रूट, यही हमारा ट्रेडिशनल पाथ है, एंड बल्क प्रोडक्शन के लिए यही पाथ ही एग्जिस्ट करता है. बट इसमें जो चेंजेस सब आया है, अभी हम लोग ने ब्लास्ट फर्नेस गैस को द टॉप प्रेशर रिकवरी टर्बाइन के थ्रू से, TRTG के थ्रू से उसका ही एनर्जी को यूज़ करते हैं. वेस्ट हीट रिकवरीज मेनी प्लेसेस, सेंटर प्लांट्स, ब्लास्ट फर्नेस, वहाँ पे यूज़ हो रहा है. हमारा पास में अभी पहले जो वेट क्वेंचिंग कोक ओवन्स का था, हमारे वहाँ पे ड्राई क्वेंचिंग जो फैसिलिटी है, वहाँ पे हम लोग बैक प्रेशर टर्बाइन्स यूज़ कर रहे हैं. ऑल दीज gases are being used for power generations, and those power we are using for our steel making also. And उसी के साथ साथ में हम लोग ने हमारा फर्नेस में जो रोलिंग मिल्स का फर्नेस में हाई एमिसिविटी कोटिंग्स यूज़ करने के बाद में हमारा वहाँ पे एनर्जी कंजम्पशन has been reduced by almost 6 to 8%. A lot of things we have done. Then जो सबसे blast furnace में सबसे important thing एक होता है coke rate. But अभी हम लोग ने coke rate को कम करने के लिए जो सबसे important another is pulverized coal injections. We have maximized our pulverized coal injections. So that has reduced our coke rates. Ultimately, our energy consumptions as well as carbon footprints, that is also getting reduced. And recently, we are also going some new initiatives. We have tried biochar injections, but still that is in the nascent stage. And उसके साथ साथ में हमारा जो एक इम्पोर्टेंट थिंग होता है दैट इज़ वन कॉल्स प्रिपेयर्ड वर्डन्स. पहले जो मैं बात कर रहा था जो 89-90 में जो हम लोग ने ज्वाइन किए थे स्टील प्लांट में, वहाँ पे ऑलमोस्ट आप देखेंगे जो आयरन ओर वाज 80-85% आयरन ओर डाल देते थे. आयरन ओर एंड सिंटर ये दोनों था. अभी हमारा प्रिपेयर्ड वर्डन जो है एक उसके अंदर एक इम्पोर्टेंट फैक्टर होता है सिंटर, एंड उसके साथ समय आजकल हम लोग ने पैलेट यूज़ कर रहे हैं. ये दोनों मिलाने से प्रिपेयर्ड वर्डन दैट इज़ बिकमिंग मोर देन 90. तो आयरन ओर दैट इज़ नाउ ए सिंगल डिजिट फिगर में आ गया. तो जब मैंने प्रिपेयर्ड वर्डन जो बढ़ते जाता है, देन जो फ्यूल रिक्वायरमेंट फॉर कन्वर्टिंग दोज रॉ मटेरियल्स इनटू स्टील हॉट मेटल लिक्विड मेटल दैट गेट्स रिड्यूस्ड. तो सर यही बहुत सारे स्टेप्स हम लोग लिए हैं जो कि अभी हम लोग वी आर होवरिंग अराउंड 6.
Thank you, Mr. Anusandhan. I think I'll extend that discussion in aluminium. Maybe we can take it through your consumption at the present scenario. What we are going to reduce those in many of the aluminum industry pass say, because you are a global aluminum expert. So can you just pass it?
Okay, we are discussing about the decarbonization, and if we see that the global footprint or the global decarbonization, which we are targeting almost 50 billion ton, which needs to be reduced per year to maintain a stable 2 degrees centigrade global warming. The aluminium is coming out almost 2%, which is around 1 billion ton. 1 billion ton of carbon dioxide is emitted by aluminium industry globally. And I think steel is around 2.7 to 2.9 billion ton. Okay, now when we see exactly what is being done in the last maybe 2-3 decades, first thing is that for aluminium you need almost 40% of the aluminium production cost is coming from power, that is the electricity. So if we see that domestic electricity we measure as units or kilowatt hour, so we need almost 12,000 units of power to make 1 ton of aluminium. For it, if you compare it as a house, so maybe 2 years, an average house's 2 years aluminium consumption, power consumption will make 1 ton of aluminium. It is that big. Now the other part where we are using carbon is the electrode with which we do the electrolysis. So the process of aluminium making for last, from all the commercial technology and all, it is all same Soderberg the electrolysis process where you have got an electrolyte and there will be a carbon anode which has to be consumed. So that number used to be almost 600 to 700 kg per ton of aluminium when it was Soderberg technology. That technology is almost completely eliminated globally, and now the pre-baked anodes which are being used, with that, with the latest technology, the carbon consumption will be around 400 to 420 tons per ton of aluminium. So there is a huge reduction, and also one big Soderberg technology has been completely eliminated. With that also a lot of fluoride emission and all that has been reduced. On power consumption, also if you see, there is a significant reduction. Almost when around 40 years back, it used to be almost 18,000 units of power per ton of aluminium. That has come down to around almost to 12. So there is almost a
30 to 40% reduction in the power consumption. When we see the even in the same sort of technology, if you see the old and new plants, now the plants which are coming up, like the plants in India, some of the Vedant plants, and some of the plants which are Hindalco plants, they use huge electrolytic pots which consume almost 300 plus kiloampere current. So more current, electricity intensity produces aluminum at a much more efficient manner. Even the older technologies which are still in India, like we have got some of the plants which are running at below 100 kiloampere, those pots also through their continuous improvement project and all, they have also reduced their power consumption. So there is overall a great reduction in the power consumption and the carbon footprint. The main challenge in India is that our power is coming from burning coal. And that's why when we compare different regions in the world, there are some of the Canadian smelters and all, they use hydroelectricity, their carbon footprint is very low, whereas Middle East factories like Bahrain, Dubai, Qatar and all, it is medium because they use natural gas, and India and China, it is the highest, almost 17 to 18 ton of carbon dioxide per ton of aluminium. I think that is a brief starting point.
Thank you, Bebu. Thanks a lot. I think, can the organizer be connected to Naveen, please? Is he connected? Or can you try to connect? If it's not done, we'll continue with these three. Okay. I think there is some power cut, I think, after that. Now, I think to continue with Bibab, I think now Bibu has given, you can continue from your perspective of your industry as a whole.
So as you know, this aluminium itself is by nature is an energy intensive industry. So over the years, many improvement has taken place. We started with 16,000-17,000 per ton of aluminium. To now we are in the tune of 13,000 to 13,500 tons kilowatt hour per ton of aluminium. So many technological intervention has taken place because mainly power is coal based, and the coal has a limit. It's a natural resource. So to meet our commitment to get out of this zero carbon emission, so the industries and we are also progressing in the same way to conserve energy. So there are ways to conserve. As I said, one way is to adopt cleaner technology. That means with the higher amperage technologies where you get more output and they are more energy efficient. So that's one way to do it. Another way is to go more towards the renewable one. So that's it's a cleaner metal, I think, to produce green metal. So that has also now is moving, but at a slow rate, close to 10 to 15% of only power is available in the green form. Third way, I can say, is more of a adoption of a modern way. I mean, in the digital and AI era. So now more efficient process can also lead to better energy efficiency and better productivity. So that's another way where we are working on to bring in more automation in the process control part, where with the available technology, we can run our smelter in an efficient way. So that's a call, maybe in the smelter world, it is called digital twin and some more AI-enabled processes. So these are the area where we are working to reduce our energy consumptions. And though in smelter is not just electrical energy, other than electrical energy, we use many fuel also. So now the fuel, from fuel to the gas. So natural gas is the way to adopt a cleaner technology. So we are also working to switch from oil to gas, because HFO or LSHS, again, it leads to environment pollutions. So we also improving our processes to adopt that cleaner way to produce aluminium. And the way we are doing and the scaling up the process, I'm sure the things and the metal which we will be producing will be more cleaner. And as I said, there may technology evaluation is going on. So it's just your focus and commitment is required, dedicated innovation, and the R&D has to continue in this area. So these are the things which will ultimately lead to zero carbon footprint, because this will not happen in 1 day or 2 days. It will take some time. So, but unless we take a step now, I think that we do have a plan to go to 2050, we may reach to carbon zero emission, but the steps have to be taken now. So this way we are moving, and of course, it's a long way to go, but the way we are doing, I think we are on the right track.
Okay.
Thank you.
Thank you, Vibhav. I think if Naveen is connected, yeah. Hi, Naveen, are you able to listen to us? You are in mute.
Sir, I'm able to hear you, sir. Are you able to hear me?
Are you able to hear us?
Yes. I'm able to hear you, sir. Are you able to hear me?
You are able to hear. Okay. I think probably missed now that you are in the VC mode. My first question to all panelists was that what is the present scenario in your industry, that's where you have been involved in steel for a long time, about the energy scenario in your industry in terms of the consumptions, in terms of the reductions, in terms of the process efficiency and other measures that you people are taking to reduce it. So your views on this, please. Yeah, Naveen.
Yes, sir. Thank you so much for the question, sir. And I'm sorry that I could not join the event physically.
That's fine.
So basically, where we are focusing right now, energy efficiency is one of the key lever or driver. For reducing the carbon footprint, that our industry comes under hard to abate sector, and now the CCTS draft norms have been already, notified, and after 60 days of consultation, it will be actually, notified, and it is a clear target. The clear target is close to 3% annual on year-on-year basis. We have to reduce our, carbon footprint. So it is a very good platform where the good behavior will be rewarded and the bad behavior will be punished. Meaning the good behavior, if we are able to reduce our carbon intensity, we are able to generate carbon credits. And the bad behavior, if they are not able to really do anything, they have to buy the carbon credits from the market. So there is definitely a knock on the bottom line and on the top line as well. So in our industry at Jindal Steel Limited, where exactly we are focusing right now, it is about the energy efficiency. So what is driving the energy efficiency? It is about making our blast furnaces smarter, using variable frequency drive to reduce the carbon, to reduce the energy efficiency, using smart motors, the blast furnaces, all the flue gases or the waste gases coming out from our blast furnace, from our basic oxygen furnace, from the coke oven, they have been actually utilized. Gone are the days when all these gases were used to use as a fuel. I think there is a better value that we can derive from, especially from the coke oven gas, which has got a very good hydrogen content close to 65% and a very good calorific value. So instead of using this gas as a fuel, we are going to use this gas as we are actually using this gas as a reductant. So first time in the world, that we are running world's only coal gasification based DRI plant in Angul, Odisha. And we are gasifying coal using our Swadesi coal, gasifying coal using synthesis gas into our vertical shaft furnace. So first time in the world, we have introduced this coke oven gas directly into the DRI furnace. So this actually helped to reduce our cost, and it is actually also helping us to lower down the cost as well. When we talk about the per ton of DRI, and it is actually the reduction process in the shaft furnace. It has also gone, very good because of the presence of more hydrogen. Along with this, we have also, what we tried, we have introduced the basic oxygen furnace gas because it is high on carbon monoxide. Close to 65% carbon monoxide is there in this gas. We introduced this gas into the DRI furnace and we have got a very good result. So this is how I think going forward, this is a path that whatever the low-hanging fruits, quick wins are there, especially for our hard-to-abate sector like steel, aluminium, cement, power, petrochemical, chemicals. These are the energy efficiency is the one that is going to drive the thing. That is one. Second, the use of the renewable energy. Now, this is actually, especially in India, it has actually reached to that to a very mature phase right now. And I am pleased to inform you that we are right now in a process of commissioning 1.5 gigawatt of solar power in Bikaner, Rajasthan. The power is going to come and power our steel operation in Angul, Odisha, and in Chhattisgarh, basically in Raigad, Chhattisgarh. So both the plants are going to get this renewable power. And by end of this year, we are going to commission 700 megawatt of wind power in Karnataka and Tamil Nadu. And by end of next year, we are going to double the wind power from 700 megawatt to 1.5 gigawatt. So I think these are the levers, and it is not that this renewable power, now it will actually help us to reduce the carbon intensity. And on top of this, this is actually it is a business. We will be in the money. We are going to save money. The power coming out from the thermal power plant is costing us close to 5 to 6 rupees per kilowatt hour. And the power that is going to come from solar and wind combined, it is going to cost us close to 3 rupees 50 paise. So close to half, right? So it will help in both the ways, reducing our cost and also helping us to reduce the carbon intensity. And this is exactly what CCTS is going to drive this behavior. So these are the initial remarks, sir, from my side on the energy efficiency, on the renewable energy. As we move forward into the process, I will try to maybe explain more.
Thank you, Naveen. I think you've already covered part of renewable. Exactly, to all my panelists and also to the audience, you know, we in the steel industry, in the aluminum industry, and that to a process industry like cement, I think BIVA has worked for some years in cement industries. The operational man, operational in charge or CEO of that plant always looks for the methodology to reduce the energy consumptions. There are plenty of ways. Over a period of time, as I said, 60% of reduction has already come to us in the energy consumption per ton of crude steel. It has just come, not like something. It is over a period of research, period of use of those research findings, and over a period of technological terms. Biggest is the technology one. But having said that, it's a energy intensive industries. What should we do? Should we stop it just to see that our carbon dioxide, it doesn't affect so much like that? It's not possible because steel and aluminum are two prime metals you cannot stop. So what to do next? Whenever there is a limitation to come to a reduction of energy in plenty of ways by which every panelist explained to you. Next way is how to do that. My energy that I get it can be transformed in terms of a form. That exactly as Naveen has already explained in terms of a renewable. Renewable can be, times of solar, wind, and the hydro, and of course now I think Dr. Batra was saying about, we're talking about something about nuclear and other way of energy like biomass, etc. But there is another the part of it is in a biomass. We are talking about biochar. So on this front, now that Naveen has already explained, can I talk to one more answer from Bibhu regarding the renewable part of it in the aluminum industry? Because we sometimes, I know a lot of things have been discussed about green steel part of it. When you talk about green steel, you understand that whatever the carbon dioxide per ton of crude steel has to be reduced because of late the Ministry of Steel has defined what is in my green steel. So they call it a green steel taxonomy, where they've designed 5-star, 4-star, and 3-star ratings. So similarly, I also want to understand from aluminum side what they have been doing in the aluminum industries from people.
Okay, I think the aluminum industry, because it's globally they decided, and in fact it is very well aligned with the technological requirement and all, that recycling is to be in recycling you use very little electricity or very little power. So when I talked about all these big numbers, 12,000 units of power and all, So only 5% of that you need for recycling of aluminum. And aluminum being a scrap aluminum recycling is a big business. So any recycling is considered as green. And that's why you will find that in the recent years, all the big aluminum players globally, whether it is Dubal, Alcan, Alcoa, even Hindalco, all of them are going big on recycling. In fact, one of the plants which we are building in USA, and that is one of the largest Indian investment in USA, is a 6 billion ton recycling plant in America we are building now as a part of Novelis. So recycling is going in a big way. Of course, the technology has also improved. The way you distinguish different alloys and all, that is one big thing which is happening. Second thing which, as a company we have done, the concept is not new, but many companies, they don't deploy it. When I was heading the manufacturing of Hindalco around from 2017-18, we started deploying it. It is called the internal carbon price. You decide what is the cost of carbon dioxide as a company. Don't wait for the outside world to tell you. So at that time, with a lot of with experts and all, we decided at that time that the internal carbon price was almost $22 per ton of carbon dioxide. So now if I have got two technologies and I am going to do the capex, so ultimately in the capex calculation, I will come to the net present value of the technology and then we will decide what to take. So there, if there is a carbon, because of this internal carbon price, the net present value of any green technology used to come to be cheaper. So that's why from 2016-17, we were one of the leaders. I think we were the first company globally in Odisha, in Lapanga, Sambalpur. We did a 50 megawatt solar power plant. Now, of course, the solar power cost has come down and all, it is no-brainer. But that time, the cost was still higher, but we implemented. And whole Hindalco, I think close to 300 megawatt we are producing in different units. And in this same spirit, now, when it comes to reducing the carbon footprint by going for natural gas and all, many of those places, we have got the dual-fired furnaces, the whole system to use the natural gas. So when the natural gas price was low, that time we were using, of course now this scene has changed. So like that, many of the innovations can be done and they can be deployed in the aluminum industries.
Thank you very much. I think both Vishwaranjan and Vivo, are you going to add some points on this renewable part of it? Oh, it's okay. Vivo?
Yeah, I think in this process, I think the waste heat recovery is another area where smelter is working on, particularly in the ABF. And we do get many hot gases. Now we are working on to how to utilize that heat, so which will ultimately help us in reducing my energy consumption. Also, the value recovery from the dross, because that is also it's again it has become an industry, industry within industry, I should say, which will ultimately give you a green metal, because you get alumina. Otherwise, it was just going as a no value material. So now we are getting value out of wealth. At the same time, the aluminum or the metal which we are producing is of completely free with energy. So these are the additional ways where we are working on, other than what Vipul said. So of course, but there are, many ways to go. So I'm sure we will again work upon that.
Yeah, thank you very much. I think my next question to Naveen, the steel industry and you are in steel industry, I'm talking about the metal industry as a whole has an ecosystem. It doesn't end with making steel just like that. It comes from iron ore, from our bauxites. It has a process by which agglomeration, it has got alumina, then you go to aluminum, then you go to steel, then you go to rolling mill, then go to rolling mill. It's a system which takes care of this. In everywhere, we are just discussing over a period of time, it's 45 minutes or 50 minutes, to only point out those focus points which needs to be, to be understood properly. For example, we are now talking about a basic, Naveen, as a basic reductant, we are using coke in the blast furnace in a BF route. Okay. And similarly, right now the time has come to use hydrogen as a part of a reductant, also as an energy. Coke was not only giving a reductant, it's also giving a lot of energy. So in this manner, we are talking about, because the best way to produce steel today, anywhere in the world, people tell it, go through a DRI, EAF route of making steel instead of BF, BOF, where you will reduce the steel and you use those energy from renewable power. But could you believe it, today when you're talking about 1850 million ton of steels, 960 China and 160 in India, and majority of our production is blast furnace BF route, 70% to 75% still BF route, where the carbon emission will be more. Now, as you said, rightly Naveen has said earlier, there are blast furnace design also being changed, the way things are happening. We want to reduce the same BF route to 70% of the steel consumption in the world are being reduced from a level of, when we're talking about 2.5, 2.6 in Indian average, we are now aiming for 1.8. And there are world industries in same route has achieved almost 1.4. So that's what I'm talking about, a lot of things happening. So having said that, have you, from your Jindal perspective, and also to a private sector, to that extent, what that you are going to do from your sustainability, Naveen, please.
Thank you so much, sir, for the question, and very pertinent question, because there is a saying in English that what got us here won't take us there. So there has to be some incremental steps if we have to reduce the carbon intensity. And as you have rightly said, the green steel taxonomy have been already issued by Ministry of Steel, and there is a 3-star, 4-star, 5-star category. When we talk about the 3-star, the carbon intensity has to be 2.2 tons of CO2 per ton of finished steel, and if it has to be 4-star, it has to be between 2 to 1.6 to 2, and 5-star is less than 1.6. And 5-star, achieving 5-star, you have to do a massive heavy lifting, and the heavy lifting we explained in our basically the initial questions. The heavy lifting in terms of energy efficiency, in terms of deployment of renewable energy, in terms of resource efficiency, in terms of getting the iron ore beneficiated and use those beneficiated iron ore, maximizing the use of pellets in the plant. So these are some of the quick levers which will help us to reduce our carbon intensity by close to 400 to 500 kilos of CO2. Now what next? The next lever has to be, sir, in terms of hydrogen and carbon capture utilization. So hydrogen, I think I'm pleased to inform you and panel and also the audience that we have injected hydrogen along with synthesis gas into the DRI plant. We have just commissioned the 5 megawatt electrolyzer. What we did, we were having this electrolyzer, we made green hydrogen, and then that hydrogen we injected along with the synthesis gas that is going into the DRI plant. And I'm pleased to inform you that the plant, this unit has been commissioned, and it is giving a very good initial responses. Example, in terms of per 5 megawatt of electrolyzer, we are able to derive 1200 normal meter cube per hour of hydrogen. The electricity consumption at the system level, not at the stack level, at the system level, we are getting close to 51 units as compared to 56 units that have been talked about. So the initial data is very, very good. And the phase 2, in next 1 month, we are going to order another 25 megawatt of electrolyzer. So all in all, on an annualized basis, we will be injecting 4,500 tons of hydrogen along with synthesis gas into the DRI plant. So this is the first step that we have done into the DRI. And the vertical shaft furnace that we are using in Angul, I'm pleased to tell you that up to 30% of hydrogen we can inject along with synthetic gas without changing the infrastructure of the furnace. So meaning up to 200 megawatt of electrolyzer we can just add on without changing the overall anatomy, without changing the infrastructure of the furnace. So this is what we are going to do basically in Angul. The second incremental step that we done in Angul, first time in the world, is to use this synthesis gas into the blast furnace. So I'm pleased to inform you that we have injected 5,000 normal meter cube per hour of synthesis gas into the blast furnace, and the idea is to see the impact of this gas on the reduction of the PCI. You know that in PCI, the big blast furnaces, any number between 170 to 180 odd kilos of PCI per ton of hot metal. And we believe that with the injection of this synthesis gas, we will be able to reduce our PCI by close to 10 to 15%, and thereby the equivalent carbon reduction across the blast furnace. So these are the incremental steps that we have done. And so far as the hydrogen is concerned, I think it is absolutely going to not the only silver bullet, but I think this is going to be one of the important levers as we move forward. And along with this, I think the carbon capture utilization is also one of the strategy where hydrogen has an important role to play, because whether we make ethanol, whether we make methanol and sustainable aviation fuel, whatever chemicals we are going to make, hydrogen is the main building block if we have to go for a low carbon emission or a green chemicals as we move forward.
Yeah, thank you. I think all my panelists have deliberated on the reduction part of it. Deliberation also was done about the the change of form or the diversification of the energy form. And the third point is mentioned about hydrogen. But let me tell you another most important point of when you're talking about this journey from reduction of energy and where you reduce the cost also. Then the form of energy from one form to other form, that from coal form to renewables and others. And third is most important, which is very vital, which is basically an interaction between the industry as such and also with the government and also with many of the R&D and academia that INAE is also doing out, where we form this transition path. We do not call it the energy transformed. We always call it energy transitions. That means a part of energy being transitioned. Just how talking about there are some coal-based power, there will be some renewable, integrated out, again small transitions. So over a period of time, you follow this path of journey by which your renewable powers. So I'll ask Vishwaranjan, are you having that point of view for your transition journey in Steel Authority or in your factory?
Hello. One thing is confirmed कि स्टील बनाना है तो एनर्जी तो लगेगा. तो two ways out. One is to reduce the energy consumption, and another one is जो conventional energies, जो basically steel बनाने के लिए the main source is fossil fuel, that is coke. तो एक तो हमने डिफरेंट बेस्ट अवेलेबल टेक्नोलॉजी लाने के बाद में वी विल बी रिड्यूसिंग द एनर्जी रिक्वायरमेंट्स, दैट इज स्पेसिफिक एनर्जी कंजम्पशंस, दैट इज वन एस्पेक्ट. सेकेंड एस्पेक्ट इज हाउ टू रिड्यूस द फॉसिल फ्यूल कंजम्पशंस. जैसे अभी महंती साहब ने बोले कि अभी हम लोग ने इन सेल द आउट ऑफ टू अल्टरनेट एनर्जीज, रिन्यूएबल एनर्जी, दैट इज वन इज सोलर, वन इज विंड. We are going towards solar. In our plan, in around 27, 28, 28, 29, in entire sale, our plan for different units, we have got Bokaro, Durgapur, Banpur, Bhilai, totality around 300 megawatts. We have planned different units. Those will be coming in 27, 28, 28, 29, especially in RSP, Route Class Steel Plants. Presently, one small hydroelectricity project that is coming, most probably in February 27, 10 megawatts. And another one, that is Mandira Dam, there is a dam there, that RSP, Mandira Dam, 100 megawatt floating solar plant. In collaboration with NSPCL, already clearance has been given, we have given the go-ahead. That is coming at RSP. Apart from these things, a lot of initiatives we are taking on war footings, especially different school buildings, different offices, rooftop solar panels installations. तो सेल में सर ये सोलर की यूनिट को छोड़ के बाकी में और कोई डाइवर्सिफिकेशंस में नहीं है. ओनली अनदर थिंग इज अभी हमारा जो कोजन गैसेस है उसका एक्सटेंसिव यूज़ हम लोग अभी कर रहे हैं. इवन हमारा जो कैप्टिव पावर प्लांट्स है, देयर वी आर यूजिंग ब्लास्ट फर्नेस गैस एंड वी हैव स्टॉप्ड कंप्लीटली कोल. देन इन केस ऑफ in special there we have got 260 megawatt units. Now we'll be diverting our BF gas to one of the units of 60 megawatts. They will now be converting that to also to gas fed. Even in our calcination plants, we are going for mixed gas for 2 kilns. So in this way also, we'll be able to reduce the fossil fuel consumption totality.
Thank you, Mr. Rajan. I think as we are going to, toward the end of our discussion, I think what my panelists and also Naveen there on the BC have explained that, everybody is in the journey of renewable integration to a great extent. The company that I represent, I am the CEO and Managing Director of the Metal Mining Division of SR in the country. And I can tell you this, we call it SR Energy Transition. A department has been opened, EET is a separate division of the company, where we want that every division, that every verticals, business verticals of the company, whether it is the infrastructure, whether it is a metal mining, whether it is energy, or whether it is the project and technology, every department or every vertical has to transform the type of energy he is using to other. For example, we have a technology division which is almost 2 billion turnover. Black box, if you can Google it, find out, one of the topmost the IT industry in the world, where they are opening up GCC. Anybody who talk about global capability center and also the cloud center, the amount of energy they consume, probably must have discussed during these 2 days, as probably we sometimes do not hear in our big industry like steel. You'll be surprised to know the consumption of energy on the GCC, also cloud computing centers, and also the cooling water required, and for cooling water to pump also the power generator is huge. So basically, we as a company have taken a decision. Similarly, other companies who are also with panelists me have to take a call that yes, we need to go towards energy transition. We are energy intensive industries. So we need to find out what exactly, in which way our energy has to be formed, to be transited from a environmental intensive damaging or carbon intensive intensify to come to a much lower part of a greening part of it. So having said that, I think we'll look forward a few questions from the audience so that you'll be able to take a view of entire the mass that you are available here, intellectual mass. So we can able to take a question from you, and you can always point out from whom you want to answer from our panelists, whether it's Bibhu, Naveen, Vishwaranjan, and also Vivek. I'll request that one. So few more questions. I think after that I can have a closing and then we'll end it. Okay? I think, yeah, please. Give them I think Dr. Bhaskar is from Tata Steel. I think we can give the microphone, please.
Yeah, thank you for a very engaging discussion. I think whatever you have mentioned, whichever ways and means of reducing the carbon footprint and the energy intensity, I think these are all being tried out by various steel plants. Just a few points, I mean, it's for all the panelists. One area of, energy is the slag volume. In the steel plants, that's a huge source of, energy, and we also granulate that. And then that energy is lost actually. Both the blast furnace slag as well as the, the EAF slag. So any plans or any ideas of how to capture this energy from slag, the heat energy from slag. The second is the radiation losses. If you see the steel plant, various sections you have radiation losses which keep happening, and these are huge and often not captured. And this is actually a waste of energy. So have you thought about it? And the third point which the JSL gentleman was mentioning, Mr. Alawat, was, yes, this blast furnace top gas. Actually, this Hisarna technology, which we have actually developed in Netherlands, we are trying to commercialize it. And this is already, a pilot plant is already there in operation, where we're actually this syngas, from the top blast furnace gas, this is being injected into the TUS, and there is also some plasma heating also being planned. This seems to be a very promising technology for this. And coming back to this DRI, and gas-based DRI unfortunately has not really taken off in the country because of various, various factors, including the policies and the pricing of gas and so on and so forth. Otherwise, for us, it should have been a very good technology, considering that we can produce, actually, we are the largest producer of DRI, but unfortunately, it is all coal-based. So it's not green, and also the effectiveness reduces because of the carbon content. When you use it, the gas-based DRI actually gives you carbon, which helps in the further, the process. So the less carbon actually is a disincentive for using coal-based, apart from the green part. So what are your thoughts on these few things?
Yeah, Dr.
Thanks.
Bhaskar, I think you should have been panelist here. I would. So taking into consideration of your thought process is very vast. You have asked 4 very clear questions. How do I capture my radiant heat losses? Number 1. How do I my heat loss which go for slag, which I utilize after slag granulation, then go to cement plant and sell it out in a slag cements. And how do I, basically talk about this sponge DRI natural gas being not there. So I think these are all something I believe, heat capturing, or you can say waste heat capturing, all the things. I think, Naveen, you want to say something before?
Yes, sir. Just want to add what Bhaskar ji has just asked. I think starting from his 4th question first, I think he rightly said, I think the gas base in India, out of 160 million ton, 55 million ton of the steel is being produced from the sponge iron.
But let me tell you, just hold on there. SR was the first company in the country itself. They utilized the entire 6 DRI furnace way back in 90s to produce steel in gas base in a steel plant. I mean, nobody thought up always very sponge iron. Go ahead, Naveen.
Yes, sir. Rightly said. So I think, sir, this coal gasification definitely, is a partial answer. I'm not saying that it is the only answer, but since where we are importing 55% of our natural gas requirement, and that is where the issue is. The imported landed price of natural gas is close to $14 to $15 per MMBTU, and that is where it make the DRI quite expensive as compared to the DRI being produced into the Middle East, where the gas is close to $2.5 to $3 per MMBTU. In that regard, I think coal gasification can be a potential answer. So, like the plant that we are running in Angul, our cost of syngas is almost half as compared to the natural gas, and that can bring down the cost quite significantly. So that is one. But along with this, I think when we talk about the major upside of reduction in the carbon intensity, this route of gasification, gas-based DRI, there are 2-3 things which are very important when we talk about the future decarbonization. In BF and BF route, you have only few levers to decarbonize. You don't, you can use renewable power, you can use energy efficiency, and after that, the incremental steps become very, very difficult. But in case of gas-based DRI plant, the upside is quite huge. Meaning, if we use renewable energy instead of basically using the energy from the grid, you can straightway reduce the carbon intensity by 700 kilos. That is one. Number 2, you can also use hydrogen basically along with the synthesis gas, so that will also help you to reduce the carbon intensity. So upside is quite huge. So that is where I think I was just want to add that the gasification coupled with carbon capture utilization is definitely a potential solution for our condition in India, and where we have got a huge coal reserve. We have got close to 350 billion tons of coal reserve. So I think it is better we monetize and valorize and use these reserves before the carbon tax becomes so prominent that this coal will remain within our mother earth.
Thank you, Naveen. I think Dr. Bhaskar's question coming up. First of all, the lost heat for the slag granulations and also the radiant radiation, whether it's a slab rolling, whether it's a hot roll coil rolling, all the things, we are not able to still capture it. What we have done is basically over a period of time. Right now, the conventional hot rolling process has been replaced by casting and rolling. Earlier, you were talking about TSCR, thin slab rolling. Now, we are talking about casting and rolling. What they do that, you cast it out, You don't go to a slab here to cool down your slab, you can put in the reheating furnace. Again, to go through a tunnel furnace, whatever temperature you lose, you reheat those tunnel furnace and go on continuing this to your roughing stand. Then after roughing stand also, I'm telling you for flat, it can be also semi-long because you worked in both. Also another tunnel furnace so that you do not lose heat. So what you do it out, this we are trying to regenerate the heat in terms of a form of a change of technology. So this is what I think a process. But as on today, as I said, 70% of the steel are being produced still a conventional way. We are still going to research how that waste heat or heat not being recovered or not being captured can be done, number one. Number two is basically, you asked about the gas part of it and hydrogen part of it. And Bibu was asking us, Dr. Bhaskar, that what is the result of those, this what Naveen was telling, injecting hydrogen in some 2 years in the blast furnace in the Tata Steel. So I think there was an experiment which you did it out. And also Tata Steel has gone out a small, a small size of carbon capture system, for which we are now talking, designing. I think these are all something I believe, for me, it's like a nascent stage of going off. We are, he has asked for 300 megawatt of renewable power, and Bibu has explained, and I think Vedanta is also going in a big way of renewable. But these are all minuscule in the type of energy that we use, complete. And that is exactly talking about a huge amount of interactive for power in our industry, how the form of power can come. Number two is your question coming up, how to capture those waste heat which is going on this form of slag and etc. I still believe that some research and some way of doing it out, but I only gave a small example of how a type of change of technology can able to save this type of loss from the radiations. So I think you have anything to add? Yeah, I think anybody can just be a microphone there itself. Don't have to bring it here back. I think. Yeah, you had a question, please. I think before that come. Okay.
Yeah. Thank you for this engaging discussion.
So, आपका introduction थोड़ा.
Yeah. I am Ashish Savarkar, Associate Professor, Department of Chemical Engineering, Motilal Nehru National Institute of Technology, Allahabad, Prayagraj. And our research group is working in the area of gasification of biomass as well as coke, as well as petroleum coke, which is a petroleum refinery byproduct. At the same time, we are also trying various combinations of these three and trying out checking out the quality of syngas. So my question is to Naveen-ji, who has just said that they have tried injecting syngas as well as hydrogen in the blast furnace. So we are producing a lot of biochar through pyrolysis process as well, through sheer agricultural crop residues, as well as through sewage sludge. So whether any experimental analysis has been done regarding biochar being used in place of coke, and secondly, what was the difference between hydrogen being fed individually, not in tandem with syngas, as far as the blast furnace is concerned?
Naveen.
Yes, sir. So to your first question, Professor, thanks for the question. So we have used bio-coal or biochar in our coal gasification plant. We use it along with the coal that is coming out from our own captive mines. So there we are able to see very good result in terms of the overall thermal efficiency, cold gas efficiency, and we are able to reduce the coal consumption by almost 2 to 3%. We ran this experiment for close to a week along with Indian Institute of Science, Bangalore, IIC Bangalore. The only downside here is the economics. The cost of the landed price of the biochar is coming close to $100 odd per ton versus the coal close to $40 odd per ton of the coal that we actually get from our mine. So 2.5 times higher, that is the only upside, so that we have to sort of see how we can optimize it, number one. Number two, in terms of the using the biochar, biocoal in our blast furnace, so I'm pleased to inform you that we are using that experiment right now as we speak in our Raigad plant, where we have got a very small blast furnace of 600 meter cube. So maybe I'll be able to share with you the details in next 2 weeks when we complete this experiment. Okay. Coming to your first question about the biochar. Yeah, sorry. If you can just repeat your first question, please.
Hydrogen and synthesis gas together, did you separately? What has been the result so far? Combined together or separately?
Yes, sir. So when we used the hydrogen basically on a standalone basis in the blast furnace, we are able to inject close to 7 to 8 kilos of hydrogen per ton of hot metal, only up to that level. As per the theoretical calculation, we can go up to 15 odd kilos, but we were able to go only 7 to 8 kilos. So that is our experience. When we inject the same hydrogen into the DRI plant, we were able to go up to 550 normal meter cube, which is almost equivalent to the synthesis gas. So I think these are the results, and I'm pleased to inform you that when we put the hydrogen into the DRI plant, the overall reaction rate goes very fast because of the lightness of the gas, because of the reaction rate goes almost double as compared to the synthesis gas. So we got very good result in the hydrogen. Same way, we are going to amplify now. What we are going to do, the syngas, we are going to put up a PSA, and we are going to put a high amplified normal meter cube per hour of hydrogen into the blast furnace. So that way we'll be able to really see that by putting it into the tours, what is the overall impact in the PCI. Right now, the PCI impact that we are able to see by injecting syngas is close to 5 to 6% reduction. But as per our calculation, it should go up to 15%. And that is the experiment where we are busy right now.
Okay, thank you. You want to add?
One thing I also want to add, regarding biochar, we have also in the Rourkela steel plant, we have also tried in our blast furnace. But two obstacles are there. One is just now, sir told regarding cost. As compared to pulverized coal, that cost is almost 2 times. And another one is availability. हमने तो वहाँ पे trial कर लिया है, तो that will replace replacement ratio as compared to pulverized coal, almost 1:1. But these two factors are not at all encouraging. One is cost factor, one is availability. Future is there, but we have also tried 1 year, 2 years back, but again, we stopped only because of availability.
I think we'll take a last question, Bhaskar, please.
Yeah, this is not a question, just to continuation of what I mentioned. Yes, biochar we also tried, and the main challenge is the availability and also the creation of this ecosystem. I mean, you need to create this ecosystem. Just by trials will not prove anything, number one. Number two, this carbon capture, we have had a pilot plant there, and we can capture up to 5 tons per day. You know, through metal oxide technology, a metal carbonate is formed, but again the challenge is the utilization. Even if you capture 5 tons over a period of a year, you would be capturing thousands of tons. So viable use of this, you know, the captured carbon. We are in discussions with various agencies. One obvious solution could be the ethanol, you know, convert into ethanol and then as a fuel in vehicles, but then it's still, some more work has to be done on that. And coming back to hydrogen, yes, you are right. We could also inject up to 5 to 6 kg, you know, replacement. But then the ecosystem again is an issue. Because we realize that gaseous hydrogen, you know, it requires huge volumes. And in a steel plant where already there are space constraints and there are legacy issues, to create the infrastructure of these hydrogen ecosystem itself would be a challenge. Forget the cost. The very logistics of creating this would be huge. And we need to think about it because liquefaction is not a solution. That would make it even more expensive. So these are some of the practical challenges and as we go on this decarbonization journey. And collectively, I think we'll have to address these challenges.
Yeah.
And we need to collaborate actually to solve these issues.
Yeah, thank you, Dr. Bhaskar. I think we are coming to close our paneling. You have a point? Yeah, I think, can microphone given to Dr. Acharya, please? Sir, आप बैठ के बोलिए ना. You sit down and talk.
No, it's okay. First of all, I must admit I am not a metallurgist or anything, or not a chemical engineer. I am not an expert in that type of thing. But one thing actually which comes to my mind, maybe I am wrong, that is this both aluminum and steel that you were talking of, and including the GCC centers that you are talking of, they are highly energy intensive. And what is required is actually there that you have to have continuous availability of the energy. Okay? I think the option that will be the best suited in today's context, in my view, is that actually you should go for having nuclear power plants. And now, this something up to say 600 megawatt of capacity in nuclear power plants, smaller ones, they are easily available and it can be done within the country. Now, the renewable part that which you are saying, that we will have actually solar, these things. Solar actually, the availability is actually, night you don't get it. Either you have to have a very heavy storage, which is very costly, or you have to give it to the grid. But that actually doesn't reduce actually the energy consumption. It only gets transformed to some other thing. And maybe you are actually gaining something in the daytime, that energy, that gain is there. But in the long term, to me it appears that actually nuclear will be the best option for all these energy intensive industries, and more so for aluminium and the global capability centers or data centers. I think we may think of something of that type.
Yeah, thank you, sir. You have now concluded our panel discussion with your wisdom. I think Dr. Patra is sitting about nuclear power plant. As I know, as far as the nuclear power is concerned, sir, I think I have been also talking to the Mr. Jindal, Mr. Satish Pai, who are the actually stalwarts of in the aluminium and steel industries. There are also discussion continuing with the government of India for the parliamentary. They have passed out a 200 megawatt to 400 megawatt of nuclear power. What do you call it? Modules. Yeah, that.
Sir,
Small
modular,
modular reactor.
I can. Maybe, sorry, I can just maybe add to this on the nuclear, because we are doing a lot of work on this, and on Friday itself we had a long discussion with Niti Aayog. So I'm pleased to inform you that at least at Jindal Nuclear Power Private Limited, it's 100% subsidiary of Jindal Steel, we have already shortlisted 3 sites in Odisha, in Andhra, and in Jharkhand, and we are going to put up the large modular reactor. So I think this monsoon we are hopeful that the Shanti Act, which was actually proposed and passed by Parliament, it will be notified. And once that is notified, then the license will start getting issued by Department of Atomic Energy, and private sector can participate and start putting up this nuclear power plant. So I think this is definitely one of the most efficient way as we move forward. And I think especially for the hard to abate sector and for data centers, emerging data centers, this is the possible and the only, I think, business case as we move forward.
Thank you, Naveen, and thank you very much, and thank you, audience, for a wonderful doing it out. I think we will not take much time. You must have 2 days in fatigue now, so we little bit wanted to infuse some of the enthusiasm in a big subject, which would take 2 days to completely understand and and assimilate about this type of thing. Anyway, with these words, I must thank every one of my panelists, Mr. Vibhav, Mr. Bibhu, and Vishwaranjan, and also Naveen, who have been able to participate, and also a lively audience like yours. Hopefully you would have given more time, would have given more justice. But anyway, thank you very much for giving an opportunity. That's all. Thank you very much. Thanks a lot.
Thank you, Mr.
Okay,
Mohanty.
thank you so much, sir. Namaskar, sir. Thank you.
And our esteemed panelists for a highly insightful and engaging discussion. May I request Professor Damodar Acharya, Chairman International Advisory Board of SOA University and Chairman INAE Bhubaneswar Chapter, to please come on the stage and felicitate our esteemed moderator and panelists. Thank you. Ladies and gentlemen, please note that the panel session featuring the paper presentation, poster presentation and startup display is being conducted at Convention Center. The paper presentation and poster presentation for chemical engineering is being conducted at second floor, and electronics and communication is being conducted at third floor at the Convention Center. After the panel session, we look forward to welcome you back at 5:30 p.m. at the auditorium, the same venue, for valedictory session. Thank you. करूँ? कुछ ऐसा नहीं है, बस एक announcement है. Do we have Dr. Neeraja Batala here? Yes, you are here. So. स्टूडेंट की लिस्ट दे दीजिए वॉलंटियर्स की।
स्टूडेंट 30 स्टूडेंट हैं। नहीं अभी 5-10 मिनट लगेंगे, जस्ट हम सेटल डाउन हो जाए।
अरे 5 मिनट आपको जो यूज़ कर रहे थे तो 5 मिनट।
हाँ वही मैंने आप इम्पोर्टेंट है सर, ऐसा नहीं। बस अब प्रेजेंटेशन ही दिखानी है ना, दिखा लेंगे हम लोग जब ये सीपू है कर लेगा, मैं भी कर लूँगा। सर थैंक यू, मेरा बात हुआ उनसे, बहुत खुश हुई सर। Kept that again new name plate or without name plate also we can सबके तो होगा ना, इधर नहीं होगा, मैं देखता हूँ।
स्लाइड दिखाना सर को, स्लाइड दिखाना अपना वैलिडिटी को लैपटॉप में देखिए, उसमें दिखाएंगे रिजल्ट भी। क्या है सर, जो इसमें 4 थे, लोग जो रह गए स्टार्टअप कर रह गए, अभी रह गए। She is one of the member who was not there. उनको अभी उनको बुलाएंगे। हाँ डाल के स्लाइड बना देते हैं, वो नहीं डाला बट हम और थोड़ा 2-4
told me, man, sir. He'll announce. Feedback. No. Then I think some people can speak. At least 3-4 people. Okay. Invite कर दीजिए, they will speak. I will tell you. हाँ. Right, you know. हमने agenda में रखी है. Man, sir, once we are able to. What time is your flight? What time to leave? 7:15. हाँ तो ठीक है, हमारा टाइम है. Flight is 7:15. नहीं. So what should do is that once ये अनाउंस हो जाएंगे ना, अभी एक जूरी वाला भी फेलिसिटेशन ऑफ जूरी है, उसके बाद you have to
SOA का जो भी वॉलंटियर्स जिन्होंने काम किया
उनको भी दिया जाएगा. वो भी है, जूरी है, बट उनको
भी है ना पूरा स्टीयरिंग जिसने
अच्छा उनको तो क्लास नंबर होगा. नहीं उनको नहीं दे रहे सर. उनको क्या हम प्लान कर रहे हैं, डिक्लेयर कर दीजिए. उनको हम हम क्या कर रहे हैं, उनसे लिस्ट मांग रहे हैं सर. हमारा सर्टिफिकेट दे देंगे बाद में.
So sequence is that first you have, I'll show you the program.
Vote of thanks के बाद मांगे, vote of thanks पहले मांगे.
This is the program.
बाद में तो vote of thanks the last
So
feedback
first the Mantri sir will have the address, then Damodar Acharya sir will have the address, then sir as the chief guest you will be addressing, and then we'll announcing the winners, and then we'll announcing the jury, we'll felicitating the jury members, then we'll felicitating the team of SOA.
No, need
Sir,
to.
we are not felicitating the students, but we are felicitating the teachers.
Oh, teacher.
There are 13-14 people only. So we are giving gifts from INAE. So we are.
They will take 25 seconds each.
Yes.
Scroll कर देंगे.
Right. And then vote of thanks.
No. Vote of thanks before just announce the
Feedback.
Some people can. I think that will
Feedback
complete.
of technology conclave, right?
That will completely complete the process.
Right. So should we start?
No. They have not arrived.
The program.
They will arrive 8 minutes. Just 5 minutes. उसके बाद एक स्लाइड और डाल दे, कॉपी कर. ठीक है बस. तो ये मीमांसा को डालते हैं. मीमांसा हाँ वो तो डालेंगे. हाँ डाल देंगे, आने तो दे. मेरे पास है ना ब्लैंक. ये ब्लैंक है. ये शानदार को दे दूँगा हाथ से लिख के. इसमें मैं साइड बनी हुई है ब्लैंक. लेकिन नहीं वो मीमांसा को दिखा पहले सीक्वेंस. मीमांसा सॉरी मुझे लगा नहीं बैठना नहीं. मीमांसा ये है. प्रेजेंटेशन मोड में जाएगा उसमें नहीं जाएगा. प्रेजेंटेशन मोड में नहीं जाएगा उसमें. प्ले कर. ये प्ले है ना. पर्सन ही नहीं मिल रहा मुझे तो. कुछ ऐसे देख ले रहा हूँ. ऊपर चलने इसलिए पहले चले ये वाली स्लाइड सही नहीं आ रहा. हैंग हो गया. आ गया. ये स्लाइड है इसमें.
हाँ ये सब है. ये देखिए नेक्स्ट.
सर ही बोलेंगे. सर ही बोलेंगे. ठीक है. नेक्स्ट ये पार्टीशन कर दिया. ये हो गया हमारा रजिस्ट्रेशन जो भी हमारे इन्वॉल्व है. ये सामंजस्य बोल देंगे. वो तो देन उसके बाद ये रहेगी नीचे बता राइट है. इसलिए वो लिस्ट है काम के लिए तो लिख लो. अरे स्लाइड डिस्प्ले होगी ना. इसको हम पहले रखें क्या? इसको पहले रखें हम. इसको करेंगे. उसके बाद एक फीडबैक है. किसी को विल रिक्वेस्ट somebody to come from the audience and tell your views about it and then शोभा सर को. ठीक है. यू आर क्लियर? फाइन. अब आयुष इंतजार नहीं कर रहे। बहुत लेट हो गया यार।
शिवा प्लीज हेल्प मी ना। शिवा शिवा क्या चाहिए? क्यों लगाना है? ये गिर जा रहा है। पास हो इसमें और इसमें एडवर्टाइजमेंट रिलेटेड टू मतलब AI एंड सेकंड जावा बट जावा का बेसिक खत्म होने के बाद उसका जो डेटा स्ट्रक्चर हाँ oops है DSL मतलब oops वाला DSL उसके बाद था लाइक डिस्ट्रिक्ट मैथ वो अभी थर्ड सेकंड सेमेस्टर में सेकंड सेमेस्टर में चल रहा है दो कंप्यूटर रिलेटेड टॉपिक्स हैं एंड वन तो डिस्ट्रिक्ट मैथ का आता है हाँ हाँ आया था वो ICT में था वो DA में था
जिसके अंदर आपका इलेक्ट्रॉनिक्स वायर डाटा स्ट्रक्चर्स
डेटा स्ट्रक्चर्स मतलब आप क्या क्या क्या
एक्सप्रेशंस हाउ एल्गोरिथम वर्क्स
अच्छा वो थर्ड ईयर सेकेंड ईयर से भी है उसका है एल्गोरिथम्स वही है सब्जेक्ट
BSc का डेटा स्ट्रक्चर
हाँ हाँ थर्ड ईयर से है आपका
HRA भी आएगा मैनेजमेंट टेक ऑफिस ग्लोबल बिजनेस
हाँ सर होगा बाकी
कोर्स नहीं पढ़ा करिकुलम
नहीं पढ़ा
मैं इसलिए हमारे टाइम में प्रोग्रामिंग लैंग्वेजेस कौन सी
जावा पाइथन सी
हमारे में C++ फोटरन को सुना भी नहीं
हाँ अब तो रस्ट थोड़ा बैंक यूएस पास करना है
बैकग्राउंड जो है ना उसकी बाइंडिंग जो है ना वो लूज हैवी नॉन स्ट्रक्चर्स नहीं है तो डाटा
जल्दी पूरा
रेट क्या होता है जैसे जो है लूजली लाइट लो क्या होता है जैसे अगर आपको 15 MB की फाइल ट्रांसफर करनी है पेन ड्राइव में तो इट विल टेक यू मोर देन हाफ एन आवर
छोटा छोटा हो जाएगा
फाइल जो है उसको
एक
हर एक फाइल को चेक करना आप 100 200 MB सिस्टम बना दीजिए उससे जल्दी
उसको जल्दी नहीं आया अभी
और मान उसमें किस पे जाओगे फील्ड में जाओगे आगे क्या प्रोसीड करना चाहिए बेसिक
हाँ सर इसके बाद करना है MSc का सोच रहे हैं टॉपिक नैनो टेक एंड AI
कंप्यूटर पर क्यों मन लगा लेकिन वो सीधे MSc बोलते हैं
हाँ MSc मतलब MSc करेंगे एक्चुअली आई वाज प्लानिंग फॉर IIT हैदराबाद एंड थोड़े मार्क्स से रह गया उसका लाइक 0.25 मार्क्स से उसका रह गया लाइक उसके लिए नहीं हो पाया बिकॉज मैं उस पर प्लान कर रहा था लाइक उसका एक ब्रांच है CSC एंड AI उसमें मैं प्लान कर रहा
नई ब्रांचेस भी हमारे लिए तो बताओ उनको है ना सैंडविच कोर्सेस
हाँ
सैंडविचिंग किसी को किसी के साथ इसमें क्या फ़ायदा है
बट
आपका भी रियल टाइम कर सकते हैं हमारा 1.5 साल तक कुछ ढंग का नहीं
हाँ
स्ट्रक्चर उसी में सब में स्ट्रक्चर में
वाले हाँ 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 तो कंस्ट्रक्टर्स बिल्ड करते हैं एक जावा का पूरा बेसिक्स कंप्लीट हो गया ठीक से मतलब अभी तो मैं सर वही जावा पे ही पढ़ रहा हूँ स्प्रिंग बोट मतलब बैक एंड जो संभालता है वो बैक एंड सीखना सर बट जावा इवॉल्विंग एवरी
बेटा सर बुलाए
मैसेज आ रहा है भेजूंगा IRCTC से मैसेज आया वो फ्लाइट के लिए उसमें फेयर भी लिखा हुआ था वो ठीक है मैसेज भेजो कर मैं बस निकाल रहा था वो करिकुलम मेरा मेरा ब्रांच व्हाट्सएप करना
टेक्नोलॉजी दिस इज वायुरक्षा दिस इज IRA ये दोनों स्टूडेंट स्टार्टअप है स्टार्टअप खोलना नहीं बीच ऐसे बोलना कि दिस इज जस्ट एन एनकरेजमेंट
I am not saying chief guest.
ओ यो ठीक
इसको कॉपी करके
ये स्लाइड नहीं मिलेगा अपने को, ये क्वेश्चन मार्क है, पूरा नहीं काट रहा मैं, हैं? सर्टिफिकेट किसे?
ये तो अभी कह रहे हैं कि अभी तो आया ही नहीं इसका रिजल्ट। पेपर इलेक्ट्रिकल
वो एक्चुअली उनका काफ़ी रिजल्ट नहीं था, तो मैं सोचा कि 9 पॉइंट और कम है और भी इससे ऊपर आ रहा है।
अभी तो आ रहा है। हो गया मैं शिवम का है ना, I'll ask him. He'll take.
ड्यूटी लगा दिया है।
Sir, name.
डॉक्टर रामानुज, एक मिनट, उनका नाम है डॉक्टर रामानुज ना, एक मिनट IMMT डायरेक्टर, what is the sequence?
Sir, like you'll be sitting in the center, the chief guest. First Damodar sir, then Samantri sir, then the chief guest, and
देखिए डॉक्टर रामानुज
Ramanuj.
नारायण,
Okay.
डायरेक्टर
ज़्यादा कुछ बोलने की जरूरत, डायरेक्टर IMMT, CSI और IMMT बोल देना बस, ठीक है?
ओके, ठीक, चलिए
कौन कौन होंगे बैचलर एंड
Damodar sir, Samantri sir,
कॉलोनी रॉय,
and then last one.
ज़्यादा लगा तो मुझे प्रेजेंट ही करना है, 5 एक निकल 5 5 5
sir, please take your seat.
A very good evening and a warm welcome to the valedictory session of INAE Technology Conclave 2026. Over the past 2 days, we have witnessed a remarkable exchange of ideas through inspiring plenary lectures, thought-provoking panel discussions, engaging technical sessions, paper and poster presentations, and vibrant interactions among distinguished academicians, industry leaders, policymakers, innovators, entrepreneurs, and students. As we gather for the valedictory session, we reflect with great satisfaction on the enriching deliberations and valuable insights that have emerged during the Technology Conclave 2026. It is my privilege to welcome the distinguished dignitaries who are who is also the chief guest of the session. Professor Damodar Acharya, FNAE Chairman, International Advisory Board, SOA University, and Chairman, INA Bhubaneswar Chapter. Professor S.R. Samantre, FNAE Dean, IIT Bhubaneswar, and Secretary, INA Bhubaneswar Chapter. Dr. Ramanuj Narayan, Director, CSIR IMMT, and Lieutenant Colonel Shobit Rai, retired Deputy Executive Director, Indian National Academy of Engineering. May we please have a huge round of applause for the dignitaries on the dais. With the dignitaries in place, we shall now commence the valedictory session. I now invite Secretary INA Bhubaneswar Chapter to present the brief report highlights.
Very good afternoon to all of you. So, the dignitaries on the dais and of the dais, all the delegates, participants in all the three verticals, the speakers in the keynote speakers and the panel discussion experts. You know, we have conceived this proposal of conducting this conclave just 3 months back. And this was really a Herculean task. How to really structure and how to really set the benchmark of this conclave. So fortunately, things happened in order, and that is how we are standing yesterday and today together and in this concluding session. So you might have seen we have designed this program with 3 major verticals. One is the panel discussions, keynotes in very emerging topics starting from the energy security, the healthcare technologies, then we have communications, we have critical minerals, we have energy intensive industries and discussions to go forward, and transport logistics. So all the keynotes and panel discussions were really up to a different grade, different mark. We have also learned many things. Yesterday while going through this logistics, transport logistics, I could not believe the way they have gone ahead. So this is the platform where the new knowledge dissemination really occurs, and that is what we have already witnessed. The second vertical is the startup. We got almost 40 startups, and I think that has gone to a very remarkable stage, which has been already witnessed by our people as well as appreciated by all our experts together. And really, what we discussed today also, this structure can go ahead with the next edition of this conclave. And the third vertical was regarding the paper publications and the paper and posters together, which really created a new knowledge dissemination platform. So considering all these three together, our conclave has really achieved a certain benchmark. Obviously, there is always a scope of improvement that we always accept and go ahead. I really thank many people, and at the last moment, Dr. Ramanuj joined us, the director IMMT, and we had the stalwarts like Professor Tiwari from IIM Bombay, Then we have many more experts from industries. Today, the last final panel discussions was only including industries. So I extremely thankful to all the people who have participated and created this kind of platform where the dissemination has gone to a very high grade. So this conclave, we believe it will take a different shape altogether in the next editions. And obviously we are part of all this. INAE is a very elite platform of this country. It's the only academy of engineering which serves the technology innovations as well as the policy recommendations for this country. This chapter is also, Bhubaneswar chapter is very active, and we are trying to connect even government for different policy recommendations, at least in the state to start with. Further, I will also request the INAE headquarters to bring, even if small, white paper on this conclave, which can really go and which can set the benchmark for the next event tomorrow. So thank you very much for your attention and involvement and participation in this conclave. Definitely we will meet in future in different editions. Thank you very much.
Thank you, Professor Samantre, for presenting a concise summary of the conclave. I now request Professor Damodar Acharya to address the gathering, please.
Very good evening to all distinguished persons on the dais and of the dais, plus all our actually startup friends and the paper presentators, INAE members, and the faculty and student of this university. So it is actually yesterday we are not very confident that whether actually the whole program will go in the nice way that actually that has been planned, because in the morning the inauguration session actually got delayed. One of the session actually we have to scrap. So, but in spite of that, in spite of that, the program actually went up well, and it has come to a conclusion now, and it is not actually this INAE Bhubaneswar chapter or the SOA University or IIT Bhubaneswar actually where we have done it. It is actually all of you who have made this particular program a memorable one and a successful one. I must actually thank all of you in doing this, and we look forward in the future editions it will be done in a much better way. Thank you very much.
Thank you, sir, for your inspiring remarks. May I request Dr. Ramanuj Narayanan, Director, CSIR MMT, to please give some words on conclave. Thank you.
Jai Jagannath, Jai Jagannath, Jai Jagannath. Very good evening to you all. On the dais, the Kulguru, our pathfinder, and the person who ordered me to be here, Professor Damodar Acharya sir. Another my guru and my senior from CSIR, Professor Shantanu Chaudhary sir, that he was the director of Siri Pilani, then IIT Jodhpur. Then my very new dear friend when I came to Bhubaneswar, Subhranshu Samantredi and Colonel Rai Sahab, that who was minding the show with all his military experience I was watching from last 3 hours. Another, our Guru and Pathfinder at IMMT, Professor Patra, all senior colleagues, young associates, that now this is not the time that you will be feeling to listen the lecture, so I will not lecture much, but I can tell that the moment I entered the startup show, the poster show, the enthusiasm of the participant, the type of paper you have, type of a stall you have, so it is a very well done efforts by our INAE, and always we can rock on. And then I was able to listen a wonderful lecture by none other than the originator of RE in India, Professor Patra. That was a great learning. And then we do have a panel discussion. Some of you might not have participated into that, but on a very important topic of decarbonization and that how greening is going to happen in future. But my only one thing, that INAE is dedicated the moment Professor Damodar Acharya sir and Subhranshu ji has taken over last 3 years. I have been associated with them, the type of program, the type of lectures, whatever is being carried out, that has been wonderful. And last to last year, we do have a very big conclave, and this year we are doing this conclave. So it's an initiative, and you know, Viksit Odisha 2036 and Viksit Bharat of CSIR President and Honorable Prime Minister, the line goes from Bhubaneswar. So this type of INA activity, the organization will be very, very beneficial in putting that. Any industry you see, any industrial growth you see, and engineers growth you see in the country, the type of institution which has come at this place, that will make a milestone in the future. So I will lecture later, but some I will do with some Sero Sairi, so that you can understand that young engineers should carry with them that whatever poster you presented, whatever lectures you have given, be brave, be bold. The core engineering day has come back, and whatever you do, do with an application, and India needs you. If India has to become Viksit, engineers has to make. I always tell to all my colleagues that if you are going for interdisciplinary education, chemists create molecules, physicists study molecule, biologists apply molecule, engineers fabricate molecule, and public enjoys molecule. So that is the whole molecules and material world, and where interdisciplinary, only one thing what we are not looking for, that the focus, the जिद, एक जिद होता है, वो जिद हमारे पास नहीं है. जिस दिन हम जिद्दी हो गए, जिद्दी थे, तब इतने बड़े बड़े आदमी हमारे आसन के ऊपर हैं, सामने बहुत सारे प्रोफेसर हैं. एक बार फिर से जिद ठानने की ज़रूरत है. तो रास्ते भी जिद्दी हैं, मंजिलें भी जिद्दी हैं. देखते हैं कल क्या होगा, हौसले भी जिद्दी हैं. सो हौसलों से उड़ान होती है. उड़ान तो भरनी है, चाहे कितनी बार गिरना पड़े. सपनों को पूरा करना है, चाहे खुद भी लड़ना पड़े. तो आप इंजीनियरिंग की लड़ाई में आगे बढ़ते जाएं कि इंजीनियर्स आर दी फ्यूचर ऑफ टुमारो, आर्किटेक्ट ऑफ टुमारो. मिले न मिले मंजिल, ये तो मुकद्दर की बात है. हम कोशिश भी न करें, ये तो गलत बात है. तो हम INAE के साथ और हम सब लोग मिलके, आप सब लोग मिलके एक साथ कोशिश करें. कोशिशें हमेशा कामयाब होती है. जिद ठाने कि हमें ये करना है. और उड़ीसा प्रदेश में किसी चीज़ की कमी, इट्स ए यूनिक स्टेट. यू गो फॉर फॉरेस्ट प्रोडक्ट, you go for mineral deposits, you go for sea resources. So the people tell that Kerala is the God's own country, and I always believe and I do understand Odisha is the God's blessed country. We need engineers to come together to fulfill the dream of Viksit Odisha. Jai Hind, Vande Utkal Janani.
Thank you so much, sir, for your inspiring remarks. It is now my honor to invite our chief guest, Professor Shantanu Chaudhary, Vice President INAE and Professor and Dean, School of Advanced Computing, Ashoka University, to kindly deliver the valedictory address.
Good evening. So we have come to the end of a very productive and interesting and exciting Technology Conclave, the second edition of Technology Conclave, which was held at Bhubaneswar. And in fact, very interestingly, what has been talked about is that the excitement of engineering, the adventure of engineering, and the challenge of creating new things is what engineers really pursue. And in that sense, I think the whole idea of organizing this conclave was actually to celebrate and look into all aspects of engineering, the way it can contribute to the progress of technology as well as society. One part of it is obviously the entire academic community. INAE is an academy of engineering. So its basic commitment to engineering, and therefore, when you look at the fellowship is being celebrated because of the excellence of achievements in terms of their work that has been done by individuals. But there is a process by which people achieve excellence. But people who are involved in the process, and it's a very important duty of the academy to bring them to the front and actually get them exposed to a multidisciplinary environment so that they get new ideas, new ways they can progress. And they should be also in a position to present their work to a bigger community. And this is also motivated by another objective, is that in the morning also Indranil had talked about, it's not 1,000 fellows, but INAE should have maybe 10,000 members, that's 1,000 into 10, who are actually representing the entire community. If that is so, then we should have a community platform. And therefore, this Technology Conclave has been conceived as a community platform. And in that community platform, who will participate? One part of it is academicians, they have participated. Other side is there are people from industry who have participated in variety of forums. And also at the same time, engineering also means a very thriving innovation ecosystem. So you had the startup forum. So if you look into it, therefore engineering community's engagement in terms of research being represented by academia across in all disciplines, the innovation by the startup group, as well as industry through various panel discussions, presentations, lectures. So all these three streams have come together. In that sense, this is a celebration of engineering and INAE's initiative for excellence in the entire domain of engineering. At the same time, we introduced this time the felicitation of members. INAE has started the scheme of members, and members have actually been recognized for their achievements and what they have done in their career and the significance of what work they have done. And they become part of the INAE family. And this event is actually in many ways is providing them an opportunity to come forward. And we are looking forward to have more members across the country. In fact, I would appeal to all the members who have become members today to get 10 more members. Each one of them should actually motivate others to join as members. And all others who are participating in the event should also actually take that message across that INAE is providing this forum. They should come forward and join, because This is a forum for having a research work being presented. This is a forum for startups showcasing their initiatives. This is a forum where industry, academia, and startups can come together and interact. So this kind of multi-dimensional, multidisciplinary forum really is not there in the country in the space of engineering. This is exactly the void which is intended to be filled by this event which INAE is organizing. It's important that I should actually acknowledge, I think, the guidance and the help that we have got. I think guidance is Professor Damodar Ajaria. I think he's unparalleled in terms of the way he actually welcomed our suggestion, guided us, got deeply involved into it, and made this happen in the scale which is unprecedented. So on behalf of INAE and myself, I express my gratitude, sir. Also, the faculty members of, I think, SOA, the support they provided, and I think it's not only today, it has been for a process for just 2 months. And in 2 months, it was talked about in 2 months, 2.5 months it was done. And the amount of effort that goes into making it happen is humongous. And it's very clear that the kind of a support which has come from the local ecosystem. And I would like to thank and express my gratitude to the entire faculty community of SOA and IIT Bhubaneswar and other institutions who are all involved, including IMMT, who is actually a kind of a sister organization. Once upon a time, I was part of CSIR. So how they have come forward and supported it is, I think, to be acknowledged in a big way. And it's important that to put across that, that this is not one-off event. This event will continue to happen every year. And so all the participants who have been part of it should keep their eyes open and actually look at these announcements and calls, and please participate in future editions as well. So I also thank all the delegates who have traveled from across the country and have attended this conference, attended this conclave in various roles. Also the students of SOA who were volunteers and who have actually participated in every organizational activity, and it has happened because of them. And therefore, it's also my duty to thank these university, the founders, the management, and decision makers in this university to come forward and provide all the facilities available to INAE. Now, I think I have a pleasant duty to make certain announcements. Announcements is, because as part of these, we had paper presentation by researchers across the country in multiple verticals. And there are also startups who have displayed their products. I think these startup displays and products are fantastic and really eye-opener the way they have worked and produced things. So there are certain, we would like to announce awards for them. And so let me first announce the prize for the startups, I think, which is important because startups need funding to grow forward. The startup prizes that we are now announced today is So prizes are, first prize is 25,000, second prize is 20,000, third prize is 15,000. At least that would be a small contribution, I think, for the growth of the company. And that's also is one of the things I think INAE would like to support, these young innovators. And now let me just announce the results of startup competition. First is FX UAV Technology Private Limited. Second is Vayu Raksha Kinetics Private Limited. Third is IRA. Are you here? Are participants here? Please stand up, please. Congratulations to all of you. We hope that you become unicorn in time to come in future. Okay, now let's come to the paper presentations. And we shall announce the best one in each of these sections. In civil engineering, it is presented is Mr. Neeraj Kumar from Neeraj Kumar from Tank to Ocean, World and Field Testing for Maritime Innovation. This is from DRDO. I would request Mr. Neeraj Kumar to come on stage and receive the memento. Is there? Okay, so maybe we can move forward. Then electrical engineering, Dr. Rudra Narayan Pradhan. It's the intelligent harvest, a multimodal AI approach using computer vision, fuzzy logic, and regression analysis from Odisha Institute of Technology and Research. Are you here? Yeah, they are not here. If their friends are there, they can collect. Okay. So, CS and IT engineering, Ms. Amrita Bose, mitigating denial of service attacks on legacy implantable cardiovascular defibrillators. Then we come to mechanical engineering. Is Dr. Indranil Aich, adoption of lean practice in restarting a paper mill with capacity enhancement and re-engineering of material flow. Is Aich appraisers and auctioneers and valuers. It's a company. Next one is Professor Gargi Das. Is she around? She might not be here. Energy efficient pipeline transportation of high viscous oil, a novel device to stabilize and re-establish core annular flow. She's from IIT Kharagpur. And electronics and instrumentation, Professor S. Indu, autonomous multi-robo triage for remote casualty localization and medical assessment from DTU. Okay, let me thank all of you for making this conclave a success. Okay, so now let's go to the next event. Thank you.
Thank you so much, sir, for your inspiring remarks. We have felicitation ceremony now for the jury members and other volunteers. We would also like to express our gratitude to the jury members of the poster presentation.
I think startups who have got the award, please come to the stage. Yeah. Let me just announce the name and please come to the stage.
Those who are around, please come.
So, FX UAV Technology Private Limited.
First started.
Vayu Rakshak Kinetics Limited. Yeah, all the startups, please share your bank accounts with IMMT.
No, he Vayu.
Good job done.
Third one is IRA. IRA team, yeah.
So there's a
So we would also like to express our sincere gratitude to the esteemed jury members of the poster presentation. Despite their demanding schedules, they graciously devoted their time, and on behalf of INAE, we extend our heartfelt appreciation to all the jury members for their invaluable contribution. I'll be calling out the names. Please come on the stage for the felicitation. Professor Uma Prasanna Ojha. Professor Uma Prasanna Ojha, please. Professor Sunil Kumar Sarangi. Professor Sayan De. Do we have Professor De with us? So next is Professor A.K. Tripathi. Professor Ganpati Panda. Professor B. Maji. Professor Maji, do we have Professor Maji with us? No. Professor Renu Sharma. Professor Devashri Tripathi. Dr. Devashri Tripathi. Dr. Venugopal. Dr. Venugopal. Thank you to all the jury members for their unwavering support and coordination. As we come to the close of the event, I would also take a moment to express our sincere gratitude to the faculty coordinators of SOA University. Their meticulous planning, unwavering support, and tiring efforts behind the scenes have been instrumental. So I am calling out the name of all the faculty coordinators of SOA University, including the top guru, and please, we request you to come on the stage for the felicitation. So, Professor Damodar Acharya, he is himself on the stage. We are grateful to you, sir, for your unwavering support. INAE is grateful on behalf of all of us. We extend our heartfelt appreciation for all the dedication, commitment, and gracious hospitality by SOA University. Thank you so much, sir. Professor Manas Malik, the director of SOA University. We are grateful to you, sir. A small token from Indian National Academy of Engineering, sir. Next, we are grateful to Professor S.R. Samantre from IIT Bhubaneswar. A small token. We are grateful to you, sir. Next, we have Professor Renu Sharma. Ma'am, your support backstage and in front of the stage is unwavering. Thank you so much. Your tireless effort, ma'am, we are so grateful to you. Thank you so much, ma'am. Dr. Sasmita Tripathi, ma'am, backstage, she was throughout with us. Thank you so much for all the efforts you have put in to make this event so successful. Thank you so much. Next, we have Professor Apul Narayan Dev from SOA University. Sincere gratitude to you, sir, for coordinating the event so well. Dr. Akshay Verma, he is also the individual member of Indian National Academy of Engineering. Thank you so much, sir, for your efforts to make the event successful. Dr. Abhijit. We have Dr. Abhijit with us. We extend our heartfelt appreciation for your dedication, commitment, and gracious hospitality. Mr. Prem, do we have Mr. Prem with us from SOA University? Mr. Shiv Patnaik. Sincere gratitude to you, sir. Dr. Lopa Mishra Jana. Thank you so much, ma'am, for all the efforts you have made to make this event successful. Mr. Debasis Parida. Mr. Debasis Parida. Next we have Dr. Ayas Chime. Ayas, sir, please. Thank you so much for all the efforts you have put in. Thank you. These were the faculty coordinators from SOA. We also extend our heartful appreciation to the student volunteers, though we do not have the list right now, but no event of this scale can be successful without the enthusiasm and dedication of the student volunteer, whose energy, discipline, and unwavering commitment ensured the seamless execution of every session. On behalf of Indian National Academy of Engineering and all the participants, we thank each one of you for your invaluable contribution. We have some names. I'll just announce the names. We'll be giving the certificates to you from INAE soon. We'll be sending it to Dr. Renu Sharma ma'am. So we have the names D. Satakshi, Mirka Nayak, Ananya, Apurva, Siba Prasad Panda, Vaibhav Krishnan, Ayush Sharma, Ayush Kumar Singh, Spandan, Abhijit Bagh, Ishan Mohanty, Shriya Sahu, Simran Sahu, Supriti, Balram Randhan Pradhan, and Priya Brat Sethi, Madhusmita Behra. So we are really thankful from INAE. On behalf of INAE, ladies and gentlemen, we want you to give a huge round of applause to all the student volunteers for their cheerful spirit all the time. They have made this conclave a memorable success. Thank you. we at the end of the valedictory session, we would like to felicitate our chief guest, Professor Shantanu Chaudhary. May we request Damodar Acharya sir to kindly felicitate the chief guest of the session, please. We would also like to felicitate, we would request Professor Damodar Acharya to felicitate the Director of IMMT, Dr. Ramanuj, please. Also, we have one request. We have one individual member waiting since long. She has been elected as an individual member. Dr. Nirja Batala, please come on the stage. We'll be giving her the certificate. Can we have a huge round of applause for her? She has been elected as an individual member of Indian National Academy of Engineering. One little appreciation for the transportation department. Since the felicitation is going on, the students volunteer of transportation department, they are also there. So we would like to take their names also once. Please, can we have a round of applause for Ankit Kumar, Anurag, Akhilesh, Anushman, Arpit, Mohit, Arshibad, and Devadatta. Thank you so much for coordinating and for the transportation and giving us smooth journey from airport till the campus and the hotel. Thank you so much. Now may I request, at the end of the Technology Conclave 2026, we would like to request Lieutenant Colonel Shobhit Rai, Deputy Executive Director, Indian National Academy of Engineering, to kindly address the gathering with the vote of thanks.
Distinguished guests, good evening. I know we have had a series of thank yous, but without a formal thank you note, the conclave cannot end, and we all cannot leave. So before we end the proceedings, let me say a very good evening to our respected chair of the valedictory session, Professor Shantanu Chaudhary, Vice President INAE, and I am extremely privileged to be here with Professor Damodar Acharya, who is the Chairman, International Advisory Board of SOA University, Professor Samantre, of course we have got Director CSIR IMMT with us, and esteemed delegates, guests, senior fellows who are here. Thank you very much for being here. It is my proud privilege to formally thank each one of you on the august occasion of this wonderful conclave. My sincere gratitude to chief patrons of the Technology Conclave, Dr. Manoranjan
Manoj Ranjan Nayak, Founder President, SOA University, Mr. J.D. Patil, President INAE, for their valuable and praiseworthy directions and counsel that made this meaningful event a reality in all its grandeur. Overall guidance and insightful contributions from the patrons of the conclave, Professor Damodar Acharya and Professor Santanu Chaudhary, who are there with us on the dais. I am extremely grateful to Professor Samantre, continuously helping us in getting these things together. The leadership, the plenary speakers, panelists, organizing teams, which have been, few of them have been named, unfortunately couldn't name them all. Delightful to have the privilege of listening to enlightening addresses by esteemed dignitaries on the dais in the inaugural session as well. We've had a wonderful session on the membership, and let me tell you the bit of a genesis that has been a brainchild of our governing council, largely inspired by Professor Indranil Manna and Professor Santanu Chaudhary, and supported vehemently by our president, Mr. J.D. Patil. And that is why we see this second conclave happening today. The first one was a stub, we learned. Second one was at its full grandeur. And who else to do than the one which a special task can be requested to, and that was INAE Bhubaneswar chapter. We knew that they will come good, and surely they have. Thank you so much to the INAE Bhubaneswar chapter and its esteemed fellows and all the team associated. The value addition to the technical content wouldn't have been possible without the help of the general chairs, namely Professor P.K. Nanda, Vice Chancellor, SOA University, Professor S.R. Samantre, of course, Professor Tapan Kumar Gandhi, Head of Biomedical Engineering Department, IIT Delhi, who helped us in conceiving of this event, Dr. Malik, Director SOA, Dr. Renu Sharma, Dr. Tripti, and many others who have been associated with us. All the teams of the organizing committee, program committee, finance and sponsorship committee, you see those number of names there. Thank you to you all. Because of them, we have now a large number of sponsors, other associated committees such as venue management, food and hospitality committee, accommodation, transport and logistics, registration, publication, media, web and IT, cultural committee, who had a wonderful performance yesterday evening for their deep-rooted commitment and sincerity. I would be failing in my duty if I do not name some of my colleagues of INAE who have been working right at the background at the behest of this academy, and my team members. Of course, we have Colonel Atul Sharma, a pillar of INAE, Ms. Mimansa, who hosted the event, Mr. Rakesh Antil in the background, Mr. Pramod Gaware, Mr. Shivam conducted the sessions for the paper presentation, Mr. Sheetal Sharma, our IT expert, Mr. Piyush Sharma, our transport person, and our social media expert, Ms. Vishakha and Mr. Shivam. Thank you to you all, and I am full of gratitude towards SOA University, Professor Acharya and all others for making this happen. Thank you on behalf of INAE, and Jai Hind.
Sir, just a moment. We have one faculty whose name has been left, and Mr. Umar Shankar Biswal from Transportation Department. If you have him here, please come on the stage and take your memento. Mr. Umar Shankar Biswal, please come on the stage if you are here. Yes, yes. His name was actually left by mistake. Please come on the stage.
We close the Technology Conclave 2026. Thank you.